welcome everyone to day 2. A few less people in the room today, for some strange reason. Hope everyone had a good night. Just a couple of bit of housekeeping. So all the usual stuff. If you weren't here yesterday, if there's an earthquake, drop and hold and follow venue instructions. If any other emergency occurs, again, just follow the venue instructions. Toilets are out there around to the left. The only other thing is in your swag bag you do have at least one battery or juice pack, so just bear in mind nowadays that cannot go into your check-in luggage, and I think on most airlines it can't even go in the overhead lockers. It needs to be under the seat in front of you, so just be careful on that. Check your swag before you fly or whatever. Anyway, without further ado, we've got Matthew Hayes here to talk about data center interconnects. So welcome to the stage, Matthew.
Good morning. It's always challenging when the first thing you see walking into the room is a bucket of Red Bull. So I hope you guys had a good night. Hopefully the Red Bull is helping to stay awake. First presentation on day 2 is always an interesting time zone to click into, but hopefully the topic will be a good one for you guys to cover off. So, as mentioned, I'm going to be talking about data center interconnect. From an agenda standpoint, I'm going to run through a few market insights. I do not know what that slide is. That is not my slide. See? First presentation on day 2. What happens there? Slight technical challenge there. But maybe it is a programming language. It's not one that I've come across. There we go. Thank you. So after that quick, I'm not going to use the term, programming interlude, just let me touch on a few market insights. Obviously, globally, we still see a number of macro challenges. I thought the conversations around inflation, exchange rates, were a thing of the past. Now, living in Australia, I was proved very, very wrong because we've just had a 0.5% increase in our interest rates. The New Zealand economy seems to be fairly stable. I think you guys have had a halving of the interest rates over the last 18 months, which is a positive sign. But of course, the continued geopolitical challenges are driving uncertainty and instability within the marketplace. There's always discussions around tariffs. The T word never seems to be going away. And I think ultimately, the telco industry is also going through some very subtle changes in terms of how we operate and how we work with the customer base. And of course, a lot of that is driving what I will call a supply and demand chain challenge. Demand for product, demand for high capacity product is certainly through the roof, and it really is a struggle to keep up with those requirements from a global customer basis. And I think I talk across the whole vendor community when I talk about that. If I look at the opportunities, though, it's not all grey skies and storm clouds. There is a huge amount of investment going into the market, right? You've probably seen a few press releases recently around AI investments. You'd have seen the bandwidth requirements that are driving some of these AI investments. And also, I think from a networking standpoint within the ANZ market in particular, after a couple of years of fairly flat CapEx growth, I'm now starting to see more and more investment coming into the network infrastructure. So there's certainly positive signs of opportunity coming through. Now, if I look at industry and just take the service provider market to start with, there's obviously some key drivers within that marketplace, right? So from a 5G perspective, I think certainly from an Australian market perspective, the 5G rollouts have saturated themselves. There's not a lot more investment going into the 5G infrastructure builds. However, there are architectural changes being made within the RAN networks to move to more cloud RAN architectures or standalone architectures. From an enterprise standpoint and from a residential standpoint, the market seems fairly flat. Enterprise services seem to be on a downward tick, mostly from a legacy technology perspective, but I think they will level out and drive a little bit more growth over the next few years. There's certainly two areas that are influencing the service provider investment community. Of course, AI is one of them, and the second one I see is the LEOsat market, specifically from a backhaul perspective. If you look at the new constellations that are being deployed and talked about, it seems to be around a 10-fold increase in the backhaul capacity that's being required for some of the LEOsat constellations. Right? And I think ultimately, and there was a talk yesterday around network transformation, I see a lot of network transformation discussions taking place across the service provider patch, moving away from legacy siloed networks, focusing on OpEx reductions, and driving more automation for operational efficiency. If you take the AI and the cloud providers, it's a very different trend. There is massive build, there is massive scale. We talk about designs now that are scale up, scale out, and scale across, and I'll take you through some more details on what that looks like. And ultimately, the design specs are very, very different to the ones that we would traditionally see within the carrier space. Just to touch on some of the New Zealand market dynamics, there's a couple of diagrams there. It's hard to read all of the text, but there was a really good white paper released around a month ago from Boston Consulting Group around the data center market within New Zealand, and specifically the opportunity for data center growth within New Zealand. The current view is that there's around 125 megawatts of data center capacity. That is expected to grow to around 300 megawatts in the next 2 or 3 years, and the recent announcement that came out from DataGrid is a good position for the view of that data center growth. And I know that Pierre, I don't know if Pierre's here, but Pierre will be talking about data centers, specifically DataGrid's investment this afternoon. So I won't go into too much detail on that. If I look at some of the data points around bandwidth growth, the good news is that everything is on a hockey stick in the upward direction. The bad news is I think we've completely underestimated some of these growth figures. Right? If I take network bandwidth as an example, it's grown more than 30% in the last 2 or 3 years globally. Right? So I see that continuing, if not increasing to 30-35% year on year. Data center bandwidth, obviously, we're seeing huge requirements for data centers. Globally, the build-outs of data centers are increasing. I think in Sydney alone, I read the other day that there's 15 applications into the local councils for planning permission to build data centers, right? So that is a massive growth area across the globe. And of course, that in itself brings challenges because high-end data centers, especially AI-enabled data centers, require very, very high power requirements, right? More than the traditional data centers that we have today. And I'll touch on that in a second. So there is a bit of a revolution from an infrastructure perspective going on. And I look at it in 3 parts. From a scaling perspective, I've mentioned scale up, scale out, and scale across, and I will touch on that again in a second. We see networks now being more distributed. And when I say distributed, capability being positioned in different parts of the network. From an optical perspective, we're seeing photonics and the modems being disaggregated and deployed at certain locations where it makes sense to do so, and converged networks taking place as well, so optical and IP convergence. From a reliability standpoint, certainly the hyperscalers and the AI players refer to this thing called RAS, reliability, availability, and survivability or serviceability. The reason for that is because when they're running huge large language model training capabilities, what they call training stalls has a big impact on the cost of running that network. So as an example, Meta predicted if one of their training models stalled for about 30 minutes because of network outage or link flaps, that would cost them around $200,000 to $250,000 in lost money based on the number of tokens that they're going to have to use and purchase up front, okay? So reliability within networks is even more critical now than it ever has been. And then from a power and cooling perspective, I have touched on this a little bit, but ultimately the power required on a per rack basis when you move into an AI training and inferencing world is 10 times the power that you would have in a traditional data center, right? We're now talking gigawatts of power for data centers, and there's a couple of examples coming up in a few slides' time. If I just look at the global data center market, there's over 10,000 data centers around in operation right now. Traditionally and typically, they are really servicing wholesale customers, colo customers, interconnect, cloud on-ramps, right? But now we're starting to see a proliferation of AI-enabled capabilities, and those percentage rates at the bottom were take-up rates within data centers that are now converting towards AI stacks, okay? That is envisaged to move to around 70% of global data centers in 2030. Just to equate that to a power requirement, that's around 77 gigawatts of power globally required to run AI-enabled data centers, right? So when you talk about the data center world, you have to talk about power, cooling, and also capacity, right? So I have touched on scale up, scale out, and scale across. So traditionally, when we refer to scale up, that's building capability within the rack. That's bringing in more storage, more compute, GPU as a service, as an example. Then we move to a scale out architecture, which is rack by rack, or data center floor by data center floor, or pod by pod. A lot of data centers, certainly the ones that I talk to in Australia, will pre-sell a half of a data center storage, and then they will keep the remaining for power, and typically a single customer will come in and buy the remaining footprint of that data center floor, right? So as an example, I think NextDC in Australia have pre-sold all capacity, current and planned, for the next 3 years. So this is pretty huge capability that we're talking about. And then, of course, there's scale across. And the reason why scale across is important is because the typical metrics that we would use to build data centers are changing. So now we're looking at where can we get the land access, where can we get the power, and where can we get the cooling. They are the most important things to build a new data center, right? It's a little bit easier to then build the capacity to those data centers. So this scale across model is really being architected to ensure that the hyperscalers, the AI players, the data center players can build diverse, scalable DCs within 20, 50, 100, hundreds of kilometers, right, to build that diversity into the training models. Now, of course, associated with the data center models in terms of scale up, out, and across, there's different photonic and optical platforms that can be used to drive that capability. So within the data center, you can typically use cables because the distances are very short. Moving into a scale-out model, we're now starting to talk about near-packaged optics and co-packaged optics alongside the traditional IMDD optics. Coherent pluggables are always talked about from a interconnect perspective as well as a low-cost way to do it. And then from a traditional build-out from a long-distance perspective, then we talk about high-performance modems and also plugs, right? So it's a market that you can use to drive very different architectures and technologies. Now, just to give you a little pictorial in terms of some of the scale that we are seeing across the market, there's 3 diagrams there. The one on the left is a metro campus fiber duct infrastructure that was being built for a very large hyperscaler in the US. And typically what they're looking to do here is to build, as I mentioned, resiliency in the data center and resiliency into the training models. Now, this particular customer lit 384 fiber pairs, full C&L band, to deliver 34 petabytes of traffic, right? So the kind of scale that they're talking about is in the petabytes now, right? Not within the terabytes. These two data centers, so the Microsoft Fairwater is a 1 gigawatt facility purely for AI learning. They are building another facility in Atlanta, which is around 700 kilometers away, and they are connecting that with multiple fiber pairs to build the same level of scale. All right? And then Meta has announced, and I think they've broken ground on Hyperion in Louisiana. This is planned to be a 5 gigawatt facility. Now, just to put that into perspective, 5 gigawatts of power is enough to power the whole of Manhattan from an electricity standpoint, right? So the conversation when it comes to data centers and builds is around how much power do I have access to, how much do I build from day one, and where are the customers going to come in to use this capability, right? And I mentioned traditional data centers. So we know that a traditional data center from a CPU and compute perspective draws around 10 to 12 kilowatts per rack. When you look at the NVIDIA chipset, and especially the Grace Blackwell, which is the current release, that requires around 110 to 112 kilowatts per rack, right? When we move into Rubin, which is the next iteration, that will be released in 27, and that's being talked about for more around the inferencing stage of AI. That is going to be pulling around 200 to 250 kilowatts per rack, which is why you see the scale of these big multi-gigawatt data centers being built now. And the architecture, of course, is very different from a traditional data center to a high-performance compute data center with GPU as a service. So why, in particular, does AI need connectivity? You might think that just by training the data, all you're doing is ingesting and running the models and running the learning activities. That is true when you're in the initial training phases, but as I've mentioned, the AI players, the hyperscalers, are looking to build scale across these data center footprints. So they're building scale across models, and I've already mentioned a couple. But the reason to do that is to overcome power and space, as I've already mentioned, but also to run distributed learning capabilities, right? So dense photonic architectures, point-to-point solutions are really the key to driving the capacity models for this scale across model. When you move to an inferencing stage, this is when the applications are available for use within the enterprise, within the residential, within whoever the customer is, right? Now, this is where the network becomes really, really important, because a lot of these applications require high speed, low latency capabilities. The models are agentic, they require instant response, and the actual capability that the user is expecting, the user experience, requires a much lower latency capability from the network. So that's where it's really important that networks that are being built today have the ability to run low latency capabilities. And of course, one of the reasons that we talk about that within the data center world is because we believe that the optical portfolio and the optical technology platforms are the ones that can truly drive the lowest latency within the data center interconnect models. And the way that we look at it within Sienna is we can look at it from a campus perspective, a metro DCI perspective, a backbone. So these could be long haul, and in Australia, you know, we're talking about Melbourne, Sydney, or we're talking about Melbourne to Perth as an example. Here, you could be talking about, you know, metro DCI connections from Auckland down to Hamilton as an example. And of course, there's the submarine capability as well, because we have to ensure that the submarine capacity that's bringing in the data that's being ingested into these AI models is as close to the data centers as we possibly can get it, right? And then, of course, there's the new paradigm, which is scaling within the data center and running some very low latency interconnect models using different photonic architectures, and I'll touch on that in a second. So if I look at some of the consumption models, I think a lot of you, if you're familiar with optical networks, you'll be familiar with the transponder and the muxponder technology. These are very high performance modems, which we can now drive up to 1.6 terabits per wavelength, okay? We're seeing a very different market shaping now, and that's more around a pluggable form factor, right? So coherent modems are now being deployed at mass scale using 400 gig ZR, 400 gig ZR plus optics into data centers, right? That allows low cost insertion, that allows more flexibility when it comes to some of the deployment models, and ultimately the interconnect points between the optical network and the IP network are a lot simpler. In fact, we're now seeing converged architectures coming in where coherent modems are being deployed directly into the router ports. As we see this expand, coherent pluggables become just as important, right? We're now seeing 800 gig ZR, 800 gig ZR plus, and now we're talking about 1600 ZR and ZR plus optics being developed. The interconnects between the transponders or the optical photonics into the router layer become even more important, and that's where we're starting to see some of the co-packaged optics and the near-package optics being deployed within those models. And then moving on, there's new MSA capability, XPOs, extra dense pluggable optics, which can support terabits of capacity on a single plug. I've seen Arista around. I know Arista have launched some XPO plugs. That is going to be another shift in terms of the capability and the capacity that's being deployed. And ultimately, these are being deployed either within transponders, so Ciena is looking at that from a technology investment standpoint, but also directly into the router platforms as well. And then the next instantiation that we're working on within Ciena is this concept of full spectrum transponder, or FST. So if you take the example of a point-to-point data center, typically you don't need any ROADM architectures or structures because the data is literally from point A to point B. There's no drop sites required. So really using many, many transponders or many, many plugs is somewhat inefficient and power hungry. So we're developing full spectrum transponder capabilities to run a full C-band in a single capability. And eventually we may even see that being pushed into router platforms as well. So just to touch on some of the architectures, I've mentioned power capacity cooling. So we're moving from megawatts to hundreds of megawatts now into a gigawatt world. So the unit of currency is tokens, it's gigawatts, and it's petabytes of data, right? Now I know that it may seem that that's a fair, far journey within the New Zealand market, but I think if you take some of the AI data sovereignty requirements, certainly within Australia, there's a lot of companies now being set up to run sovereign AI data center capabilities. Firmus is one example of that. I see no reason why New Zealand couldn't also run a similar model and build commercial models and commercial frameworks to then host some of the neo-cloud opportunities that come through into the market. And then, of course, if I take a network, and this is a rough example, and please excuse my geography, I don't know the full distances between Hamilton and Auckland. That's as the crow flies. I know the fiber distances may be somewhat different, but typically, if I look at a 400 gig plug architecture versus a full performance transponder, you can see the differences in the number of fiber pairs required to run terabits of capacity or even up to a petabyte of capacity. So of course, yes, there's efficiencies to run on a coherent modem, pluggable modem, but by running full-scale transponder architectures and performance modems, you do get efficiencies and economies of scale when it comes to fiber exhaust and fiber requirements. Now, if I just look at some of the growth opportunities, obviously from a traditional access perspective, we see the market driving up to gigabit speeds. In certain enterprises, they're now starting to look at 100 gig, potentially 400 gig services. From a bandwidth or a wavelength perspective, 100 gig wavelengths are the norm. 400 gig wavelengths are absolutely coming through, and now we're talking about 800 wavelengths and 1.6 terabit waves as well for high scale. You can add extra layers of encryption for security applications on top of those platforms. And a lot of it now is, from a Sienna perspective, is quantum secure. So we can run now quantum-enabled encryption services. If I look at cloud players, typically the model for cloud players is that they will buy wavelengths from a capacity standpoint, which is great for the provider, great for the CSP, because it is a much stickier service that you can control. There was a time, and it still happens now, to be fair, but operators were selling dark fiber assets directly to the hyperscalers, which is exactly what the hyperscaler is looking for, right? Because then they can control the whole asset themselves. But the CSP loses the ability to then control the capability and then to upsell any more services into that player. So now we're seeing waves moving into what we call managed optical fiber networks, a MOFN. That's the ability to lease a fiber pair, but build a service on top of it, right? So you still control the capability and you still own that fiber service. And then we're now looking at terrestrial spectrum leasing as well within domestic networks. That's been around in the submarine world for many, many years, and now we're seeing that being deployed terrestrially across the globe. And then from an enterprise perspective and a cloud on-ramp perspective, we're now seeing a lot of fabrics being built. Obviously, Megaport is a fairly well-known global brand. I know Megaport are in the room here somewhere, but we're also seeing optical fabrics also being built globally. Lumen is a good example of that with their PCF, and it offers very low latency, very high capacity on-ramps for enterprises and for the cloud players. Lastly, just to touch on some of the technologies that I think will be driving transport innovations and optical network innovations over the next 5 years. OFC is a very large optical event that took place 2 weeks ago at the same time as GTC, which is the NVIDIA user conference. At OFC, a number of vendors, including Sienna, presented hyperrail photonic solutions, which is really designed to bring efficiencies into the amplification capabilities. So being able to run hundreds of fiber pairs within a single rack unit from an amplifier perspective, and again, that is key for these scale-across applications within the data centers. I've mentioned full spectrum transponders. Liquid cooling is absolutely a key area that is being invested in from a Sienna perspective and from a general vendor community perspective. As we drive towards the Shannon limit, we drive more watts per bit, we drive more power into the capability. We cannot rely on air cooling anymore, right? We have to rely on liquid cooling to cool the chipsets and also within the data center and for the data center. So liquid cooling is going to become extremely important. Digital twins, I think most people are fully aware of that. Network as a sensor, so that's fiber sensing within the domestic networks. That technology is being utilized now globally, right? So fiber sensing will be a very key asset for every operator to investigate from a network security perspective and from an operational perspective. And then, of course, there's hollow core fiber, which, you know, I think Microsoft announced a week or so ago that they've managed to deploy up to 300 kilometers of hollow core fiber. So the application is there for metros, for data center to data center connectivity, but pushing the boundaries over hundreds of kilometers is going to prove challenging from a manufacturing standpoint, but also from an operational standpoint, right? Because it's not a traditional fiber splice that we look at here. This is a vacuum, effectively, okay? So these are the 6 areas I think will be transformative over the next 3 to 5 years. And finally, just a few takeaways. I think, you know, whilst the New Zealand data center market is, I'm not going to use the term nascent, I would say it's emerging because there is a lot of opportunity out there. And I think now that DataGrid has got the permission to build and connect, you're going to see a lot more activity within the NZ market. The dynamics are changing. You've seen some of the data points here, right? We're now moving into a a gigawatt world and a petabyte world. And ultimately, I think the technology innovations that are being driven across the vendor community, not just within Ciena, are going to open up more opportunities for the customers to then drive capabilities. That's my talk. Sorry, I'm slightly over, but I don't know if I've got time. If there's a question in the audience, I'm happy to take a question. Not too technical, though. I haven't had a Red Bull yet. No questions?
No, looks like no questions. You're off the hook.
Oh, there's always one.
This is for your crystal ball.
Yes.
How many data centers of that scale do you think New Zealand can realistically support?
New Zealand?
Yeah.
So I think within the New Zealand market, we're really realistically talking about hundreds of megawatts in terms of data center build. I don't think we'll be looking at gigawatt facilities just yet. I think Data Grid was 280 megawatts. If I look at Australia and the Sydney market in particular, the largest data center build that we have there right now is 550 megawatts next DC. That is sold, and it's not even been built yet. I think the gigawatt facilities will most likely stay in the US for the next 2 or 3 years. We may start to see it encroach through Europe and maybe up into the Asian peninsula. But I think for the time being within Australia and New Zealand, we're really going to be focusing on the hundreds of megawatts as opposed to the gigawatts. That makes sense. Okay. All right. Thank you very much. Cheers.
Thank you, Matthew. So our next speaker, I believe, has travelled the furthest to be here out of all of our speakers. They're long-term supporters of NZNOG, have been coming here for many years, sponsoring us for the last few years. I think one of our favourite optical vendors in New Zealand now. Anyway, welcome to the stage, Thomas from Flex Optic to talk about Channel Mania. Thank you, Thomas.
Perfect. Thank you very much, Dave. I have to get sorted. Oh, perfect.
Cool.
Thanks. Hi, good morning, everyone. Yeah, I'm pretty sure every one of you already made that experience. You have a great conversation with someone, and then afterwards you think, hey, that's an interesting topic, I want to know more about it. And then it turns out to become a brain fuck, or you think, hey, this is really deep dive into it. Actually, this happened to me last year at the RIPE meeting in Lisbon. I had a really, really great conversation at the social in the evening with Blake Willis. He's somehow a layer 2, layer 3 engineer, but also very, very good in optical transport. And our main topic was IP over DWDM, and then we jumped straight into coherent pluggables and coherent transmission in general. And we figured out, hey, there is this tiny thing, the balanced receiver inside, and what makes it so special? We couldn't fiddle it out during that conversation. We had a couple of beers as well. So I took that back to Germany, where I'm coming from, and discussed it with my colleagues in the company. And yeah, it turned out this topic is the coherent balanced receiver, all about this colorless when it comes to IP over DWDM. It turned out to be really a brain fuck in terms of, hey, we have to understand this. And the result I'm going to present today, because the clicker likes me, not? Nope. No, now it's working. You have to press harder. Okay. And yeah, we were looking into the perspective in terms of IP over DWDM. In a nutshell, is basically, hey, you get rid of your transport equipment and you do the transport by yourself in your layer 2 and layer 3 equipment. Now, that's an easy task, but when you look into it, you will figure out there are way more parameters now you have to take care of, which previously did your transport people. Now you have to do it by your own. And I think it's quite helpful to understand the foundation where these parameters are coming from, and also, especially when you want to set up a network, and even more important when you want to troubleshoot it, what is the impact? And yeah, that's basically the talk about the Channel Mania one. But let's start easy. A transceiver, a pluggable transceiver, is pretty simple. So we have basically three major components in these days in there. We have those two tiny golden boxes. One is the transmitter on the top one, and then below there is the receiver. Together this gives this artificial world transceiver. And then the digital signal processor who does a little bit magic with the signal, especially when it comes to the modulation. And for the first run, we're gonna focus on the transmitter. A transmitter in general is a laser source. And lasers have been around for a long period of time, even back in the 50s and 60s, but those ones were not usable for us in telecommunication. The first usable laser was in the 70s developed because it was operated at room temperature, and that's a critical thing. You don't want to cool your transceiver with liquid nitrogen or something else to keep the laser frequency stable. No, you want to operate this at room temperature. And from there on, it's history where we are today to make them very small as well, to fit in those tiny modules. Now, when we look at the spectrum itself of a laser, on the top left corner, the purple one, this is the spectrum of an LED. It's really broad, this nice bell curve shape there, and the line width I showed here is roughly of 100 nanometer. It's a really floodlight, basically. And now with 1 gigabit, Fabry-Perot lasers were introduced. They have this very characteristic double peak or triple peak curve, and the line width got even narrower to 10 nanometer, or in other words, in frequency, 1.75 terahertz. And in the area of 100 gig, DFB, distributed feedback lasers, were very important. And basically the main goal was to get the line width of our optical carrier in the middle very narrow to 125 gigahertz. But still, for 400 gig and above, this was not sufficient. The external cavity lasers came into place, and the line width is now at 1 megahertz. Actually, it's just a peak. So this was the main goal, to have a really precise, stable laser at a certain frequency with just a peak and not like a curve. So when you look at how to want to increase the traffic on a fiber, you basically have two choices. But in general, in the top graph, I show the optical carrier. That's our center frequency of the laser. And then there is this bell curve. That's where our information content is encoded or modulated, basically. Now, on the left side, you see the traditional approach, what you have done already in your networks when it comes to on-off keying mechanisms for the 10 gig or even 1 gig. We slice down the spectrum with filters in different colors. Okay, compare it with the white light, and you use a prism. You have different spectral colors. That's basically what happens with the multiplexer. You have different colors there, you separate them. But you lose spectrum, especially between two filter blocks. You lose spectrum which you can't use at all because the filters have to distinguish between channel left and channel right. The other way, or the other approach, is you broaden your spectrum in general, the optical bandwidth, and feed in way more information to one carrier. And that's actually done for Coherent now. So far, this was the easy part, and now let's focus a little bit more on the receiver, and we're getting now to the complex numbers again, like a little bit like last year on NZNOG meeting, but not that much. What is a receiver? A receiver is a diode. You see it in the middle. It's a pretty simple component. When there is light hitting the diode, it's opening up, current is flowing through, we get a 1. When there is no light, the diode is closing, there is no current flowing, we get a 0. And this was the typical approach in direct detection. So you use light, turn it on, turn it off, and we got zeros and ones. And we did this in a high frequency manner in the gigahertz range. Now, when we look inside of our 1 and 0, which I show here on the left side, inside there is a lot of things happening. There might be a phase change, or even the frequency is going to change. But the diode itself, it can't distinguish. For the diode, this is either light on or light off, but nothing else. So there is a lot of information in there, but we can't use it, or the diode can't use it. So we need a way more better approach to get this information inside of within that light level, basically. Okay, So when we now take an example again, the 16 QAM modulation, no worries, I don't want to do too much on the 16 QAM today. We have those 16 constellation points. Each symbol, 16 symbols, can represent 4 bits in total. And we can encode a lot of information there, 4 bits with those 16 symbols. But the interesting part is, where is a single dot located within our diagram? And to figure that out, we have 2 choices. You see this on the right diagram. Either we follow the blue path, we use a vector and an angle, and we can do the math, which we have done in high school, and then we can find the position of that dot. Or the alternative, the orange way, is we use the straight, or the direction of the quadrature component on the y-axis, and the in-phase component on the x-axis, and then we do a triangular formula based on a rectangle triangle, and we can even calculate then the position of that point. And the INQ component, that's the important thing later on, also for the DSP to do the math. Okay, now to that receiver in general. A single-ended receiver, what I have showed at the beginning was shown in the top one here. There is a receiver, he gets a signal and does a detection. But before the signal hits the receiver, we do something special. We use an optical coupler, and this coupler has basically 4 legs, 2 incoming, 2 outgoing, and it does just combine 2 signals and distributes it on the 2 outgoing ports. This coupler has some benefits, and you will see that now. So the first, when we look at the incoming, we have our desired signal, that's the orange path. We get the optical carrier and also the information content around our optical carrier. And then on the second leg, on the incoming port of the coupler, we use a local oscillator. We are still at the receiver, but what a local oscillator is, it's actually a laser source. So we use a second laser source, a second light level, and feed this into the coupler. And the coupler has a great benefit. It does combine them both. And due to the fact that the local oscillator and the optical carrier are almost at the same frequency, we get rid of them. So we just basically get the information content, which we call now the down-converted signal. It has a way lower frequency, that signal. We are not talking about terahertz any longer. We are more in gigahertz. That's the single-ended version. Now, when we look to this bottom example, that's the balanced receiver. The incoming ports look the same. We got the optical carrier and also the local oscillator combined in the coupler. But now on the both outgoing legs, we have 2 photodiodes detecting the signal. And the interesting part happens in the coupler, actually, because the coupler is an optical component, and it also has a characteristic that cross ports. So the incoming top left one and the outgoing right bottom one, the phase is shifted by 90 degrees. The same occurs to the top outgoing port, also the phase is shifted, and as you can see, either the local oscillator is phase shifted, or the optical carrier or optical bandwidth is phase shifted by 90 degrees, and when we hit them both on 2 diodes, we get 2 signals, and when we combine them, like back in high school when we have 2 waves, same at the peak, what happens, they're gonna accelerate them to a higher level, and that's a pretty helpful thing now. So our down-converted signal achieved way more gain. It got stronger. So we get less noise and more output of that signal, just out of the fact that the coupler does a phase shift, and we have now 180 degrees in total of a phase shift. Now for Coherent, this is not all what we need. So now we have the signal in general, but we still have this INQ component which we have to distinguish. How does this happen on the phase diversity side? Well, it's actually, we double it. So we have 2 of those detector components with the coupler, but the local oscillator itself is phase shifted for the bottom detection pair again. And then either we can detect the Q component on the x-axis or the I component for the top part. And here we go. We got I and Q, and then we can do the math to get the phase information out of our signal. And last but not least, and together this is called an optical hybrid. And now we have 2 optical hybrids, because what we do now, we take our signal, and as we have polarization as well in light, like wearing sunglasses or the privacy screen on your screen of the laptop, we can use a beam splitter, a polarization beam splitter, and split two polarization direction and fed it into two optical hybrids. So in total, there are 8 laser photodiodes in a balanced receiver or a coherent receiver in general. Okay, so as I said at the beginning, it's a little bit tricky to understand this all, but while we were working on it, we figured out this is getting more rocket science now, and we are on the way to build a rocket. That's what we do now. But before I jump into that, what we have gained so far, when we look at the current development on 400, 800, and 1.6 terabit, so we need more optical bandwidth, more to feed in there. And typical approaches for 400 gig running at 16 QAM modulation, it's 75 gigahertz of optical bandwidth which is required. For 800 gig, it's a double amount, 150 gigahertz. And as you can imagine, for 1.6 terabit, it's even, again, double amount, so roughly 300 gigahertz. So you need 300 gigahertz of space on your fiber to feed in there. This won't work with traditional multiplexers, which were typically in the 50 or 100 gigahertz range. So we need something a little bit greater than 300 gigahertz to put into a filter. So a good example is a 400 gigahertz filter, because we still get a little bit space, and they are commercially available off the shelf. When we compare this, that's also where the title of the presentation is coming from. This Channel Mania was an approach in the past. When we looked at the C-band, we were able to do 96 channels, 10 gigabit, sliced down with 50 gigahertz filters. Pretty great, but we lost a lot of spectrum between the filter ports, and we had a lot of channels. Now, when we go towards 400 gig and above, we want to reduce the amount of channels down to 12, for example, when we have 400 gigahertz filter blocks. And then we can feed in there either 400 gig, 800 gig, or even 1.6 terabit. If we only do 200 gigahertz, then, well, the 1.6 terabit won't be a solution and won't fit through those filters. That's pretty simple math. Okay, now back to converted signal, because there is also one important thing there. When we down-converted signal, things also happening, and there's also a drawback of the coupler. And the first approach is the heterodyne way. As I said at the beginning, we have a local oscillator and our optical carrier. And when they are not at the same frequency, things happen that we also get a mirror frequency. So the optical coupler combines it, that's great. And we want to get rid of our optical carrier, but when the local oscillator has some offset, and it will have some offset, then we get a mirror frequency as well. And this mirror frequency, again, can be in the next channel and interfere with that next channel. So we don't want to go for a heterodyne approach. And because we down-convert that signal, and the difference between the local oscillator and the optical carrier is, in this example, for example, 622 gigahertz. And 622 gigahertz to detect on an electrical way is still a big challenge. Not impossible, but a really big challenge when we talk about small scale inside a transceiver. So, obvious, the other way would be to do a homodyne way. Precisely set the local oscillator to the same frequency than our optical carrier. Technically, this would be possible. The great thing is there is no intermediate frequency, because they are at the same frequency, and the offset is 0 gigahertz. To detect 0 gigahertz is great. Well, the challenge there is to get this so precise, and it's expensive, and you need special components like an optical phase lock loop, and we don't want to fit that into a transceiver. So the combination of both is the intradyne detection. We get the local oscillator as close as possible to our optical carrier within the range of the optical bandwidth. So the mirror frequency is not an issue for us at all, because we are still within our filter. And the intermediate frequency between the local oscillator and the optical carrier is getting down to a range which we can detect easily. For example, here, 5 gigahertz. And to detect 5 gigahertz is quite simple. Or in other words, when you tune your receiver to a certain frequency, he only sees what he wants to see. And that's a really important thing, because that's the foundation for colorless, and that's all we get out of the balanced receiver, because the receiver is now tunable on an electrical way, and he takes the desired signal, which is desired for him. When we tune it a little bit away, he doesn't seize the signal any longer. Yeah, so we basically made it now. We built a rocket, we can fly to the moon, but as you can imagine, behind the moon there's a little bit more. What can we do now with that? On the left side, I still stick to the 400 gigahertz filter block. On the left side, you're gonna see the traditional approach. You can feed in 8 channels of 50 gigahertz on-off keying within a 400 gigahertz filter when you cascade it. Pretty simple. Now on the right side, we call this the DIY superchannel. You can feed in 4 times 400 gigabit if you want to, and you don't have to separate them with an additional filter. What you can do is, and the pond people will know that, you can use a pretty cheap splitter and just split the signal, the optical signal, and what you get then looks like this. On the left side, we see a combination of our signals, the on-off keying 10 gigabit, and also the combination of the 400 gig signals coming into our 400 gigahertz demultiplexer. The top path is the traditional approach, feeding everything into a filter and separate each channel per frequency or with a demultiplexer. But on the bottom path, we just use a splitter and split our signal to 4 legs. So every receiver, so the blue, green, yellow and red one, they get all 4 times 400 gigabit, but as we can tune the receiver, the red receiver only sees the red signal and discharges the other colors like blue, green, and so on. And even more, what you can imagine, and for the yellow, the same applies, and for the green one as well. And now you can think about new designs as well. So for example, you could say, well, on the left side, there is my core data center. We have there a coherent plug. And on the right side, it's not only one device now, we have 2 devices. They are tuned to the same channel, basically. And then if one is failing, you can swap over to the other one, and then you have a triangular combination, so one device can take over and stays on that optical path just by tuning the receiver into that frequency. When the first, like the blue one, is failing, you can jump on that channel if you want to without unwiring your whole network. You can do this with the CLI, basically. And that's, in summary, an important thing. As I said at the beginning, there are way more parameters now for coherent plugs. And one example is when you look on the CLI now, you see the optical signal power, or the optical power in general, but you will also see on the CLI in the future with coherent plugs the optical signal power. And the optical power in general is the light level of what the receiver receives, and the signal power is actually after we get this down-converted signal when the receiver is tuned to that certain frequency, and that's the desired signal we want to look at it. And if there is an offset, for example, to your light level, then something is broken and you might end up with bit errors, or even you're on the wrong channel tuned. And yeah, the great thing is the colorless. It's a pretty amazing thing what you can do now in the network designs when you think about the DIY superchannels I showed previously. And for me in person, the most important change was not to think in nanometers any longer, or even channel numbers, although this was in the past a mess with the ITU, and Cisco made their own channel numbering. No, you have to think in terahertz and gigahertz now. That's, in my opinion, the biggest change, because otherwise you will screw it up, or there is a misunderstanding when you talk to someone else. And as Matthew already mentioned in the previous presentation, in this whole new universe now, what we can do, yes, there are new things coming up. I'm personally pretty impressed about the XPO approach, doing 12.8 terabits, and there is actually liquid cooling inside of the plug itself. So I have seen them on OFC, and there were really two incoming legs where the liquid is going through the plug. It's pretty amazing mechanics. It's getting a little bit bigger though, but it's pretty awesome. And with that, I want to finalize my presentation. Thank you very much. And let's see what's going to happen on the next social and which topic will arise there. Thank you very much.
Any questions for Thomas?
I never in a million years thought we'd need a plumber to plug in an SFP, but apologies if I missed this, but is your tuning of those optics in software or hardware, can we have one optic and reconfigure it to be on a different wavelength, or is it a hardware change?
No, it's a software change. You do this on the software side.
No worries, thank you.
Yeah.
Jeff Houston, you know, Nirvana for me is wavelength agile cross connects, where you inject light at one frequency, I want to send it out at a different frequency through my cross connect. Will it happen in my lifetime?
It's a question, Jeff. Thank you very much. I hope you will live for a long time. All right. I don't know, to be honest.
Anyone else?
Yeah.
No, you're
Okay.
off the hook.
Oh, I have a question for the audience. We have to leave a little bit earlier today, so we're going to be until the end of the conference, but then we have to go straight back to Germany. And we have 2 tickets for the dinner tonight at 5 o'clock for the 3 course. So who wants to have them? They are paid. Here we
That's
go.
the tramway dinner. Yep.
Here we go. And yeah, with that, we brought some gummy bears with us. Take them. I leave them here on the stage.
Thank you, Thomas.
Sure.
Okay, I think that broke my Friday morning brain. So next up, we've got Warren Finch talking about open fiber data standards. Welcome to the stage, Warren.
Hopefully it doesn't make it too hard for the cameras up the back. Good morning, everyone. We've had some very technical talk just then, and then we had the hyperscaler capability. Now I'm going the other way, looking at terrestrial fiber and giving you an introduction to the open fiber data standard. How many people have heard of that before? OFDS. So only a few of you. You've obviously been to other conferences maybe. So my talk today is not as technical. I was hoping to do a demo, but it's actually a little bit harder to get you all up to speed on GIS and how to use different tooling for that. So instead, it's going to be a story. So I did want to, when I submitted this talk, make a story about what happened about 3 years ago. I think most of you that are local know about this story. But NZNOG, way back in 2023, there was someone that did a talk about the impact to their networks. So Simon, thank you for that. It makes it a little bit easier for me, and I'm hoping a few of you have been there, but we've got a lot that are new to NZNOG this year. So there's a link there to NZNOG 2023, talking about the impact. And what actually happened based on the post-incident report was that there was a certain bridge that wiped out your fiber for a lot of your networks, which then wiped out a region from communication, the internet, mobile cell towers, and so on. And then last year, if you were here, thank you to John for giving a talk about using different sources of information that are in GIS to then come up with resilience. And it looks like my YouTube link has not come through properly. Looks like it's been deleted. So I'll have to update that. But John's talk was based on a report that he did for Hawke's Bay. And that was the improving the telecommunications resilience. And as one of his recommendations was to set up a diverse fibre optic backbone path. And that's essentially what this talk's trying to give information about, is this open fibre data standard. And it's encouraging different networks, different countries to document their fibre backbone and being able to share that, whether that's publicly. That would be the ideal way, because I'm from the Internet Society. We think that the internet should be trusted, secure and open for everyone. Or whether you are sharing it with the appropriate agencies that make decisions to improve the resiliency for your country. It's up to you how you do that. So mapping fibre networks. If we think about undersea cables, there are lots of resources out there already that are publicly available that you can get access to, and you can find out information there. The terrestrial maps are a different story. There are sometimes open source ones that are publicly available, but they're very old. They're downloaded in different formats, so it makes it difficult to be able to share between organisations or between agencies, and then being able to do something meaningful with that information. And there's no norms on how that information is published or shared. This makes it difficult to track the terrestrial fibre, because you've got to go collect it from various data sources. Those data sources, as I said, can be dated. And it makes it harder for researchers to then make assumptions or recommendations or do research for future development for those. Most of us use some mechanism to document our own networks, where our fibre is going, and we have something like KMLs as a simple solution. If you use KMLs, do you make them available? Here's a project from a Canadian ISP, and that's called the Connected Coast. And you can download different states of that network. So you've got the cable location map. In Australia, we have dial before you dig, so you ring them up before hopefully you start digging, and they have an idea of where these cables are. But that's not publicly available. So it makes it a little bit difficult from there. How many of you use KML files as it is at the moment? Yeah? With the KML files, are you able to add extra metadata to your fibre paths? So you have your destination points and so on. You can add some metadata to it, but it's not a standardised format. One organisation does it one way, another organisation does it a different way. And so if you want to share your maps, you then have to manually or somehow update those properties or that metadata. So that's the challenge when we're thinking about our terrestrial fibre maps. The accuracy, for starters. When was the last time they were updated? Especially the publicly available data sources that are out there. Some of them are 5 years old. Various organisations have commissioned things like the World Bank studies. The completeness. Not all of those are up to date and have all of the latest project updates put into those maps. Sometimes there's limited information. That information that is needed to make decisions about policy. Example would be the bridge that got wiped out if that was known that everyone was running fibre across that bridge, they might have been able to make a decision at a higher level to say maybe we need to put in a separate path. The publication format, it comes back to your network and what package you are using to document your cable infrastructure, how you are then going to publish that format. And then once you have it published, are you going to make it public? And then who are you going to give it to? Then finally, the validation of that. How are you going to make sure that it's being validated and it's kept current? And so that's a challenge. And that's where the Open Fibre Data Standard discussion started, is how can we make this a simple way to make it easier for different organisations to share information about their terrestrial fibre maps, and then keeping it up to date. I did a quick search about some of the typical resources for what you could use in New Zealand. So in Christchurch, you've got this spatial open data portal, you've got Earth Sciences and other organisations that actually provide mapping for you. Here's an example from Chorus about their data centre locations, but their backbone potential. It's in PDF format. For me to get meaningful information from that, I now need to convert that into a format that is going to be usable in a GIS system. Obviously, you can, if you're purchasing dark fibre from networks, you can approach those people that are giving you that fibre and say, can I get a copy of where my dark fibre is laid to? And they will give you a map. That makes it easier. But then you don't know exactly what other dark fibre has been laid and where it's going. Just doing a quick search using your friendly neighbourhood search engine, and you can see that there's lots of different options available there. I even went to a forum and they're saying, there's this map here, there's this map here, maybe download it here. A lot of them were in PDF format. In 2015, if you can imagine this terrestrial map, or even this map here, as a living document. So it has some undersea cable in there, it's got different fibre terrestrial paths that are actually going through different countries. But if this was a living document for the Asia Pacific Information Superhighway, it would make it so much easier for you to figure out how well you are connected to the rest of the world. And then what could be the breakpoints? What do you need to invest in if you are different organisations? Now, when I talk about the Open Fibre Data Standard, it's trying to come up with a common language. How you are going to describe your different terrestrial fibre components. It's not about whether the network maps are going to be shared publicly or not. So you have the open data, and then you've got the open standard. So being able to have a standard to describe your terrestrial fibre network and make it easier for each organisation to then share information if they want to. To give you a quick overview of some of the concepts behind it is that we have the network, you have nodes, and then the spans between the nodes. You can then add metadata to include about that terrestrial fibre network. Things like contracts, your network providers, and phases, or even who is paying for this type of network. Okay? You're not limited just by this. You can build that out, and it's going to be a more complex way of doing it, but essentially what we tried to do is build a relational database in our GIS system that you can now use to add in all this extra metadata about your terrestrial fibre networks. So the components for the Open Fibre Data Standard is a schema or a code list. So being able to define the structure and the format of that data, the meaning of each field, the rules that must be followed to publish the OFDS data. And as part of the project, there is some documentation. So it's been going for a few years now, and we've created some open source resources for you. Open source, yeah, that's a tongue twister. But open source resources for you that you can use to go and read about how to do this, as well as some tools that are available for you. So if you have a KML file, there is a Python script that you can run to convert it into OFDS format. Once you've got it into OFDS format, basically it creates 3 files, a JSON file and 2 GeoJSON files. You are then able to then put it through this open source tool on the left called Cove, and that's convert, validate, and explore. And that will go through the process to make sure that KML file that you've converted has actually comply with the OFDS concepts, the schema and the code list. The categories of data that you can store in OFDS is your location data, what you're doing already in your KML files. You can add technical data like capacity, your fibre standards, your power availability. And then you can add other administrative data to that. Who owns the infrastructure? The status of the infrastructure? The availability of your dark fibre and things like that. The Open Fibre Data Standard, it's not aimed at the undersea cables and it's not aimed at the last mile at this point. It's that national and middle mile section, the cables that you provide as your backbone or backhaul or something. I know there's going to be a few questions after this. There will be time for questions. I'll see how we go. But the benefits of the Open Fibre Data Standard need to think about it by the organisation. So the governments, they can do more strategic investment in their fibre because they know where everything is. In theory, most governments should have an idea of that already, but you just don't know. So this isn't just for New Zealand, this is for other countries as well. They have a better understanding of their national and regional network resiliency. And John talked about that last year at NZNOG when he said, we've got the quake maps and the flood maps and you've got your terrestrial maps and being able to make decisions based on that. Having improved coordination across the sectors and then hopefully reducing the interruption to your physical infrastructure. From the network operator's point of view, if you're wanting to have better investment, you know where certain fibres are, you might need to go to a certain carrier to then get that coverage. And hopefully build some trust between you, which NZNOG's always a good start, one of the better NOGs. From the researchers, is there any researchers here? Wrong audience. Obviously, Europe, there's a lot of researchers, but but researchers are always interested in finding out where your terrestrial fibre is because they can do different sort of future proposals and so on like that. In Rio de Janeiro, we can see this example here. So understand the true extent of the national fibre infrastructure. They now know, I don't know if I can point this up. You can see here that they've got lots of resilience here and different paths. So if something happens, they can hopefully have some resiliency. With the Open Fibre Data Standard, we're in the process of working with different organisations to basically create a multi-stakeholder governance structure and do the research into this. So there was a workshop in Geneva, and there are ongoing OFDS workshops that are going to be happening. And here are some of the members that are working on this standard. The idea is to basically draw on past experiences and build a more resilient network for your terrestrial fibres and develop a community that is strong and diverse around this standard. As I said, the Internet Society, we're trying to make a global, secure and safe internet, as well as one that is resilient. And as part of that, we have this IXP, we have a tool called Pulse, and that tracks resiliency, network outages, and so on. If you are interested in learning more about this, there are lots of resources available for you. So there is training available on the ITU Academy for if you're new to mapping and GIS. There's also a whole heap of data sets that you can go and grab. They're in the JSON and the GeoJSON format. There is a sample demo map that you can go have a look at. And there's the various tools that you can go and use as well. As I said, I was going to do a demo and also trying to play movies inside PowerPoint live on stage. I don't know if the demo gods will allow me to do that. So I've given you a link here where we took the example of the Chorus map, put it into the actual Google Earth, added the points and the routes, then we go and convert that, or we don't actually convert it, I don't show you how to do that, but then we go and show you how to set it up in QGIS, the open source tool to go play around with the Open Fibre Data Standard. It's about a 24-minute talk. From the Internet Society's point of view, we've outsourced the maintenance and development of those tools to a professional organisation. We're just doing secretarial function, and resources are freely available for you to do, get access to. And we're trying to do more fundraising and ongoing development for the adoption of the OFDS. If you're interested in learning more, send me an email. If you're interested in running a workshop, send me an email. Or if you're interested in helping to develop the standard, send me an email. Or I can put you in contact with someone at the Internet Society that is actually in charge of this. And that's it. I think I'm ahead of schedule. Yes, I left time for questions. I'll give you the mic.
Nico.
Really awesome what you're doing. I think it's well needed. The biggest problem that I see in New Zealand is, and I completely understand why providers are like this, is security concerns around releasing where their assets are, and there's very good reasons for that. What I think we need is a tool that lets me, like, I don't actually really care where fibre runs physically. What I care about is I want to have 3 paths that don't cross each other. So one of the things that I think would be beneficial is to be able to say, can you please tell me which 3 providers have 3 paths that are diverse to a organisation that can keep all the data secret, but just give me the results of that separate. Have you guys done any research or put any thought into, and I don't know whether that'd be a government function or someone like NZNOG's function or whatever, but has there been any thought into, I mean, I'm assuming this is a worldwide problem where people are concerned about the security. Has there been any effort into some sort of tool like that where you can keep the data secret but deliver the customers the outcome?
Not that I know of, but I could defer that to one of my colleagues. The concept could be easily done, and there's been lots of discussion about that. The reason why I don't know about it is because we're pushing it to be open data, as in people are able to access that. And it would be an easy tool to create, I think, but who would look after it would be the problem. Because, the reason why, you mentioned about security, but there is an option for you to publish your data so that way you can say whether it's going to cross that path or not without having to tell them the exact path. So there is research already. There's a couple of white papers here. This one here is looking at obfuscating your actual physical infrastructure maps. So you can have people ask a question to that organisation, say, do you cross this route or path? But no, there hasn't been that I know of.
Along the lines of,
Yep.
Someone else like to go first?
No, go
All
John.
good. Along the lines of what Jonathan Saylor was suggesting, most of the maps that are out there will show multiple operators in the same, they're actually in the same sheaf, but they'll show them as parallel cables on the maps.
Yes.
And so most of the data you see on the ITU maps is garbage, on the SCAP maps is garbage, and of course submarine cable map will publish any planned cable.
Yes.
And so when researchers go and look at that, they say, oh, there's a cable here. So the OFDS actually tells you who owns the sheath,
Yes.
which is great. And so you know where the pairs are and where the pairs are going. So it will be a big step forward to start to have data in this format. So
Yeah,
I'm keen.
The thing that I really like about it is getting that extra metadata against the fibre and knowing who owns it, who's funding it, or there was someone down there that had their hand up. Whose cable, sorry? Sorry, I didn't quite hear, but for the people that are online...
Going through Molesworth, there's one fibre cable, and that's a Transpower cable laid by FX back in the day, but on your maps there you're showing it being a chorus route, and they also showed chorus going up the coast on the east side, which is correct. So there's actually, you need to show who the actual fibre sheath owner is, like John says, because these operators have got fibres. There's only really 3 going up through from South Island.
Yep.
But if you looked at some maps, it would show multiple fibres, and there's actually only a couple or 3.
You want to run a workshop? We can bring all the resources in, teach you how to do it. Let's do the documentation properly.
We only look at it from our point of view, from being an operator here in the South Island. So when we have to choose who we upstream with, we have to go, well, where's your upstream path?
Yeah.
Are we buying it on the same path that another operator is actually already operating on? So if we get a fibre cut, say on that Molesworth one, which is one of our primary cables that we use, where is the alternative provider that we'd be buying through going to be operating?
Yeah.
Because at the moment, they all say, oh, this is our routes. Well, it's more of a route direction rather than an actual physical fibre cable.
Yeah.
Because when we had the Kaikoura earthquake, the chorus fibre was damaged going up the east coast. So, of course, one of the most reliable ones is going up through Molesworth. So it's a fibre in a duct rather than a direct buried fibre. So big difference. You could even put that into your map.
Definitely.
Because then you know a fibre in a duct is more reliable than a direct buried fibre that can be pulled or tucked on a bridge or whatever sort of thing.
Yeah, that's true. But if there's an appetite for doing a workshop, let us know. NZNOG, we could potentially do one next year, but that's a long way off. I prefer to do it sooner than that, but anyway.
So yeah, just an observation on available data on different sorts of networks. From going down some rabbit holes, I've found that the electricity distribution networks in New Zealand, some of those publish through various tools maps of their networks. So for example, in Auckland, you can get very detailed maps of their distribution and some transmission networks, and there's also quite a lot of metadata in there, and those. It's public and not particularly obfuscated.
Yeah.
And they would, I presume, have similar concerns, although a buried electricity cable feeder can defend itself a bit better than fibre.
Yeah.
Yeah.
That's right. So there are electrical grid maps out there that you can go and look at, and other utilities, look at the roads and other infrastructure. It's there. Yes, that's true. The other thing you can do with the OFDS, we're mainly focused on the terrestrial fibre, you can add in all these other utilities into the standard as well. So whatever you want to map could go into that. Any other questions?
No, looks like you're all done.
I thought there might have been harder questions, and 2 minutes to spare. Oh, thank you, Ev.
Cool, thank you, Warren.
I do want to get a photo from up here down at the audience. Come on, you can come up and take it, because you also want it from your LinkedIn, don't you?
Cool. So just while the photos happen, we're just getting to the end of the first session. For anyone suffering this morning, we do have AWS energy drinks, and we do have Searchlight coffee available. So recover. Everyone stay still. Cheers, Warren. Okay, thank you, everyone. Reconvening at 11 a.m. Thank you. Cheers.
That works. Kia ora, everyone. Welcome to session 2 of today. It is my great pleasure to introduce my colleague Jody Anderson, who will speak to you about a very different side of the internet, which is not about cables, not about TIC, but about internet governance and what you as the network providers can do to influence how the internet is governed. That's the 3rd year in a row that Jody gives a variation of this talk. We hope that 3rd time is a charm. So if you find it interesting, please find Jody during the break, and she will tell you all the secrets about internet governance.
Square clicker is the best clicker. Kia ora koutou. Thanks, Maria. My name's Jody Anderson. I'm the Internet Governance Lead at Internet New Zealand Ipurangi Aotearoa. Oops. Can't work it. Internet New Zealand is a not-for-profit organisation that operates the .nz domain space for Aotearoa New Zealand. We're a sponsor of NZNOG, and we've got a little booth out there, so come and visit whoever's on the booth at lunchtime. Operating the .nz domain space is our core work, but as a member of the internet, the global internet technical community, those who run the core of the internet, the internet technical community that keeps the internet working for the benefit of everyone. We also work to defend and improve and actively participate in multi-stakeholder internet governance as a foundation of the open, global, secure and interoperable internet. That's our relatively new constitution, and you can see that in there these actions and objectives are captured. And that's what I'm here to talk to you about today. What multi-stakeholder internet governance is, why it's foundational to a global interoperable internet, why and how and where it's at risk, and what we're doing and can do about that. Thank you for having me back for a third year in a row to talk about this. Some of you will have heard me talk about it before, so I'll try not to linger too much on the things you've heard before, but I do have some new points for those who have heard it before, and I haven't forgotten that I promised to come back and tell you last year, when I was here last year, about how the WSIS plus 20 process turned out, and all that will be covered. I'm starting here with what actually matters, with what the real goal is, because sometimes when we talk about multi-stakeholder internet governance, it can seem like that's the goal. But multi-stakeholder internet governance only matters because it's a means to protect the global, open, interoperable internet. Many people, in fact, probably most people, think that the internet is the thing that they interact with every day. The social media, the websites, the AI, the applications and innovations that sit on top of the internet. And they don't understand that the real internet sits underneath that. The real internet is a network of independent networks. I don't need to tell you all that. And these networks interoperate so that they act and present as a single global internet. The internet has one simple function, which is moving packets from point A to point B. And the internet can act as the single global system essentially because we have common protocols to ensure interoperability across all of these networks, and we have unique identifiers, domain names, which is our business, that are allocated and registered to enable routing to the right place, IP addresses, all of that sort of thing. And the fact that the applications that sit on top perceive it as a single global network and use it as such is why the internet has become a global platform for innovation, and that has delivered extraordinary benefits to businesses and economies, people and societies across the world. Internet governance answers the question, who is in charge of this internet, this network of networks? Who ensures that it keeps working day in and day out? Who makes sure that the common protocols are developed, the IP numbers are allocated, the domain name policy is made, and the route is maintained? Who governs the core of the internet? And the answer is no one and everyone. There is no central developer, owner, or operator of the internet. The technical coordination of the internet is governed by a decentralised but collaborative patchwork of various bodies. And you will have heard me say that sentence last year and the year before. These bodies were not put in place by a master plan. Instead, they sprung out of the internet as the internet developed, as the core internet technologies and systems grew out of small-scale research experiments and scaled up to become the global network of networks that we know as the internet today. These institutions sprang up to govern these technologies and systems. Here are some examples of these bodies that govern the internet. You've got ICANN, the Internet Corporation for Assigned Names and Numbers, and they manage the unique identifiers such as domain names and IP addresses and root zone functions. The Internet Engineering Task Force, the IETF, that's the standards body that develops open standards for the core functions of the internet. You've got the regional internet registries, the RIRs, like APNIC for Asia Pacific, who works out of Australia. And they allocate IP numbers regionally. And you've got a number of other organisations as well. Those are just some examples. And these bodies operate in a special way that has come to be known as multi-stakeholder internet governance, or the multi-stakeholder approach to internet governance, sometimes the multi-stakeholder model of internet governance. Model's not a great way to talk about it because they all have a very different way of doing it. But what that means in general terms is that they are private, they're independent of government. These are not government institutions or run out of government to government institutions like the United Nations. They have more of a shared global ownership. And governments are just one of the group of stakeholders that goes to these institutions and helps do the work on equal footing, which is a phrase that's used a lot in internet governance, with other stakeholders. So governments aren't special. They don't control the process. They don't control the space. That's the first important characteristic of multi-stakeholder internet governance. They're also open to broad participation by interested parties. Any stakeholder that is interested in or impacted by their decisions can participate. And those bodies, examples that I had up on the slide before, they all have slightly different ways of allowing different stakeholder groups to participate. The IETF, for example, you come as an individual. Even though your work might be paying for you to go, you engage in that space as an individual. Whereas ICANN has different communities. So .NZ would go and be part of the country code top-level domain community, and there's also a generic top-level domain community, and there's a government advisory committee, and there's a civil society group called At Large. So you sort of go and you engage in your communities, and those are the communities that run the work or action the work of ICANN. But any of you could also go. Like, these places, they are open to everybody. And their decision and policy-making processes tend to be bottom-up and consensus-driven rather than top-down, like it would be if the governments ran them, probably. And it's the community that drives the work, and they work to meet the needs of everyone to keep the internet open and global and interoperable. Multi-stakeholder internet governance is why the internet remains unified and global and resilient. This form of governance is uniquely suited to ensuring that the internet as a public good is managed in a way to preserve that character. Multi-stakeholder internet governance is effective because the internet is just too complex for just one stakeholder to run. Multi-stakeholder internet governance supports the solving of complex problems because it draws on the wide range of expertise and diversity of perspectives from multiple stakeholders. I mentioned before that there's lots of stakeholder groups in multi-stakeholder internet governance. The ones that tend to be talked about are governments, the technical community, which is all of us who run the internet, civil society, the private sector, and academia. So each group brings its own expertise and interests to the decision-making and the governance of the internet. And this means that complex problems can be solved. Multi-stakeholder internet governance is accountable. This model, by design, prevents any single entity or any single stakeholder, particularly governments or states, exerting undue control or influence over the internet's architecture. It guards against the specific interests of any one stakeholder that might undermine its critical properties, because the governance is shared between stakeholders with different interests and objectives. And so they all keep an eye on each other and they all balance each other out. And it reflects the vision that the internet is a global public good, a commons to be coordinated rather than a territory to be carved up and administered by governments. So multi-stakeholder internet governance essentially works to ensure that the actors in this space, and especially governments, don't take control and act in self-interest and in ways that would impact the internet's technical layer and impair its openness, interoperability, and global nature. So multi-stakeholder internet governance is the optimal way to run a globally distributed network. And it's the way the internet has been governed, essentially, since its beginnings. But that doesn't mean it will always be governed this way and that it's set in stone. It's actually quite vulnerable. The system is actually fragile because its legitimacy doesn't derive from laws or a treaty or from central authority. It's a system whose legitimacy derives from more nebulous things like consensus and engagement and performance. And all these things interrelate. In terms of performance, it's been said that the best safeguard is to do a good job. So if, for example, ICANN demonstrates that it's the right neutral steward of critical internet resources, then there's no need for alternatives. Good performance in this way essentially bestows some legitimacy. Engagement is key because these institutions run on volunteers. Volunteers is a funny word. It doesn't mean that people don't get paid, because often the people that go are being paid by their employers. But it's people from governments and technical community and academia and civil society, private sector, turning up to actually do the work. It's not the institution itself that does the work. The institution tends to, they're all different, but the institution tends to have like a staff or a secretariat that sets up and runs the meetings, and then the community comes and actually does the work of the institution. So engagement in these institutions feeds into performance because they can't do a good job without the multi-stakeholder internet governance community engaging, but it also bestows legitimacy because the community turning up identifies that this is where the work is going to be done. And in terms of consensus, multi-stakeholder internet governance is widely accepted as the international norm for internet governance, and this has been legitimised by states in a particular United Nations outcome document called the WSIS a number of times now. But this consensus relies in large part due to the fact that these institutions continue to keep the internet running through consistent engagement. So all these things interrelate to provide legitimacy to the multi-stakeholder internet governance ecosystem. But there's nothing truly structural stopping the governance of the internet being moved into state control. The system works because stakeholders choose to engage, and consensus is maintained because it works. But the whole thing could come crashing down if enough states decided that it wasn't working well enough anymore. And it may be currently widely accepted as the international norm by most states, but that doesn't mean that this norm is not constantly threatened or that states won't move on their position. In the last 25 plus years of multi-stakeholder governance of the internet has also been 25 plus years of campaigns to remove multi-stakeholder internet governance in favour of nation-state governance of the internet. Certain governments, and this is most often China, Russia, and their friends and their regional alliances, want to control the core of the internet. They are deeply uncomfortable with the management of such important infrastructure being done by organisations where governments are just one stakeholder on equal footing and not in control. They want to embed the governance of the internet's critical resources and infrastructure into an intergovernmental institution like the United Nations, where it can be controlled by states. And there are numerous forums in which these states have attempted to do this, to get rid of to get management of critical internet resources under government control. They've used the WSIS negotiations, which is a summit in the United Nations. They used that in 2005, 2015, and last year, 2020-25, where they've tried to insert language into those outcome documents for this. They've used other multilateral agreements in the UN over time, including the Global Digital Compact in 2024 and the Cybercrime Convention around the same time, trying to insert language in there to do it. They've had numerous attempts over the years, ever since 1998 in the International Telecommunications Union processes, and also at the Internet Engineering Task Force. So they use all the forums at their disposal to try and embed the governance of the internet's critical resources and technical infrastructure into a place where governments can control it. And their choice of place is the ITU. That's where they want, that's the place that they want usually to have control, because they can gain greater influence in such a structure because it is a government-run structure, and because the ITU's members are nation states which they can influence, and there's no other stakeholders in there. It's not a multi-stakeholder institution. And so having it in there would make it easy to exert direct state control over internet governance processes and critical internet resources. Other governments have continued to recognise throughout this time that the multi-stakeholder model is the better way to run the internet, and until now there have been enough of those other states and they've been organised well enough to push back. But this balance has started to tip, and I've been here the last 2 years to tell you that it's slipping, and it's continuing to do so. Because not only have China and Russia and others been working hard to convince other countries that it would be a good thing for states to have more control over the internet, and that narrative is something that states are starting to listen to more and more, and they're starting to agree with. But also the recent behaviour of the United States has been playing into these arguments. Why is it a problem if the core of the internet is not governed in a multi-stakeholder way, but instead just by states? This is a question I get asked a lot, because these states make what look like really good arguments, which is states need to control the internet's too important a resource, our economies and our societies depend on it, the governments should have control. The problem is that states naturally make politically motivated decisions. They act in self-interest, and they can't always be relied on to make decisions for the global public good if that's in conflict with the government of the day's own short-term interests. The danger is that states, unconstrained by the input of and accountability to the other stakeholders, would start to take actions like removing political adversaries from the root zone, or rather the country code top-level domain, for example, redesigning and controlling the infrastructure to allow for surveillance and shutdown of the internet, taking over the resource allocation to enable control and surveillance. And these are all things that states have proposed in those forums that I talked about that didn't get anywhere, but that's the type of thing they want to do. And these decisions could eventually impact the core of the internet and impact interoperability, and lead to fragmentation of the internet, where the internet eventually splits into a bunch of isolated networks. And this could be deliberately or by mistake, because without the technical community involved in the multi-stakeholder internet governance and making the decisions, states could just as easily break the internet by mistake as do it deliberately. A fragmented internet would undermine all the benefits of a global unified digital ecosystem. The internet's power comes from interoperability and universality, and as interoperability decreases, friction increases, and services may be blocked or slowed for users. Users may need to use different tools depending on where they are, because infrastructure and data will become localized. Fragmentation can also create security, surveillance, and trust issues, because if traffic has to go through national gateways, those are opportunities for surveillance or censorship or abuse. And divergent laws about encryption or liability may reduce trust in cross-border services or require large overheads. Fragmentation could also create economic cost and innovation drag, because fragmentation means duplicate infrastructure, which is inefficient. Cross-border collaboration, which has been a source of innovation, could become more constrained. And it could also cause unequal access and power imbalance over the world, because some countries may be less able to negotiate or enforce their interests, and they could be locked out of parts of the internet or forced to use inferior services. And all in all, none of this would be particularly good news for a small trading nation at the bottom of the world. That's us. So this is why we work to defend multi-stakeholder internet governance, because it's foundational to the open, global, interoperable, secure internet that sustains our economy and our way of life. And working against this threat is essentially a global army of stakeholders: government, civil society, technical community, academics, and private organisations. And these stakeholders engage in multi-stakeholder internet governance spaces, not only to make it work, do the work, ensure the legitimacy of these spaces and support that consensus that makes it exist, but we also look to defend it in the places that it's being threatened. Last year's battleground was the WSIS plus 20 process, which I told you about last year and the year before at this talk. And I told you then how that was shaping up. WSIS plus 20 is WSIS is the acronym for the World Summit on the Information Society, which was a summit held at the United Nations in sort of 2003, 2005, where a lot of countries got together. They wanted to talk about all of this new information technology and how they were going to work together to make sure that everybody rode the wave of that. And while they were there, they realised that what they should probably talk about as well is internet governance. And while they were talking about the other stuff, they also agreed in 2005 that internet governance should be multi-stakeholder, like it was already, but they sort of put it in their outcome document, which gave it that sort of international norm status. And so WSIS keeps getting renewed. The outcome document only lasts for so long, so it has to keep getting renewed every so often. And the last opportunity for renewal was last year at WSIS plus 20, which essentially just means the 20-year review of WSIS. And this was a focus for many in the internet governance global community because, again, it provided that opportunity for states who wanted to undermine multi-stakeholder internet governance and bring that governance into intergovernmental spaces. It provided an opportunity for them to reopen that debate and get the words into that agreement that would allow it to start to achieve that aim. And as expected, during that process, certain states and blocks did propose provisions for the WSIS plus 20 outcome document that would have shifted power away from the multi-stakeholder model towards an intergovernmental structure. Last year, I also told you about the Technical Community Coalition for Multi-Stakeholderism, or TCCM. Internet New Zealand worked with other ccTLDs.au, .ca and .uk to establish an informal coalition of members of the global internet technical community. It was about 2.5 years ago now, because we were concerned by the limited coordination and activation of the technical community to respond to WSIS plus 20. So we set this coalition up to support the capacity of our members in the coalition to engage in the WSIS plus 20 process, because these UN processes, they're pretty opaque, they're pretty hard to follow. And we also wanted to have a clear voice in contributing to these dialogues and to speak up for multi-stakeholderism and for the technical community's place in that model. And so throughout last year, TCCM worked with the objective of seeing specific outcomes in the WSIS plus 20 process, which included recognition of multi-stakeholder internet governance. How am I doing for time? Are you standing there? I think 3 minutes, okay. So I just wanted to quickly talk about the outcome. The good news is that we got the outcome we wanted. The good news is also that it was adopted by consensus of all member states rather than going to a vote, which gave the outcome greater legitimacy. But behind the scenes, the news wasn't as great. And I talked to a couple of people who were inside the negotiations, and things really came down to the wire. The outcomes on internet governance were in real danger right up to the end, and it was a hair's breadth away from losing consensus and going to a vote, which would have significantly undermined the outcome. Because of limited time, I won't go into some of the things that I was told saved the day in too much detail, but what really, really got things over the line at the end was the fact that there were other stakeholders on the delegations of those governments, and those stakeholders worked behind the scenes to bring the countries that were dragging their feet over the line. So victory was snatched from the jaws of defeat, essentially, because multi-stakeholder involvement leads to better outcomes. I might skip over a couple of these slides because all I really want to say here is that battle was won, but the battle continues, because just because we've defeated them in one forum does not mean that they're not going to be at the next forum. And the next forum is this year the ITU Plenipotentiary, which is a 4-year negotiation in the ITU, and this is historically a key forum through which governments try and get internet governance pulled into government control. So the TCCM will be engaging here. The story leaves us in a place, I think, where it's hard to disagree that we're potentially moving towards government control of the internet and some sort of internet fragmentation off the back of that eventually. The internet exists in the world, and the world at the moment is moving towards sovereignty and isolationism and nation states for themselves, and this geopolitical reality is going to affect how the internet is governed and is going to impact the open global interoperable internet eventually. But I don't think that means we give up. I think we need to choose optimism and action, because staying engaged allows us to control, or at least guide, or at least have some say in what happens next. So on that basis, what can we all do? Here's what Internet New Zealand is doing, and given that I have no time left, I'm actually going to go to the last slide, which is what you can do. Somebody asked me this last year, and I've had a year to think about it. You can support Internet New Zealand's work in this space. You could become a member and support Internet New Zealand's work in this space. You can engage with me. I'm always looking for technical people to help explain technical things as I do my policy work. You could join TCCM if you're eligible. We have certain people who are eligible to join, so check out the website. It'll be on my next slide, and see if you're eligible. You can get involved in multi-stakeholder internet governance yourself. As I said, ICANN, IETF, the RIRs, you can sit at your desk in New Zealand and engage in these spaces. You can talk to government. This is actually my big ask. If you engage with the New Zealand government in your work, consider bringing up internet governance and ask them to engage, because the more of us that bring it up, the more they might take notice. And reach out to me if you want any talking points. And the final one is, talk to your friends in whānau and strangers on the bus and on the internet about internet governance. Be the person who talks about internet governance at the dinner party. I am. The general population takes the global interoperable internet and all the benefits it provides for granted, because they don't know what the internet is, how it's governed, and what the risks are. And a more informed populace could demand a government that thinks about the internet, engages in internet governance, and works to resist fragmentation. And I will be around for the next hour and then throughout lunch. Please come and ask me any questions, assuming you're not going to give me any extra time to do that. 1 minute, we can have one question or something. But otherwise, come and talk to me. Thank you.
So I've just got one question. In this current geopolitical environment, is it easier, or do you think it's harder for the states to work together to take control of this sort of stuff for the internet freedom, or is it harder for them because it shows up their venal attitudes?
I think states. There's a few parts to that. The states that are working against multi-stakeholder internet governance are still working pretty well together. The states who have historically, they're called the like-mindeds, have historically banded together to push back were always led by the United States. The United States was like the leader of this group. They had a huge team, they had depth of knowledge, and I think that because the way the United States is acting at the moment, that's going to be a real blow to that group of states in terms of pushing back. So that's one thing. And the other thing is, which I think I referred to in my talk, which is that because of the sort of the because of the way the United States is acting, but also because of everything else, a lot of states are starting to feel very sort of they're talking about digital sovereignty, and they're leaning into isolationism. And so when Russia and China talk about things like you should have control over the internet that's in your country, it falls on more fertile ground. So I think those are the two ways that it's affecting that. Did that answer your question? Thank you very much.
Thank you, Judy. And I am very pleased to invite one of our favorite speakers of all times, who usually has highly rated presentations in NZNOG. Please welcome Simon Allard, who will share progress on the project between 2 Degrees and AST Space Mobile.
Cool. So I don't think I actually need to introduce myself. I think Warren did a pretty good job of introducing me before. But for those who don't know me, my name's Simon Allard. I work for 2 Degrees. But before I start, I've got a message for Sean, just to say happy birthday from Brent from Chorus. Something about revenge is sweet, something like that. But yeah, so for those who don't know, there's a bit of a space race going on, and I'm not talking about the billionaires club, building massive rockets, trying to build bigger and better rockets between the two. I'm talking about a space race between the three mobile companies in New Zealand. We all know that 1NZ has been using SpaceX for a very long time, be coming on 2 years. We've got Spark, who've just recently announced they're coming soon, mobile operating on space. I don't think you have to read too much into that to figure out who they're going to use. And then we've got ourselves, 2 Degrees. So we've partnered with AST, but AST isn't the first space venture we've had. We used to have a partnership with a company called Link, and Link was a very similar model to what SpaceX is, and we managed to do our first phone call across that Link constellation in 2003 from the middle of the North Island. But unfortunately, Link wasn't to be. They didn't seem to get their funding and haven't managed to get any more satellites up in the sky. So we've now pivoted and we've now gone with AST. So the race is on. So LEO has been very proven in the broadband space. We've had SpaceX up there in a long time in the LEO distance, which is about 300 to 700 kilometres above Earth. They've been there for a very long time. They've been doing some excellent stuff in the broadband space, and they've started to dabble. I say dabble. They've started to do the mobile space to mobile offering in with quite a few partners. T-Mobile has obviously been one of the first, and 1NZ was the other one. We're very proud to be partnering with AST. AST is a very different model from SpaceX, and once we take you through the slides, you'll start to see why that we've partnered with AST versus just doing something else. And we're spending a lot of money on this. This is not something that's a trivial investment for us. It's something that we see as a bit of a game changer to mobile in New Zealand. And yeah, we'll cover a bit more detail on this, but yeah, we're hopefully going to launch our product middle of this year, so we're not far away. So let's start with AST. Who are AST, right? So they're a US listed stock company. They're extremely well funded, which is great because what they're trying to achieve is pretty impressive. Most of their investment backing is coming from AT&T, Verizon, Vodafone, Google, and quite a few others. And they're effectively building what is the first only space-based cellular broadband network. And I say that because SpaceX, the original one, was broadband only. They've then dabbled in mobile as well, but it's the same same satellite doing both things. Well, AST is predominantly focused on doing mobile only, which is pretty cool. So they've done some demonstrations. They've got a bunch of satellites up in the sky at the moment. So they've managed to do some proof of concepts with AT&T, with 4G and 5G video calling, all that sort of cool stuff. But they've still got a lot of work to do. And they've got over 50 mobile operators now signed up with them. And every time I go onto the LinkedIn page, they seem to be signing up more. So they've become a very popular space constellation. Their largest comm satellite, and we'll go into a bit more detail on that, and you can see a photo of it behind me. That's one of their largest satellites that's actually up in space at the moment, with 223 square meters in size, which is huge. When you compare that to a SpaceX one, well, you'll see what the difference is there. And they're not a satellite provider, sorry, not a rocket provider, so they're having to then use multiple launch partners, and we've got a bit of stuff to show on that as well. So let's look at what the satellites are, right? So you've got a human, 6 foot, me-ish. You've got a micron, which we'll cover off in a bit of detail. You've got a card, which is 100 square feet. And then you've got what they call the Block 1 satellites, which is 700 square feet. And they've got 5 of those up in the sky at the moment. They're effectively what they consider their proof of concept satellites, where they've actually been able to go and actually prove this theory behind it all, adapt it, come up with better ways of doing things, but just basically proving that theory that this is going to work. And then there's a picture of their Block 2 satellite, which they've got one of those up in the air, which we'll talk about soon, but you can see there's quite a large difference between the Block 1 and the Block 2 satellite. Sorry about the freedom numbers. I took those out of the investment pack. But yeah, as you can see, they're pretty large. And each one of those microns is effectively an antenna on top of it. So you can see quite a few microns sitting on one of those Block 2 satellites. And I think, what does it say? Yeah, 650 microns, which you'll get a picture of why that's important coming up. So a bit more about AST Space Mobile. So they actually build their own satellites. They've got a 500,000 square feet of manufacturing facilities, and they've got 1,800 employees, which is, they're not a small space company anymore. They're not, a fly-by-night. They've invested a lot of money in this. Their Bluebird 7 one is in the process of being launched. It is identical to their Bluebird 6, which they've just launched. And it's actually in the process now of being encapsulated and sitting on a Blue Origin rocket waiting to go up. And hopefully that's going to go up soon. They're a little bit delayed on that one, but we'll come through. And then they've got Bluebird 8 and Bluebird 29 already in the various process of production through their assembly line. So their expectation is that we're going to get to sort of 45 to 60 satellites by the end of the year. It is very much going to depend on their launch partners. And we'll go into a bit of detail how that all looks. But with 45 to 60 satellites, you're going to get some pretty good coverage. Not 100%, but you'll get some good coverage across New Zealand. So this was their first Bluebird 6 launch. So they used an Indian Space Agency rocket, which was really fascinating to watch from behind the scenes. Since their satellite was manufactured in the US, they then had to work out how to get this thing from the US all the way to India. I don't think they're going to do this again because it was a massive nightmare for them. Well, not a nightmare, but it was pretty hard going to get a big satellite unit into a Antonov and then over to India to get onto the launch pad. So as you can see, this is probably the only machine in the whole entire world left, thanks Russia, that can actually get this type of cargo all the way over to India. Their next rockets, I think they're going to start using, well, they are definitely going to start using SpaceX and Blue Origin to get all the rest up into space. This one, I think, was a bit of a nightmare for them because it just, the logistics of getting it over there and the cost to get it over to India was quite large. But these guys did manage to get their first Block 2 satellite into space, which is really exciting, pretty complicated thing as well. So unfortunately, I don't have a laser pointer with me, but you'll see on the left-hand side, up where it says stowed. Top right, cool. There you go, green too. So you see that's the picture of it stowed. So that's the block, one of the first Block 2 satellites being nice and stowed. You can see the scale based on the little man standing next to it, how big the actual satellite is itself. So that sat on top of the Indian rocket and was pretty much the only thing inside the Indian rocket to get up into space. There's a picture of it going up from orbit, and then there's a picture of what it was when it was before it went into the satellite, and then there's one actually taken from space. So they've actually now managed to launch it into space, which is a cheap one on its own, and then they've actually managed to, they have to unfold it. So it's all sort of shrouded up, as you can kind of see where it's stowed. Once they've actually got it into space, they actually have to unfold the whole infrastructure to turn it into basically a giant antenna. Talking to the guys, they were very nervous about that because it was the first one they've ever done. They've really rehearsed it inside, multiple rehearsals inside the ground, but this was the first time they've actually managed to unfoil it in space, which is an achievement in itself. I asked that question, and what happens if you got it snagged? He went, we pretty much have to write it off because there's no way going up there and fixing it. So, yeah. But they managed to do it, and they're starting to do some testing on it now once it sort of goes over place, where we can actually do the testing from. So let's do a little bit of comparison between SpaceX and AST, right? So we kind of talked about it before. So the SpaceX V2 Mini, which is the one they use for the Space to Mobile offering for 1NZ and for the others, it's about 700 kilos, and it's only got a 30 metre wingspan on it once it's fully established out there. Their SpaceX model is to roll out more satellites than less, right? So I think at the moment, based on what AI told me, which we know how accurate that is about 600 of those satellites up in the sky at the moment. AST have a completely different model. Their model is bigger satellites and less satellites. So, effectively it's 10 times the size of a SpaceX Mini. Once they're fully deployed, they're looking at only having about 90-ish, probably more, probably closer to the 100 satellites up in the sky to form a full constellation, whereas the SpaceX constellation is sitting at 600, 700 satellites. So there's a different model there. The SpaceX satellites are obviously a tiny bit lower. I think they're sitting around the 300 kilometres above the sky. AST is sitting around the 600-ish around the sky. So yeah, a completely different model. So why did we partner with AST rather than just going with and following everyone else and just partnering with SpaceX? So the first, probably the point is, any 3GPP capable handset, which can do 4G, will be able to talk to the satellite. That gives a much wider range options for us. Any phone that can talk 4G should be good to go. We've got a full network overlay, and I'll cover that in a bit more detail on why that's important. But it's a completely different model for the way SpaceX works. We're able to do voice and data from day one, and SMS obviously, but you're able to make a phone call using your normal phone, sitting on top of Mount Cook, on a satellite, whereas you can't do that on SpaceX at the moment. My understanding is it's WhatsApp calling only, but yeah, we're able to do a voice call from day one. And we're investing in our own ground stations. Again, different model from SpaceX. SpaceX own and operate their own ground stations. They've got a few scattered around New Zealand and all around the world. We're going to own our own ground station. It is owned by 2 Degrees, and managed in conjunction with AST. So we've actually got a lot more powerful control over the whole end-to-end of the whole journey, the whole customer journey, which is pretty exciting. So into the fun stuff. So how does it work? So at the moment, you've got a normal terrestrial network. So you've got a whole bunch of cell towers. They broadcast out the 4G, 5G signals. And then we got the space mobile side of things. So on the terrestrial side, we all know how that works. You walk between towers. It transfers you, the core network knows where you are, transfers you around. The AST network works pretty similar, actually. You've actually got multiple cell towers on the one satellite. So instead of just, thinking satellite, cell tower, satellite, cell tower, you've actually got we've actually effectively got 300 cell towers in space at the one time. But not only that, we've also then got to work out the satellite, how all the satellite handovers, and we'll cover that in a bit in a second. But the way it effectively works is this particular system is actually plugged into our core network. So we have our own core network, we've got our own HSS, own IMS, etc. They talk to the gateway, which our own ENO-B sit at, and then that gets broadcasted up to the AST satellite station. So we actually got the whole end-to-end control. When you compare that to the SpaceX network is effectively a roaming network where you effectively plug into SpaceX, they talk to the SpaceX core, they talk to their own eNodeBs, which happen to be in the satellites, and away you go. So that they're sort of limited to what SpaceX are willing to offer. In the AST world, we can pretty much offer what we want as long as it conforms to the 3GPP standard, which is a pretty powerful and major difference between the multiple offerings. Wrong one. So, more details on how it works. So, we talked about it before. We've got our own base station. We'll talk about where that is in a moment. That will have 3 eNodeBs located inside our data centre. That data centre is in the middle of the North Island, and we'll talk about why that's important soon. There is a full data centre of stuff that controls all this, all the technology. So we have to know when the satellite's going overhead. We have to then control the satellite tracking solutions as well, because when the satellites are going overhead, they're moving at, let's just say, it only lasts over the top of New Zealand for about 10 minutes. So when that's going across, we effectively have to track the satellite as it goes across. So we're going to have 4 tracking satellite uplinks on the one uplink station that will track the 4, or up to 4 satellites that are transversing across New Zealand. And that in itself is quite a complicated, and we'll cover that in a second. And then we're using we're using a QV band uplink, which is, again, in itself a funny story, which we can cover off soon. And then the downlink is effectively the 900 megahertz band that we normally use for mobile. There are existing 900 megahertz rights. These are the ones that we just retired from our 3G shutdown, which is why we were very keen to get our 3G shutdown done, and we didn't do any delays on that one because we needed our bandwidth and our frequencies to be able to use on the AST network. So, again, we talked about the cell sites. How does it actually work, right? So, if you have a look on the left-hand side, you'll see what our existing 4G coverage is, and then on the right-hand, depending on what side you're looking at, if you're looking at the right side, you'll see effectively a satellite overlay of how this is going to function. So each one of those hexagonals is a 48 kilometre squared cell-ish. And that then uses a bunch of frequencies. We're basically going to allocate from day one 5 megahertz because that's, we're rather spectrum poor in the 9 megahertz space. Additional 5G uses 145 megahertz. So there's a bit of, we're not going to get the same capacity out of the satellite than we will out of a terrestrial satellite, but that's to be expected. And then the way that this works is really extremely clever because it uses beamforming technology inside that satellite. So when that satellite's going across the sky, our cell sites don't actually move. So the cell site hexagonal stays the same, even though the satellite's moving over at vast speeds. And that's quite a powerful feature for us because we can then pick and choose where we want coverage and when we don't want coverage, what frequencies to use and what cell, etc. So there's a lot of ability for us to control some good stuff. But it does come with its complications because effectively you've got 300 cell sites on it. So if you roam in between a cell site in the satellite cell site, you've got to signal that change, and then our core network has to know that you're moving between satellite cells. The other challenge too is effectively you're handing over on the same satellite, but you've also then got to cover the fact that someone could be standing still and that satellite that you were talking to is now moved and you're talking to a new satellite, so then you've got to handle another handover between satellites, which is quite challenging. So what are we going to use it for? And this is where things get really interesting. So disaster recovery and emergency response is probably one of the biggest things that we're quite interested in. We talked about Cyclone Gabrielle, what happened with Cyclone Gabrielle, how it took out most of the MMO's networks. This is potentially a get-out-of-free-jail card for us because it allows us to have service in there. It allows customers to still dial 111 and, text, call their loved ones, but we do have to be a bit careful with it because we've only got 5 megahertz of spectrum per 48 kilometres. So in the case of Hawke's Bay, if you lost the whole of the Napier region, for example, you've got quite a lot of handsets sitting in that small region on a small amount of spectrum. You've then got to worry about how quickly is it going to talk to your eNodeBs, all the latching type of criteria, all that sort of stuff is going to come into play. So we're very curious to see how this is going to unfold. and how we actually respond and deal with that. And we don't really know until we're actually going to, see it in anger and see how it's actually going to work. But in saying that, there's some other real cool use cases, in peacetime use cases, search and rescue. We've got customers that are talking to us about ditching their satellite phones in favour for a normal phone because, some of the telco guys, they don't want to carry around a sat phone in a normal phone. They just want to use a phone. There's cool things in there. And the other part too that we're really keen to look at is the IoT connectivity as well, because now we've got a big coverage of the whole of New Zealand. IoT becomes quite a reality. Since we control the whole end-to-end, we can start looking at things like NB-IoT and other type of technologies that the 3GPP standards allow. So let's talk a bit about the ground station. So we were quite lucky. We obviously own fibre. So we actually went out and went, this is the criteria that we need to meet. So we needed access to our fibre. We're going to build in the middle of the North Island. We knew that. We knew that was going to be a challenge. So we looked at areas where our fibres already ran. So that was nice and easy. The next biggest challenge is we need a lot of power. So we're looking at 500 kilowatts. It doesn't sound like much, especially when you're talking about data centres that are using gigawatts now. But when you're building in rural New Zealand, that is quite the challenge. So we had to go through, look at all the plans with PowerCo, figure out where we could actually build and not have to spend $1 gazillion building more infrastructure to support that. So that was challenge number 2. Then we had to build on stable land, challenge number 3. And then the biggest challenge, we needed a 10 degrees line of sight to the satellites as well, which basically meant you had to build very rural because you couldn't be next to any large buildings or be in an area where someone was going to build next to you. And it had to be in the middle of the North Island. And the reason for that is because of that 10 degree line of sight of the sky. If we're in the North Island, we wouldn't be able to reach a satellite that could then talk to the South Island. If we're in the South Island, we couldn't reach a satellite that can then talk to the North Island just because of the way the beams form. So we had to be in the middle of the North Island. And then, typical stuff as a carrier, you need to think about site security. These things, they get a bit, people don't like unknown things, especially when there's big satellite dishes in play. So we found one. So after a lot of digging around, we ended up finding a spot in Martin, of all places. And the reason why we ended up in Martin is because we went to MB and said, we want to use that QV band to uplink our satellite. And they went, that range isn't actually something we actually give out at the moment, and we've earmarked it for 6G. And I went, what, 6G, really? And so they went, well, so since it's earmarked for 6G, you can go in Martin because we don't think Martin's ever going to get 6G. So, so that's how that ended up. And we don't really understand because it's a QV band. I don't think we're actually going to use a QV band in 6G, but that's what it's earmarked for in NB land at the moment. Sorry, Martin, no 6G for you. But it did make our lives easier because it narrowed us down from 30 sites down to 1 pretty quickly. Thankfully, the site we found in Martin had power. We worked a lot closely with PowerCo. 500 kilowatts, they kind of looked at us like, really? You want 500 kilowatts there? But yeah, thankfully, the site that we found was next to some 11K feeders, and so we'll be able to get things onto those, get things stable and onto that, pretty quickly. It had 10 degrees line of sight. I've got a bit of a story about drones in a second around how we managed to achieve that. But in my grand wisdom, I went, let's put the satellite station, where's my pointer, next to the road, right? Nice and easy. You get your cars in, get your cars out. Story, that will come up soon, why that was kind of important. And then site security, right? So, and when we've currently stuck it, you can't see it from State Highway 1, so it becomes a bit of out of sight, out of mind for a lot of the locals. And more importantly, it had 2 degrees fibre, because, in the middle of nowhere, getting access to fibre is pretty hard, especially the type of fibre that we needed. So for us, we managed to, where's my fibre pointer? We managed to actually get a fibre line down here and then into our site, and then actually pull one off State Highway 1, so we could actually get diverse fibre into our landing station. This particular one will go down to Palmerston North, and this particular one will actually go all the way up to Hamilton. So yeah, thank you Nokia for lots of money spent on optical kit to get us from that site up to Hamilton, and thanks Flex Optics for the optics that are going south to Palmerston North. So yeah, really cool type of setup there. Yeah. Wrong button. So the 10 degrees side of things. This is became quite problematic. And when I said, well, let's go sit next to the road, everyone went, yep, that's a great idea, let's do that. And then we actually got a drone down there to do a bit of a survey for us. And then they plotted 10 degrees out from where the satellite dishes were going to go. And we actually found that we're actually going to hit most of the trees that are surrounding that whole area, so couldn't put the station there. And you start going, oh shit, do I just go talk to the neighbours? Can we get them to shut their tree down? And the farmer was just like, nah, that guy's very anti-anything, so you're not going to get anything out of him, so just, let's do something else. So we ended up finding, I'll just go back a second, we ended up finding a nice spot that actually worked off the road, but still had farmers access roads to the site itself, which is cool. So on the site, you'll see we've actually got 6 satellite pads. We've actually expanded because we know, we're potentially going to need 6, but we're only going to build 4 to start with. And then we've got a small data centre that sits there. And the reason why we have a small data centre is we have to effectively hold quite a lot of kit, right? We're not just putting a couple of ENO-Bs in a cabinet. There is a whole heap of stuff that goes in there. Obviously, a lot of our transport equipment in there, but there's a lot of servers, etc., that control all the satellite dishes and all the moving dishes, etc. And all the other stuff that AST comes with, management platforms and all that sort of stuff. The gateway is designed to be standalone, so if you lose the internet, the platform still runs. So there's quite a lot of kit that actually sits in the gateway to pull that off. And here's a picture of the gateway in action. So we've actually got a pretty cool camera that's sitting there taking photos of us. So we're going to have a nice time-lapse camera. But you'll see my nice artist impression of our little bunker that we're building. So that's going to take probably 12 to 14 racks worth of kit. We end up going to put 2 generators on site because we kind of deem this to be a very important site. It's going to have 48 hours of fuel if we can afford the fuel by the time we actually build it, and 2 generators. The idea behind this is we needed this site to be pretty robust. It is built, if you know the building standards, we built it to what's called an ILM 3, which is a level of importance. We didn't want to build it to a 4. That's like hospital grade, military grade. We took one down. We kind of see this as this must stand up to a big storm because this potentially is New Zealand's get out of jail card if we have another Cyclone Gabrielle. And people need to dial 111, And just on the 111 thing, at the moment, and this is going to change, you can't dial 111 on a SpaceX mobile. You can text if you're registered, but you can't dial. So what we suspect is going to happen, and this is to be very device specific, is if you dial 111 on your mobile and you're hooked up to one of the SpaceX offerings, it will fail, the call will fail, and we believe that based on on the device, it will actually then try other carriers and eventually hit the AST mobile and actually better produce a 111 call. So we're pretty excited about that. But because of that, we have to build to a higher standard because we don't want this thing to fail on us for various reasons. Here's a picture of effectively what the satellite dish is going to look like. To start with, we're just sticking with the actual antennas themselves, but we will effectively put a radome on the outside of it as well. The radome is quite important for a resiliency point of view. The dish itself will operate up to 120 kilometres an hour winds, so you're still at the range, but when you actually put a radome on top, you're talking 160 miles per hour winds that it can suffice, which is in the 300 kilometre range. So it's makes it considerably more resilient. Like anything good, it comes with its own air conditioning unit. That's more designed to keep the radome hot. So, in the icy conditions, the ice melts away, not that Martin gets very icy. Or in the extreme heats, we can actually then cool the whole radome down, which is where our 500 kilowatts comes from, because those things, they're about 50 kilowatts each. So, lots of power. And that's pretty much me in a nutshell, right? I mean, that's a pretty whirlwind tour on Space Mobile, but any questions?
Hey, couple of questions related. How far off the coast will your footprint extend? And the second question, how far off the coast would it be allowed to extend legally, I guess?
So the answer to that, if you just go back quite a few slides, is we get to pick and choose where those hexagons are on. Right, so that is effectively a commercial relationship with SpaceX. We can actually choose to extend them out quite a big distance. We can actually go quite far out with it. It just comes down to how many ENOBs you want to put into it and the commercial relationship with AST, how far out you can go out. So we have thought about it, do we go to people like Cordia, for example, and say, hey, let's extend this footprint so you can do IoT for marine traffic, for example. There's nothing stopping us doing that. It just comes down to commercials.
You said there'd be 5 megahertz of spectrum dedicated to it. What band is the spectrum going to be in?
That's in the 900 megahertz.
900 megahertz.
Yeah.
Excellent.
Yeah. And it's 5 megahertz per hexagon, right? Not 5 megahertz for the entire constellation. It's 5 megahertz per hexagon, 400 kilometers squared. No, because it's different, because you've got to have 5 megahertz here, which is different from those ones around it.
I think you only have 10 megahertz worth of 900 spectrum.
Yeah.
So you're just you're A-Bing it.
Correct.
Yeah.
Yeah.
Okay.
Having to map it very carefully.
Okay.
Yeah. Very poor in the 900 megahertz space.
So I can see that the difference between AST and Starlink is the range of where the satellite is.
Yeah, correct. So we'll go back a few slides again. Wrong button. We're sitting at the 600-ish altitudes. SpaceX is around the 350.
Is there any impact on latency for?
There will be. Yeah, rightly so, right? Because it's higher. So there will be an impact for latency. But we're not being a broadband operator. We're not selling Starlink type solutions. We're just selling mobile solutions. So we don't think it's going to have much of a customer impact on that.
Right.
Yeah. But the advantage is much bigger antennas at the same time, right? So the main difference between SpaceX is they've got small antennas, AST's got big antennas. When you're talking to a cell phone that's only got a small antenna here, the big size is going to make that much more difference.
Right.
How much of a difference, yet to be seen, but like for example, you wouldn't be able to get an AST signal in here, but you may be able to get an AST signal in your car, for example.
Right. And you guys have tested the quality and it's pretty good so far?
We haven't tested it ourselves. It's been tested by AT&T and Verizon. We're still waiting. Once we get a gateway build, which will be June, we'll be starting our testing process then.
Yep. Just on the 10-minute cycle of the satellites and the handing over, is it a complete change each 10 minutes, or do they kind of, wipe across the satellite? So if they're, say, going north to south, the incoming satellite starts taking over from the north and drains off the departing satellite.
Yeah, so it should be seamless to the user. Once the full constellation is up, it will be seamless to the user. When that satellite starts going out of range, there will be another one that's already in range. Using beamforming, there will effectively hand over between the satellites.
But it's the entire satellite at once, or it's a transition of each hexagon, like it goes?
Yeah, I'm not too sure. I haven't gone into that much detail with them. I suspect it's a full satellite swap over, but I don't know for sure.
Hey, 2 questions. One is for your scenario of Napier being offline and everyone switching to this.
Yeah.
Have you got a way of, shutting down phones, hogging all that spectrum? If everyone's phone's trying to watch YouTube, clearly it's going to fill that 5 megahertz up.
Yep.
Is there a way to go, we're going to prioritise 111 calls first, followed by normal calling, followed by basic data?
Correct, because it's all controlled by our call network, right? So our call team can start, we don't want data, right? Turn data off.
Yeah.
Only prioritise 111 calls. So we've got the full control on our core. We've got the full control and come up with those rules.
Yeah. And does that apply? I mean, obviously the downlink to the phone you can control, but what about all the phones uplink? Like, could you have lots of phones trying to overwhelm the uplink direction?
Correct. Yeah, we got that, and that's one of the risks we're going to have to try and overcome. Right, is how many phones are going to try and latch at one time.
Right.
It can support that. All those things we just don't know yet. It's going to be a see and try basically. But we can use the HSS to reject a lot of those and only accept some. There's lots of options we got there. Yeah.
Cool. And then the second question is, will this be seamless to the user from like a commercial and cost perspective? If you roam to this because you're in the wilderness, will it just be to the end user, they won't know any different and it won't cost them any different, or might this be kind of you get charged a different rate if you roam to this? Do you know how that's going to work?
I do know, but I can't talk about the commercials yet, but yes. But if you are enabled on the AST network by us, then it will be seamless to the user. You wouldn't notice it. So if you're driving down the highway, for example, and you go from a terrestrial to an AST to a terrestrial, the theory is that you won't lose that phone call and it just carries on.
Cool, awesome, thank you.
That's us. Thank you very much,
Cool.
Simon.
Thank you.
And with a little bit of delay, we are starting the next presentation, the last presentation of the second session. And please welcome Abuzar Asadi with a presentation on the evolution of optical transport.
I need to set up this, just a second. Yep, there you go. Good afternoon. My name is Abuzar. I am Technology Manager in Chorus. Last year, we launched our 400 gig product in the market. Today, I'd like to share our perspective on where we think the optical market is heading towards, and the thought process behind what we have done, what we are doing, and where we are going, and why. Sorry, I need to connect this. Yep, there we go. In optical transport, the evolutions do not happen in a straight line. We have leaps. The last big one, I think in the last at least 15 years, was the introduction of the coherent optics and the digital signal processing. With that, we were able to compensate the dispersion. And also, we unlocked the new modulations by using amplitude, phase, and also polarization multiplexing. With those advancements, now we can achieve higher line rates from 100 gig to 400 gig, 800 gig, and beyond. I found this chart from, So this is from Omdia, showing the total capacity of the optical transport globally in petabit. And I like it because it shows the portion of each line speed in the total capacity. As you see, the blue line is the 400 gig. And 400 gig has been used more and more. And I found another report from Signal AI, but I have it here. It says the adoption of the 400 gig in the first 5 years has been 3 times faster than any other line rates. And actually 800 gig is going to break that. And that aligns with what you see here in the report from Omdia. The pickup from 800 gig, as you see, is a start from 2025, 2026. 1.2, 1.6, probably from 28 and 29. They start to pick up and to dominate the network. Well, why is that? I think we know after the presentation this morning from Sienna, they're mostly used for the hyperscalers, data centers, and DCI interconnect. But I'd like let's look at the key technology enablers of how we can achieve these higher line speeds. Well, technically, to have higher line speed, we need higher baud rate and more advanced modulation. For higher baud rate, we need faster DSP, and for faster DSP, we need smaller and faster CMOS. Today, we are using 5 nanometer and 3 nanometer CMOS in most of the optical transport domain. Soon we'll be able to use 2 nanometer or even a smaller one, which makes the line rate faster, the DSP faster, the baud rate more. The other thing about the modulation is that we have 16 QAM and we have 64 QAM mainly in the optical transport. The challenge with the 64 QAM is that we have 64 constellation points. And when you have more and more of these points, the space between them gets smaller and smaller. And what happens is, if you use it, especially on a long reach, these become more sensitive to noise. And what happens is that in the receive end, it gets a little blurry, so we cannot recognize those points. And eventually, we have to fall back to 16 QAM. That means that we have to go from 6 bit per symbol to 4 bit per symbol, which reduces the line rate and the speed. To overcome that, one of the ways is to get a bit smarter. And the PCS is the modulation to achieve that. It's probabilistic constellation shaping. And in a high level, what it does is that it reduces the probability of using the outer points in the constellation, in 64 constellation. And by doing that, it reduces the energy, and also it can achieve so with the same reach, we can use the 64 QAM. Well, it has a drawback, and that is we don't then have the 6 bit per symbol. Then it goes a bit lower. But it will be more than 4 bit, which is better than 16 QAM. So we are somewhere in between. And that's how we are being smart with using the modulations. The other things that we need to address is the photonic. We have been using the indium phosphide silicon photonics in the optical transport, but they have limited bandwidth. And they are not very useful when it comes to the 1.6 tera and higher speed. There is a new material that has been used, the TFLN. It recently, I think, deployed with some of the suppliers, and I think more and more it will be used globally. The last thing is about the co-packaging and manufacturing. And that is about how we use the DSPs and photonics and where we put them and how we put them together. The Coherent pluggable that you've seen in other presentations, it's not very new. I think it started from 2019, 2020. But when we used it on 400 gig, this co-packaging wasn't that important. With higher speed, like 800 gig, 1.2, 1.6, the connection between the photonic layer and the DSP becomes more and more important, which is called RF interconnect. So the loss on that connection between the two is important for the higher line of speed. And to eliminate that, this co-packaging comes in play and put them together in a coherent pluggable. Well, I know you've seen this coherent pluggable, but let's look at it again. This is the coherent pluggable of 1.6 tera. Well, it's a concept. And the idea is that we use this on a router. As you see on the left, on your left, we have the host ASIC, which is the router card, router port. We have serial interfaces here because it's 1.6. We have 8 of 200 gig. It comes to the optical plug. The digital has to be converted to analog because it's going through the serial interfaces. It reaches the DSP. In the DSP, it converted back to the digital. And DSP does 4 major functions here. One is that it does the high-gain FEC, so it does the corrections, equalization and compensations, modulations and mapping, and finally clock recovery and timing. So these are the major things that the DSP does. But in a very high rate, this would be very complicated, and the computation would be extremely high. Then it would send it through those RF interconnections to the photonic layer, in the photonic back to the light, and it goes on. But with all those advancements in the optical, the coherent pluggables, now we have higher speed, like 800 gig, 1.6 tera, coherent pluggables are coming in. And that would change and shift the way that the transponder has been used. And that is the next slide I wanted to show you. Again, this, I think you've seen this in the morning, but I'm looking at it from a different angle. On your left, you see the traditional embedded transponders. So this is the transponders or the line card that we have been using for ages. Here we have the DSP, everything inside the transponder. The pluggable is basically just photonic layer and send it the light through the fiber. The problem with that is that, well, they're bulky, expensive, they need a space, power, so on and so forth. Now we have this coherent pluggable, which are very small, very light, cheap, well, a lot cheaper at least, but they have their own challenges. The first one is that if you put it in a router, we have a limited power budget. The router port has roughly the new version of them, at least. They have 20, 25 watt maximum per port. The other challenge with this coherent pluggable is that because the space is also very limited, especially if you use the new form factors like QSFP-DD, within that space, the DSP becomes smaller and smaller. So you have to compromise something. You cannot do the computation that you expect from a big transponder. And the compromise is that it doesn't do very well in a long reach. So at least not yet. So maybe with the advancement of the technologies, one day we can achieve the same reach, but at the moment, the reach is limited. It can be used in some certain scenarios, but in a long haul, it's still not as good as the traditional transponders. The other issue is that you are putting this in a router. You need to manage it. You need to do the troubleshooting. How can we do that? We are in the optical layer, and we want to talk to IP layer, and integration is required. Most of the suppliers, as far as I know, they're using TAPI, the Transport API interface, to do that. But it would be challenging. Any integration, whoever works in the operator side, they know it's challenging, time-consuming, and it has its own issues. So is there any other way? Well, there is. So we can use the coherent pluggable because they are cost-effective, they're easy to use. But instead of putting it in the old, big, giant transponders, we can put it in a trimmed version of the transponder. That trimmed version is called thin transponder. It's a very light one. It doesn't do all the functions, but that's the idea. So we want it to be cheaper or more cost-effective rather than the embedded transponder. So with the two, with the coherent pluggable and the trim version of the transponder, now we have a cost-effective solution, which is better than the transponders, and we resolve the problem of the management and troubleshooting. But the reach still is an issue because the reach actually resides with the coherent pluggable, and more or less the same as the coherent pluggable reach that we had. Again, with this all advancement, the other impact in the market is the business model, especially the cloud service providers and hyperscalers. Traditionally, again on your left, the cloud service providers, they own and operate everything. The fiber, the network, the operation, design, architecture, everything is coming from the providers. But we have seen that the hyperscalers do not like it much. They want to be in control. They want to do the design. They want to be involved in the architectural design of the system. And we have seen that sometimes they just come, get the fiber from these providers, and they build everything else by themselves. But it has been challenging for them as well because the operation is new to them. They haven't been doing the operation of the optical transport. So that might be a bit challenging for them. There is a new way by using all these technologies, coherent pluggable, thin transponder, and so on and so forth, which is called Managed Optical Fiber Network, or MOFN. And in that, the service providers, they own the fiber, they do the operation, because it's easier for them. They've been doing it for ages. Hyperscalers, they get involved in the architectural design of the network. And when it comes to the network itself, well, here there are different ways of dealing with each other. One way is that the service providers, they can own the optical layer, but electrical layer, which is the transponders or coherent pluggables, that can be owned by the hyperscalers. So this is a new business model that became available as the result of these advancements. Now, we talked about this line speed and how we can achieve higher and more line speed. But we have seen that some hyperscalers or even operators, carriers, they are not using the highest speed possible, and especially in a long haul or ultra long haul. They use sometimes even as low as 200 gig. But why is that? To tell you why or show you why, I have a very simplistic math here, just to prove the point. It's not that simple, but bear with me. So we have, I have 1.2 tera line speed and 1.6 tera line speed here in the picture. On the left, as you see, 150 gigahertz is the normal channel bandwidth that we use for 1.2 tera. And the other one, 200 gigahertz for 1.6. Now, again, for simplicity and for apple-to-apple comparison, let's assume we are using only C-band. We have super C-band, we have C plus L-band, but let's assume we just focus on the C-band, which is around 4,800 gigahertz. How many channels I can have for both of these 1.2 tera and 1.6? Well, 4,800 divided by 150, that's the quantity of the channels of 1.2, and divided by 200 is the quantity of 1.6. So on 1.2, we have 32 channel times 1.2 tera, that is 38 tera capacity. On the 1.6, we have 24 channel times 1.6, again, 38 tera of capacity. So we are using the spectrum differently on different line speed, but we end up having the same capacity on both scenarios. So line speed is not, I would say, the major factor here. There are other factors. One of them is the reach, and I think this is very, very important. Why? Because if you have a shorter reach, you need regeneration. Regeneration means more transponders. More transponders means more expensive. Also, it depends what type of transponders you're using. Are you using something from your inventory, or you're willing to buy new transponders which are probably more expensive than they should be? They're new. It takes time to cost for them to go down. The price goes down. So there is a compromise you need to make, and you need to decide, first of all, what capacity you need in overall on your line and on your fiber. If you can achieve the capacity that you want with the lower speed, and you are thinking of doing long haul or ultra long haul, that's the way to go. So it's not only about the line speed. The next feature I'd like to show you is called inverse multiplexing. And the reason I put it here is that sometimes it's related to line speed. Sometimes on the line speed, we have some odd numbers. So for example, we have 1 tera that we can achieve on the line. Well, if you have 1 tera and the client interface for you is 400 gig, you get 2 400 gig, and the third one is 200 gig, which is not ideal. You want to have only 400 gig. Inverse muxing is a new concept that allows you to put 2 line speed together. So for example, you have 1 tera, you get 2 of them, 2 tera, then you can divide it by 5, and you can have 5 400 gig client interfaces. We had the multiplexing from the client end. So it's not new. We have Mach sponders that put different speed from the client side to the line side. But the reversing that, I think that's very interesting. So it gives us flexibility on the line side. We can go with any line speed that we can achieve on the fiber. So far, I talked about the speed, the features, functions, but I wanted to talk about the hardware as well. And the first thing, I think the important thing is the node configuration. So when you're designing a network, you need to know what type of node you're putting at certain locations. And each vendor, each supplier, they have their own way of putting these modules together and building a node. There are different type of systems, node configurations, but we can categorize them basically in these four: colorless, the traditional directionless, contentionless, and flex grid. The most important thing for the higher line speed 400 gig or any coherent network is the last one, the flex grid. Why is that? Because when you come to the 400 gig, 800 gig, the bandwidth that you use is not a fixed bandwidth that we had in the past 50 gigahertz or 100 gigahertz. It changes, and we have so many different profiles for every of these line of speed. Like 400 gig, for example, it can be 87 gigahertz of bandwidth or 112 gigahertz of bandwidth. More bandwidth means it has better reach. But what you need to have is flex grid, meaning that you need to be able to put all these odd numbers of the bandwidth together to have a better spectrum efficiency. The rest, it really depends. Let's say, for example, you have a 2-degree node, one link coming in and one link going out. It doesn't make sense to have a directionless function in that node because you don't have any direction. You have only two. There is no other option. Also, if you're not adding or dropping any services at the site, then you just go simply by adding amplification without any of these functions inside. The next important things, I think, for the hardware is picking the right client interfaces because you're facing customers, you're facing your RSPs, hyperscalers. So what type of interface they prefer to have and you want to have for your product. For our product, the 400 gig that we launched, we are using the FR4 and LR4, which is in the QSFP-DD format. And it's been using the PAM4, 112. There are many different types. As you see, the 800 gig is coming up. And the last row is the ZR optics. These are the ZR optics that are available. Actually, I borrowed one from Nokia, the booth next door. This is the 800 gig. If you're interested, you can go and see afterward. This is an 800 gig OSFP. Is a ZR optic, and because his OSFP is a bit bigger than the QSFP-DD, but the good thing is that it does more modulation and functions and features which can be useful. There are other, so these are the roadmaps. After 800 gig, we're getting the 1.6 tera, and at some point we even reached 3 tera pluggables. There are other pluggables. I didn't include everything that is happening in the optical area. I think we had those topics in the morning from Siena, which was good. There is one that I like to add here, and that is called double-sided optic. And the reason they're doing that on the client interface is that it would eliminate the electrical interfaces between the router and the pluggable. And because the electrical interface in that side has a loss, and that loss would prevent us of getting the better and higher speeds. So far, we talked about all the features, functions, hardware. Now let's talk about Chorus and what we've done. The first things, so after all this decision about the node configuration and so on and so forth, the next is deciding about the span lengths. Why is that important? Well, we have done many simulations, and we realized that for the EDFA spans, which is the normal amplification, the best performance that we can achieve is within 60 to 80 kilometers. If you go more than that, you lose the performance. If you go shorter, you get ROADM cascaded loss, so that's not ideal. For Chorus, picking the right span, to be honest, wasn't that difficult because we have thousands of cabinets, so we can pick any locations, we can use any cabinet for amplification. And also we have more than 600 sites, so probably it was easier for us than others. That is the status of us. In Chorus, we have 55% of the span are less than 80 kilometers, around 40% 80 to 100, and around less than 6% maybe more than 100 kilometers, maximum 118. On the network side, 65% of our network today is FlexGrid, and we are going to upgrade them all by end of this year. ROADM configurations, we had some very old ones, especially in the rurals. The plan is to replace them by probably 2027. The router that we have been using, we're using Nokia. The thermal, the power budget that they have per, that's a typo, per port is 25 watts. The other things that we have considered, especially for diversity, New Zealand is very long. It's like a ladder. We have east and west with several rungs. So third route is really challenging. Cook Strait, of course, we know the fiber status. South Island, the west coast, that's another challenge. We had so many slotted core fibers that we had to replace. North Island or far north, we didn't have very good ring or network up there. We upgraded our system. I'm going to show you the network diagram. So as a result of all of those changes, we could achieve 800 gig from Auckland to Wellington on 150 gigahertz bandwidth without any regeneration. And this is about, so the architectural of this allow us to use thin transponders in the metro. We have an Auckland Metro network. Within that, we are using thin transponders. As I explained, it would be more cost effective because the reach is shorter. On the long haul, we are still using embedded transponders. And next, we are considering of offering wavelengths as a service or IP over DWDM. If you are interested, come talk to us. We want to see what we can do, what we can offer as a wavelengths to the market. The constraint, I think I explained about them, the fiber type, ages, the spectrum. We are using C-band today. I think the capacity that we have today on the C-band is enough. We are thinking of L-band. Maybe at some point, if we reach the total capacity, we move on to the L-band. Power, spaces, path diversity, I think we talked about that. And the configuration, again, CDCF probably is the best, but we have other configurations depending on the location and the site. And we are using those advanced transponders in certain locations. Now, before I show you our network, I just wanted to look at the map and see what we can achieve in this map. We have several topology that we can pick and we can deploy in the network. Well, full mesh, of course, is the best, but it's very expensive. You have so many connections. Partial mesh probably makes more sense, especially when it comes to the metro environment. And that's what we are doing in Auckland Metro. In Auckland Metro, we have around 20 sites, and between them, we are using partial mesh. Some of the sites, they have more than 5-degree connections between each other. For the rest of the country, as I said, it's mostly like a ladder, so we have east-west and with several rungs. But within that, we can have different rings. So that was our idea. So we built several rings all the way from the South Island, all the way to the far north. This is the as you see on your right, this is a network diagram of the 400 gig network that we have designed. The Auckland to Wellington piece has been completed. That is ready to use. The South Island one is under deployment. We expect to finish that by end of 26. As you see in North Island, somehow we have the third route, but in South Island it's very hard to get that third route. Still is 2 route with several wrongs. And this network, of course, we are running the 400 gig today. We are offering 400 gig, but because it's flex grid, I explained everything. It is capable of 800 gig, 1.2, 1.6 tera speed. If it's required at some point in the future, we believe that 400 gig for New Zealand probably is enough for now. And this is the original network that we've designed. This took us probably more than 3-4 years to be completed. We have more than 20 rings in these regions. From far north, as you see at the top, we have, if I get this right, so we have a ring here, another one, another. So we have 4 rings north of Auckland. And then in the central North Island, we have several rings, comes to Wellington, another one. And then in the South Island, we have, actually we built the Otago first for some reason. We have 5 rings here, and then we started building on top of that, and we completed almost all of this. It's not fully completed, it's under deployment, but we believe we can finish all of them by June 2027. And that is it. Thank you so much. One question? No question. Thank you.
I'm aware that I'm the only person standing between you and lunch. I will be really, really quick. We will start 1:30 sharp. Please come back. Rebecca Bix asked me to remind everyone that the registration desk will close at 1 o'clock. So if you need something from her, please go and see her now. And also there are a few t-shirts in different sizes left. First in, best dressed. See you. Thank you.
All right, let's continue on after lunch. So our next speaker, unfortunately, we made a mistake on the program, so it will be Rick Williamson and Rob. They will be presenting on experiments in topology visualization. I'll let them introduce themselves. So their session will explore BGP-LS to visualize live network topology and traffic engineering data. So Rob and Rick, over to you.
All right, hi everyone. So today we're going to talk about our recent experiments using BGP link state to create real-time visual graphs and simulations of a network. So some introductions first. For those that I haven't met, my name's Rob. I'm a network architect at Cordia, and my role focuses on planning, designing, and evolving Cordia's IP network.
Hi, I'm Rick. I'm the founder of Helios Software AU, and I design software control and software visualization.
So, why do we want to talk about BGP-LS today? Why does it matter? We can summarize the rationale from the original RFC as sometimes we want systems outside of the network, like controllers or analytics tools, to perform calculations based on the topology or traffic engineering state that normally exists only inside the IGP. So, BGP-LS was created to let routers export their link state database to external systems. So instead of building topology by scraping devices or passing configs, an application such as a PCE can receive the network graph directly from the control plane and build a real-time view of the topology. So BGP-LS provides a standard way to export the link state information to an external application, which would then perform path computations outside of the routers. Note that the original RFC was only the foundation layer. Other layers were added and updated later on to deal with extensions like TE, and we'll talk more about this later. So, yeah, the origins of our experiment. We both spent about 2 to 3 years working on a large-scale National Safety of Life project, and that was known as the PSN. This included working through the RFP setup phase, followed by the service management design for Rick, and the network design for myself, and then we went into pilot and build phases.
So certainly for me, the PSN was very unique. I'd never done a greenfield network before, and it was odd, really. We had an elegant design, thanks to Rob here. We had a structured build plan. We had all the metadata in the world. We had sites, devices, links. The challenge from a service management perspective was, could we generate the entire logical model of the PSN just from that metadata, just the design, sites, links, routers? And it turned out after a while we could. So it turned out that what we could do is take an event from the network, parse it through this logical model, and spit out ITIL-flavoured incidents, SLA-flavoured incidents at the end of the day. That was the good part.
Yeah, so I thought what Rick had done for PSN was pretty impressive. By using the defined design rules, we could pretty much reconstruct the network topology before it even existed. So it was predictable, consistent, and pretty powerful from an operational visibility perspective. But I raised the challenge. This capability works extremely well in a greenfields environment where we control the architecture, enforce strict design rules, and maintain consistency. But what about pre-existing in-service networks? In those kinds of environments, we don't necessarily have clean, templated design intent to build from, and especially in DMR or WISP networks, where the topology is often dictated by geography and grows organically over time. So the question became, how do we model those networks? Instead of relying on declared design rules, why don't we just derive the topology directly from the control plane? Could BGP-LS help us to extract the network's actual state and build a similar model dynamically? So I sent Rick a stack of RFCs and white papers and said, let's see what you can do with these.
Right, so after 2 days, we were comparing notes, we were reading the RFCs. I'd never seen them before. They're pretty terse. I don't know whether you've read them before. Quite ugly. So we decided very quickly, reading the RFCs, we needed to build ourselves the smallest possible mesh network. So that's what you do. If you're not a network engineer, you end up drawing it on a piece of paper like this. We've got 3 topology nodes, and we've got 1 node using Cisco's little CSR 1000 virtual router. So that was our producer. Then we have a bunch of other little nodes. So I built this by hand, got it to work, got the CLI to dump the link state, and it looked good from that perspective. But then the consumer side, that's a little bit more difficult. First of all, we wanted API access. We didn't want to just dump the link state and then be done. We wanted API control. So what we did is we identified one open source project out there that could do this for us. There's a project out there that you can all use. You can all download it for free. It's called GoBGP. It's there, it's free. The downside is it's based on Go, which is Google's language. But you can download that, you can compile it and run it, and it will act as a service, like it'll connect up to your consumer and exchange link states. But that one does not support BGP-LS. Fortunately, though, the API underneath it does, so you can actually run this thing as a little baby consumer and dump the transactions out into XML. Unfortunately, they end up looking like this. This is what they look like. In fact, this is not all of what they look like. This, if you saw it on a page, it would be 3 of this. End up being under the floor somewhere. This is one transaction table update. But I've highlighted in there, you can actually see the moving parts in there. There is hope. There is topology stuff in there. Even the state of the table update is in there eventually. But it's very hard to read, I think you'd all admit. So we decided to chuck that into GraphViz. I'm pretty sure some of you at least have used GraphViz before, open source again. When you throw that topology stuff into that tool, you get something a bit like this. So what I'm about to do is log into the CLI on one of the nodes and admin down one of the links, basically. And this is what you get, a bunch of table states in graph form. So you get, that's what the graph looks like before you admin down, and then gradually over time, you see the table updates come through and GraphViz will redraw the graph, and eventually it repairs itself. It's not the same picture it started with, by the way. So 2 days in, we were looking at this like this. We weren't very happy. Well, we were kind of happy with that kind of did work. You can get link state out. After 2 days, you do not end up with a useful tool. It's not what we were used to in PSN land, and so the dream had not been achieved in 2 days.
So we thought, if we're going to build a proper BGP-LS consumer, then what type of features would we like to include? So firstly, maps. If we had the GPS coordinates, we could overlay our network model on top of something like Google Maps. Memory, which is about state, such as the router or link changes, and those needing to be retained. What-if scenarios. This would allow for non-destructive fault simulations inside the model. Playback, so any IGP events captured by the BGP-LS consumer could be replayed like a VCR. Link costs. This allows us to see the impact of link cost changes or highlight discrepancies. And scale, so let's make sure this thing can handle larger networks, maybe hundreds of nodes. Now, bringing that all together, this is what we've got so far.
First of all, maps. We wanted Google Maps. Well, we actually wanted more than one sort of map. We wanted 2 sorts of map, but the first one we wanted to look at was Google Maps. Now, obviously, we mentioned that we wanted GPS locations. If BGP-LS doesn't do that, routers rarely know where they are, so we wanted to use the syslocation field in SNMP. We basically just dump the GPS fields in there, and then we can get it back at link table update time. But it's not quite as easy as it sounds. Even if you have GPS, just my apologies to any flat earthers out there, this semi-polar coordinate GPS transform does not work on a map. You have to basically map it to a Mercator. And if you do the transform correctly and you pick the right Mercator for whatever country you live in, you end up being able to map the GPS to a 2-dimensional space. But then you need a map. And in this country, you get the maps from LINS, and if you match the transform you did to the GPS to the map, you can stick the routers over the top and it matches. The other way we wanted to do it, because that's kind of messy, we wanted a purely logical layout. Now, if you have used GraphViz in the past, there is a format that you can give GraphViz a hint called NITO, and NITO will lay out the map using sort of mathematical it's stress minimization and force directed layouts and things. So we wanted to lay out like that, and yeah, much easier for different audience members. So I think that side is for the NOC, and the more automatic layout is best for traffic engineering people and change management folk who don't really want to see where it is, just how it is. Now, this is all it's all very well in 2D static, but we want to be able to show you that you can actually take those GPS things into the consumer, store them, and then basically interactively move them around. And if you're very brave, you can put them back in the network. So, eventually, you deploy this sort of thing into the back end of your network, and you want to know what happens when you first turn it on, when the database is empty. So what I've done here, I've got 2 panels. On one side, I've got the stress layout. On the other side, I've got the GPS layout. And on the bottom is the consumer the console from the consumer. How good is that? Okay, righto. So what we're going to do is I'm going to show you what happens when you try and load up two IGP networks. One of them's a 30-node network, and the other is a 40-node network. Now, if you do this in real time, it takes about 3 minutes, but that's a hell of a long time up here on a podium. So what I'm going to show you is the first 20 seconds real time, and after that we'll speed it up. So here we go. What I'm going to do is just enable it, and you can see the table updates, specifically the link table updates are coming through. You can see they are pouring in, and then eventually the visualization tool picks them up. And about now somewhere they're going to start to go about 3 times speed. So this is one IGP at a time. So if you're pointing the consumer at multiple producers, then it'll do one of them at a time. So this is one network coming through, and this is probably the 40-node mesh. It's done it, and now the other 30-node mesh is coming through. I prefer this one because it looks a bit like protein folding, I think, but that's what it looks like. That's a real network. Okay.
So to test how this scaled, we needed a slightly larger network than our lab. So we actually deployed this into a live WISP network, which is thanks to Uber in Northland for trusting us with that. Next slide, right? Yeah, so at Uber, the backbone area contained roughly 50 to 70 OSPF routers. So we established the BGP LS session. We began ingesting the live control plane data, and we reconstructed the full topology of their area 0 from the production state. So that validated 2 important things. Firstly, the approach scales beyond a handful of lab nodes. Secondly, it works great against real-world operational networks, not just clean test topologies. So here's just a view of Uber's area 0, and it's the geographical view, and we've pulled those locations from the SNMP. Just note some of those links are red, just because of a simulation that we had going at the time.
Link down. What I'm going to do here is I'm going to show you me fiddling with one of the topology nodes. So I've got the consumer at the bottom. I've got a SSH session to one of the VIOS nodes. The node that I've ringed in that little diagram is the one I'm going to be messing with. Now, you don't have very long to watch this because I've got pretty aggressive BFD timers running on this thing in one direction. So I'm going to hit go, and you'll see me disabling one interface. That's me doing the commit, starting the timer, and in about 4 more seconds you'll see the first withdrawal come through. There it is, the first withdrawal just gone through, and the link's gone down, it's gone red. The other direction takes a bit longer. If you're patient, then you're about 36 seconds in, you'll see the BGP timing out, and the other link is withdrawn, which takes a long time when you're standing here watching it. You've still got 6 seconds to go. And you'll see the withdrawal coming through any time about now. Yep, that's the other end of it gone.
Yeah, so for shortest path and what-if scenarios, the intent here is to be able to perform a path calculation and then model the impacts of any changes on that path. This demo is best shown in the logical view rather than a geographical map. So here's an example of how we can do a link cost change simulation. So we've got 2 PE nodes selected, and I think Rick, you can highlight those. Yeah, at the edge of the network. And the software is just going to show us the normal path used by the IGP between those 2 nodes. That's the line in blue there. Now we'll play around with the path costs. And so firstly, we're just going to simulate a failure of that link right there, and we'll see the blue path moves around, reconverges around that failure. Then we're going to simulate just a cost change of this link here. So we'll increase the metric, and we can see that blue path again move around that higher cost link. And then I think finally, we'll just take that link there out. And again, we'll see that blue path just moves back to the higher cost link. So this is another good use case, is understanding the impact of a node being down. So here we've got the same path between PEs, and we're just going to zoom in, select a node, take it out of action, and we'll see that node go red, plus the links that are associated with that node. And then we'll do that again over here. And each time the software just works out what the next best path is based on the SPF. We can go next slide. Yep. So this is about playback of events. So imagine if you come into work one morning and you discover that there's been some events on the network overnight. We would have already captured those in real time via the BGP LS feed. So we can actually use a playback type feature to replay these events and observe how they may have impacted any end-to-end path between PEs. So again, this is just an imaginary path starting and ending near Christchurch. But we're just going to use the timeline at the bottom of the screen there to select the window, and then we're going to play back the events within that window. We can also speed it up a little bit, just so we don't have to sit around too long waiting for things to happen. And the path, or the LSP that we're interested in, is shown by the blue links again. And then as links go down, we can see that path being moved around as things happen. The timeline replay window also just shows event by event. And it's the same scenario, just in the logical view, and this time we're just going to step through each event rather than playing out the entire timeline. Again, you can see that blue path just moving around between those PE nodes.
Right. One of the other things out there we were quite keen to try and surface was the mismatch of weights or cost between on a single link. So when you're looking at a network more like this, even if you show the link cost, they're really hard to find the needle in the haystack, because you can accidentally do this. You can unintentionally put in an asymmetric cost, and it'll just sit there until something interesting happens and you end up with asymmetric paths. So the idea here is that we suppress all the ones that are good and just show the ones that are not so good. Just go in and turn that mode on, and we basically just park all the other links and highlight the ones that are asymmetric. And you can see here there are 3. In each case, we've got a cost of 1 in one direction and 2 in the other. Now that may be deliberate, and that's fine.
Right. So for anyone interested in trying any of this out, there's a few other things worth mentioning. So if you're considering deploying something like this into a production network, just be aware of the risks, especially if it involves core routers. One way to reduce the risk is to introduce a dedicated BGP LS producer as a virtual router. Instead of changing existing infrastructure, this router just joins the IGP as another node. Often you could connect this via a spur link, such as a GRE tunnel. The router passively learns the link state database just like any other router. Its role is only to export the topology information via BGP LS to an external consumer. This means that we can extract real-time topology without touching core routers. Just note as well, you do need to take a bit of care to make sure that that virtual router does have enough processing power to handle the SPF recalculations in a timely manner. And this is the approach that we used with the Uber test. Also, it's interesting when dealing with multi-area networks. So things get a little bit more complicated because each area only has visibility into its own link state database. And that means a single BGP-LS producer won't necessarily see the full topology. A common workaround then is to deploy one producer per area. If possible, the most efficient place to do that is on an existing area border router, since it already participates in multiple areas. If modifying area border routers isn't desirable, you can instead run a remote virtual router, or you can use a multi-hop BGP-LS session. Each producer then exports a topology to a central collector, and that stitches those views together to build the complete network graph. Just a note, though, if you do have multiple areas, be careful, because if you use the same virtual router, and if you don't use VRFs on that virtual router, your virtual router may end up becoming an ABR. And a bit on security, so although BGP-LS is typically used just to export topology information, it's still worth treating that session just like any other BGP connection. So firstly, make sure the data flow is strictly one way, and you can use an import policy on the router side to reject everything, which ensures that the consumer can never send routes or updates back into the network. Secondly, enable authentication on the BGP session. That way only the intended consumer can connect. It's also a good idea to place the consumer on a dedicated management network, just so that the BGP-LS endpoint isn't widely reachable. And finally, it's often helpful to configure the pair and passive mode. That way, if the consumer platform goes down, your router isn't endlessly trying to reconnect.
Right. Where to from here for this experiment? Well, we don't think we're done. There's more. We really wanted more than just up and down state stuff. We wanted actual health. And we wanted latency, we wanted packet loss, we wanted available bandwidth and things. And when you look at the RFCs, there are a few of them out there about this. And the ones we looked at and the equipment that we had available to us did not allow us to do all of these things. So yeah, the rabbit hole continues. So if you want to go to NZNOG, by about that time, I think we will have made a big chunk out of this one, and we will see what we can do. And if you want to try this, because we've got that lab up there, we've generated our own lab. So if you want to play with our lab, grab that QR code, go to the website, pick the client of your choice, iOS, macOS, or Android, and then come and see us during the break, and we'll hand you out a username and password, and you can have a play. Questions?
Come a little bit of the way, giving you a bit of a workout. The feature around the traffic engineering, and do you have any idea what you might include there, like packet loss? What features might you look into?
Yeah, you want to go first?
Initially, we're looking at like getting link coloring and that kind of stuff. So those TE metrics, we want to get that out so that we can do calculations based on, show me this path excluding all red links or something like that. That's where we'll start.
Do you have any concerns around scalability, number of links?
Not yet, but we'll see.
Thank you.
Those initial RFCs, they were very tempting. They hint at a glorious future where you can access all the TE data, but they didn't do any work in helping anybody figure out how to do it. These ones, which I had back up there, those ones do. They go into some gory detail about how it all should be done. And we're going to go down this experiment from now on, trying to figure out which vendors have done which piece of it, because one of our observations is that the standards are great, but not everybody does all pieces of it, right? So we don't even know how much of this is actually implemented in real life.
Just building on the talk this morning, have you thought about, instead of doing point-to-point lines from your GPS coordinates, pulling in the open standard for the physical cable paths into your open system? That would be awesome.
Yeah, we talked about that after the presentation yesterday, about some of those APIs and things. Yeah, I was looking at Rob and he was looking at me. Yeah, we would love to get back to that model where we can actually get down to layer, whatever layer we can get down to. Because we're sitting up at layer 3 at the moment, so there's a lot of gold down there. If you can get more, further down the OSI stack, that is the dream actually. That's what we had back in the golden period. We could model it from 0, 1, 2, and 3, 4, and everything is beautiful. When you come in at layer 3, your options are limited. So yeah, being able to go back down again, that would be sweet.
Right, our next presenter is Philip Smith. Philip is a long-standing internet industry expert and training coordinator at NSRC. His presentation provides an update on Route Views project, and I'll let you continue with the rest. Thanks, Philip.
I think I'll just use this. All right, good afternoon, everyone. It's actually been a while since I was at my last NZNOG. I think it was about 10, 11 years ago, so I'm actually very happy to be back. As the folks in the workshop that I did on Monday, Tuesday, Wednesday know, one of the things that I'm involved in and folks who go to the workshop need to be aware of is some of the troubleshooting tools available out there. And so one of the things that I got involved in probably about 3-4 years ago is Route Views. And so I just want to give a little bit of update about what's going on. Quite a few of the industry have used Route Views since it started in, 1995. So there's quite a lot happening now that the project has become a bit less of a hobby of some of the folks at the University of Oregon, and we're now putting some serious amount of effort into modernizing all the infrastructure that's behind the project. So just running through this, it's the background. Not really going to go through it. You can read that for yourself in the future. Important thing is, started in 1995. There are around 55 collectors worldwide now, which are getting BGP tables, mostly hosted exchange points, but also some multi-hop collectors based at the University of Oregon in the US. Quite a lot of folks are actually using the content. There's kind of a lot of detail there. A bit of history about University of Oregon as well. The team members, you'll see those of us popping up in various places around the world. For those of you who came to Jakarta for Apricot a few weeks back, you'd have probably met Nina. And then the other Philip was there. Also, who else was there? Yeah, those two were there, apart from me, of course. So in your travels, you'll probably run into those folks, as we're trying to be a lot more visible than we have been over the years. Fundamentally, it's a tool that lets network operators see the BGP table from somewhere else. When the project started in 1995, I was still in the UK, helping out with the UK's first ISP, and I very joyfully set up one of the first multi-hop sessions to University of Oregon because the tool was really useful to find out what we looked like from the other side of the planet, or at least at that point, from the US perspective. And of course, as more operators joined, you could go to more different places to find out what your routing table looked like, what the path back to you looked like, because you could run trace route and pings and so on from the router prompt. Of course, these days it's gone much, much further. Researchers use the tool because we record all the data and have recorded data since 1997. So it becomes a fascinating tool to let operators find out what happened at some stage in history. I mean, it says there in the slide that they're strategically located. We're not just rushing around the world trying to find any and every single location to put these in. The important thing for route views is to have important, interesting, new, and different kind of views of what we can see in the global routing table. Loads of folks use it. I mean, CADA is at the top of the list, as CADA has been one of the prime users of route views for a very long time. But there are loads of others. We all know the Hurricane Electric, BGP tool, Cantake, Catchpoint. The list goes on. There are loads and loads who are actually using the route views data amongst other data as well. This map's out of date. The University of Oregon cartography folks are working on an updated one, so hopefully we can get that version soon. It's about a year out of date, but it shows the collector locations. And certainly since I started getting involved in the project, like, can we have a few more outside the US and, you know, more interesting places in around the world? So we've got quite a few more in Asia-Pacific region, and we're starting to add a few more in Africa to give a bit more interesting perspectives as well. So some of the interesting things that are going on. All the collectors use FRR, free-range routing. Basically because it's a piece of software, runs on a Unix VM, trying to ship hardware around, trying to support all the different routers and so forth. I know route views started off, it was a Cisco, was it 7200, the initial one? A Juniper one router made a brief appearance as well, and there was a couple of others before moving to, originally it was Quagga. What was it, Quagga was original, or what even became before Quagga? Of course, that's no longer developed, so FRR really is what we're based on now. Also, the collectors, historically, probably was a Supermicro or a Dell 1RU server, got shipped off to somewhere. You fought with customs, you'd then try to get it into the equipment rack, you'd figure out power and all the rest. These days, we're pretty much moving everything into VMs, so simple VM hosted by whoever's hosting the collector, which makes it much easier to deploy, much easier to manage, don't have to worry about broken disks and RAM and all the other things. Most recent ones, these in the last 6 months, Jakarta, that's San Jose in Costa Rica, Lagos in Nigeria, Hong Kong, and we've figured out all the Frankfurt issue because that was a historical one that disappeared and now has returned. So we're adding slowly. We're not, as I said earlier, we're not rushing to add more, but we're strategically adding more collectors. There's an API now, been long requested for many years by a lot of the researchers and even some providers who use the kit. So, because everybody has Telnet, and they still Telnet to all the collectors around the world, and we're hammered and hammered and hammered and hammered by hundreds and hundreds of Telnet sessions per minute. So that is being wound down. In fact, in the recent year, we've actually have to rate limit all the Telnet access because people do Telnet into the thing, show IP BGP, go away and have a cup of coffee where a poor collector falls over. So we really have to restrict all that access now. And so the API doesn't cover all the collectors yet. That's just a pure resourcing issue because there are hundreds and hundreds of full BGP tables, and it's pretty hard to try and have all those in memory all readily accessible and being able to respond to a request for what's the BGP table doing here. But anyway, if anybody wants to play or is using route views at the moment, is trying to do scripting things using Telnet, if you can sort of migrate that to using the API, please, that would really help us. Looking Glass, well, that's the other way. Telnet will go away. We'll leave it on the Cisco. Currently, it's an ASR 1004. That will probably go away. And we'll use, I don't know, the C8000V possibly, or maybe some other virtual router thing that can scale very nicely. But the Looking Glass there covers all the collectors worldwide. So every time we add a new one, Looking Glass access, and that gives the user, I mean, I've got some examples here. The user show BGP thing, show BGP reg thing, and looking up RPKI. Quite a lot of people are using just for simple RPKI lookups. Of course, we support V4 and V6 as well if the people supplying the BGP feeds include V6, which they sometimes do. So just some examples, and then, you know, it's the usual thing that you can see what you get. I was updating these slides in the Crown Plaza just the other day, and I thought, well, see what IP address I'm coming from, and of course, this is just our test collector sitting at the University of Oregon, and there we go. It's the sort of things you can see. What was that? That one, oh, that's just my home broadband, so what my home broadband looks like from one of the collectors also. Of course, the other way is a lot of researchers and consumers of the data want is access to the archive and also access to the live data. There are 2 archive servers, but the live data, well, you know, the data comes off the collectors using MTR, better than trying to do any other way. And that whole process flow is trying to get everything over to using BMP, the BGP monitoring protocol, and trying to make that scale. And that's been a long headache for the folks prior to us who were looking after the route view system, because, well, it's just scaling the whole thing, trying to do the load balancing, the BMP collector. There's a new one that's been developed, and then there's the Kafka cluster to end up to this stream.routeviews.org. So again, if folks looking for BGP monitoring protocol output from this, it's contacting us for that. It's being worked on. We dumped OpenBMP and used something that was developed in-house called BIMPR, done by one of our developers, which just gives us more visibility and a bit more, well, let me say, it doesn't crash like OpenBMP seems to do far too often for us. So there's a lot of detail there, but it certainly lets us, well, gives us a lot more scope at making the thing perform. What else? So yeah, the archive is huge. I think it's way more than 50 terabytes now. There are a couple of archives, still rsync from that, but looking at other ways of trying to spread this around. So there are other copies of this archive, because having 2 archives, well, if you know where Oregon is, you know, the Pacific Northwest, and you know where the Northwest, well, the North American plate finishes and the Pacific plate starts, it's kind of a fairly active seismic zone. And when they're having 2 archive machines are just probably a kilometer apart on a fault line. So it's looking to move those somewhere else, get copies elsewhere on the world, so we don't lose this data. If you remember, one of the Apricot keynotes was by Jim Cowie, and part of that is all this research data measuring the routing system for years and years and years, how to archive this and keep copies of it in case of disasters and so on. A lot of tooling has been improved. One of my colleagues, Owen, is a dashboard fanatic, and he's been producing dashboards galore. Some of them will become publicly available to make it more accessible as well. A lot of the collectors were running CentOS. As you know, CentOS is end of life quite a long time ago, so we're getting all those moved over to Ubuntu. For the hardware ones, it's a bit of a pain, because you can't just sort of do an upgrade from one OS to the next one. So we're taking the opportunity to dump the old hardware collectors, get VMs in their place, just running Ubuntu. Why Ubuntu? That was just what we ended up using. It was used quite a lot for other things at NSRC, so that's just what we ended up doing. FRR performance has always been kind of interesting. There was pretty much no tuning happening on the Linux platform we were using. It was just out of the box, off the CD, off the download Linux. But the Energy Sciences Network in the US, ESNet, that link there, they have a lot of suggestions about how to do performance tuning for Linux. Especially now that we're connecting at IXs, the VM, even the physical hardware is connecting at 1 gig or even 10 gig. Whereas Linux out of the box is optimized for, I don't know, not even 100 megabit Ethernet as far as buffers and everything else goes. So even implementing ESNet suggestions has made a huge difference to performance of BGP sessions. Remember, we get a full table v4, which is over 1 million prefixes now, 230,000 or so v6. So trying to load those in on weird buffers in Linux ended up being really slow. So improving that performance was important as well. And we have the other major issue with the badly behaving peers. So slow or noisy peers. I mean, I've got some extra slides here, but you know, the BMP monitoring process that we now have, we're able to really see what's happening. And we have to approach peers saying, why are you sending us 10,000 updates a minute? Oh, we aren't. Well, yes, you are. This is what it says. And they have to go back and look in their own network. Oh, yeah, so we are. We didn't know. So, well, maybe we're going to be a monitoring system for network operators in future. But we're able to look at that and help a lot of peers who have issues with infrastructure that they probably weren't aware of. And because we see it in the route views data. Researchers don't like noisy data because they go, is this real? Is this bogus? What's going on? Is there something wrong with route views? And it's like, well, no, it's exactly what we get from the peers. Also, FRR, there was a huge performance improvement going to FRR 10.51. So obviously the folks developing it have done a lot of back-end tweaks and fixes and so forth. So we noticed a big performance jump, probably converging FRR in half the time that it used to before. So that was good. That really helped us as well. So we're now trying to get all the collectors onto at least 10.51, although 3 is out, and now 10.54 seems to be coming very shortly too. But it just helps improving what we're trying to do. So yeah, noisy peer identification. We've got lots of nice dashboards. This is another of Owen's dashboards, which just lets us be more aware of what's going on. Yeah, so he's built this thing called, well, we've built this thing called Stampede, which uses the Kafka live streaming service. Does minute-by-minute analysis. Again, not all of the collectors. We've taken the busiest ones because they tend to have the noisiest peers, and just looks at things like what the peers are doing, the prefixes, what the AS paths are up to, communities, and so forth. Things that create noise. And it's usually just BGP attribute changes, or even within the provider, it can be a next hop change that results coming through to us as an update for the peer. And it's things like that. This is a particular example of one provider. We had to do do you know you're sending us a mountain of data? And we get in touch with them, they go looking, and it makes a huge amount of difference, as you can see in the graphic here. Future planning, as I mentioned before, more collectors outside North America. We do get still a lot of North American tiny IXs saying, hey, can we have a collector at our IX? And it's like, you've got 10 peers. We're trying to aim for 100 or more in big locations like that, or sort of unique, interesting locations elsewhere. I would rather have a global coverage of IXs than trying to concentrate where there's a high density of operators. So we haven't got one in New Zealand yet, but hopefully in the next 2, 3, 4 weeks, depending on our time. So I've long wanted to get one here because we have in Australia, at IX Australia, and also APNIC in Sydney. But I've long wanted to get one here in New Zealand as well. So hopefully, working with the folks at the New Zealand Internet Exchanges, we can get that happening. So archiving is important. As I said before, Pacific Northwest is not exactly the most stable geologically or anything else. So distributing that around is very important. And also to make it scale, because the amount of data we're getting now, more collectors we add, the more data we have to archive. Disk space isn't cheap, and trying to shovel 50 terabytes around is not straightforward. The peering portal is another project that's underway. At the moment, it's email to help at route views. Hey, can I peer? And we have to then start the whole process of give us this, give us that. Are you in peering DB? And so forth. So we're trying to do like some of the big content providers and others do, have a little web page. It's populated by peering DB when you say who you are, and we can try, not automate it, but at least get the information that we need before we set up peering. You know, going around with requesting money to try and run this, because we're a non-profit, so it takes money to run it. Looking for sponsor supporters, the usual thing. So that's just an ongoing job. You know, both the exchange points that support it, as well as a lot of researchers will support multinational support as well. So that's very important. As for using it, I mean, you know, I could go on and on about how you would use it. As I say, most operators know what they're needing looking glasses, what the BGP table looks like, what the RPKI looks like. Use route views, usually through the Hurricane Electric's tool set now, but a lot of people still logging directly into the collectors that we have. Researchers looking at the data, I mean, that's almost 30 years of data sitting there. Of course, the fashion for all these web crawlers or these AI type of things that seem to want to guzzle all the data immediately, it's also causing a scaling issue as well. But folks are looking for things like, you know, bulgons and ASNs changing paths, and of course with all the recent instability and the desire of wars and cutting countries off and so forth, seeing the changes in the BGP table and who got cut off when and how is always kind of interesting for researchers. What is this showing? Oh, just some examples. This was the Sydney collector. This is at APNIC Sydney. So you can see the sort of mix. You know, some of the peerings are down, others are, you know, local routes, Australian routes, others send us the full table. By and large, we want the full table. And we also talk with the IX route servers as well. So if you have selective peering, it'd be nice to get a full table from you. If you're talking with a route server at any of the IXs we're at, we see you. So, you know, this is one example. I mean, this is from my colleague Nina. You know, her years gone by, she was looking after a lot of the peering for Netflix before she worked at Kentic. So this is an example. You know, you can work out your value of peering going to collectors. She's used AS 2018 in South Africa as an example. So you can look at adjacencies and see who they're connected to. Is it valuable peering with these people or not, or otherwise? So. And it's all done through the looking glass. So these are the sort of examples. This is kind of cool. Barrett Line put this video together, was it last year? No, it would have been the year before, which takes the entire route views data since it's ever started and just showed how the V4 and the V6 internet, actually didn't check that the video is still there, I hope it is. But that's really, really interesting just to watch, taking the entire data set and just run it through this visualization to see how the internet has changed since the route views data started. What else? Okay, for consumers of the data, you know, a lot of commercial entities are using it, so please say where you got the data from. Don't just blame us when people don't like what you're doing. And definitely, I mean, since I've been helping out, a lot of folks who are using our data send consumers of their output to us for technical support. I can't fix what I see in the internet routing table. You know, you can jump onto any of the NOG lists over the last year and look, ooh, is the route views data? It is. It's what we see. It is there. It happened. I cannot delete history. You know, there's some countries where the ISP, by regulation, is not allowed to connect to some other provider, yet the paths appear in the routing table, and we get these panic messages, oh, if my government sees this, they'll shut me down. You shouldn't have done it then, should you? We cannot delete history. It happened. Lots of people have seen it. So, you know, those things. And then the bugs in BGP implementations, that's another classic help that we get. Oh, it shouldn't be doing this. Well, talk to your vendor. So it's kind of interesting. Just when you're providing a service for common good, then people come along and say, oh, blah, blah, blah. Anyway. Peering with route views, selective peering policy, it was open for a long time, but now Nina wants to talk to you first. We need peering DB entry. That seems to be pretty much standard these days. Need a peering DB entry, then we can peer. Of course, if you're at Exchange, talking with a route server, it's fine. but for selective, as in doing bilateral or for doing multi-hop, then peering DB entry is a must. Because the tools we have just use the peering DB. We do peering over V4 just for V4 prefixes, peering over V6 just for V6. I'm not trying to do mixing V4, V6 over the same peering link. Full table, because that's what's interesting to see, what the table looks like from your vantage point. And we don't say, the amount of people who understand what route views is, and then say, ooh, you're not announcing any prefixes. It's like, we don't have anything to announce. We simply collect what we see. It's the usual story. So peering coordination, I think anybody who's a peering coordinator for your own operator will probably have the same requirements that we have. We get quite a few hobby networks coming along, say, hey, I run a router in my house. Do you want a full BGP table? Well, no, not really, because we already get it from your upstream provider. So, must be more proper network operator, whether it's enterprise, commercial, academic, government, who knows. What else? And remember, whatever you send us, we see. So for exchange point, multi-hop, so exchange point, that's really the primary goal. There are quite a few people who are not at exchange point, the usual restrictive peering policy people, or locations we're simply not at. And so for those, we have multi-hop peering, which goes back to University of Oregon. And so we've got how many collectors? I think 8 collectors now that are doing multi-hop peering. We have about 40, 50 peers in each one, which is about the limit of FRR, being able to handle full feeds, dual stack. Anyway, why selective? Just so we can talk to you. I think that's usually what selective peering means. We want to talk to a human being rather than just what the route server gives us. And I added the hosting thing in here. As I say, we're going to get one in New Zealand happening real soon. Generally, the hosts are the IX operators themselves or one of the members of the IX who give us a bit of space on one of their server infrastructure. Transit is minimal. It's like 10 megabits per second just for the MRT dumps to be synced back to the archive. We don't really like physical hardware. It's very much virtual machine. Some countries, we cannot do virtual machines because of whatever security, regular operational requirements. So we have to ship the physical hardware. But most places, it's a VM these days. And there's not really much spec compared with anything else these days. So 2404, we're using FRR. Have considered quite a few others, but FRR is a good fit for what we are trying to do at the moment. It may change in the future once we get better or more scalable routing daemon. And collector hosts, we list them all on the website because without the collector host supporting us, it ends up being pretty tough. What else? Started in 1995, as I was saying. So if anybody who's writing papers or doing things because of it, there is actually this DOI, which I think is a US thing for listing publications. It's kind of helpful because supporters, big supporters always want to see, well, who's using it and what the references are and so forth. And that's pretty much all I have. Thank you. Any questions? If not, I can run away. Good, I can run away.
Just a question from me. Other than the challenges that you had, do you have other users that try to abuse the system?
The heaviest one is the telnet access, and so that's very heavily rate limited now. So for the average person who's just sitting at a command prompt, telnet to the collector, doing something is generally fine. Show IP BGP or show BGP on anything these days, even on the ASR 1004, that really hurts. But turning off show BGP, I would like to do that. I hope we can get to there soon once the looking glass is happening. At the moment, we're trying to push all these automated scripts onto the looking glass, but then we've also got to be mindful of the looking glass, so we rate limit the looking glass as well, because some of the automation is just hammering away at what the looking glass is doing. The archive is interesting. There are 2 archive nodes, and they're listed on the website, but everybody just goes to the original archive, so that's hammered pretty badly. So we're trying to find other ways of distributing, so, via other archiving entities, so that the data set can be distributed around a lot more. So that's really the other big issue. But otherwise, from a collector itself, it's not like people are trying to hammer on any of the collectors across exchanges or even on the transit link. I mean, obviously it's all protected, but no other major abuse. It's really just the archive and that telnet access. That's the headache.
Any other question? Other than that, there are students in the room, so for those that want to do research on BGP, we would love to see a lot more in our region. I guess most of it is in other regions, but yeah, it'd be good to see some of the universities here in New Zealand taking advantage of the data that they have collected and used it for research purpose.
Yeah.
Thank you.
Okay,
Philip.
thanks.
Right, our final speaker for this afternoon before a tea break is Dave Phelan. He is a senior network analyst at APNIC and a technical trainer at APNIC. He will be presenting on IPv6 landscape in NZ, and I'll let him talk more about it. Thanks, Dave.
Good afternoon, everybody. I'm between you and coffee, so let's get this done. So this is me. I was a network engineer for a long time. Now I do policy and a little bit of training, and I still like my cat memes. So we're looking at V6. So 2023, when I was in Rotorua and horribly hungover on a stage, I talked about what was happening. And at that point in time, things were coming along nicely. So is it better? Yes and no. So I could just leave it here and I'm out, but yeah. So let's look at what's happened in the world. So I've been talking about V6 pretty much since I started at APNIC, and I sort of kept point in time reference of what was happening. And so back in 2020, we were sitting around 23-ish% global adoption, up till 3 days ago, 41.1. So it's been a reasonable trend upwards, which is nice to see. So if I break that down into what I like to call the 40% club, so these are economies that are over 40% IPv6 preferred, not capable. Back in 2022, there was only 26, 8 were from the APAC region. March, when I presented it in Rotorua, there was 30 over 40, but 8 from APAC. And when I look this time round, it's 46 with 16 from APAC. A couple of stars there. We'll get to them in a second. So zoom in into Oceania. Aside from Australia and New Zealand, we've got 24 separate economies. Lots of them are very, very small. Niue, population of 1,500. Tokelau, 1,800. It's lots of tiny little places. They're geographically dispersed. A lot of them haven't got great fibre connectivity. A lot of it's satellite. A lot of it, up until fairly recently, was geosync. So nice, wonderful round trip times. But there's also limited competition. So you might only have one ISP/mobile phone carrier in these places. So back in March 2023, this is the exact slide. The Oceania sub-region was sitting around 33-34% preferred, capable, which was up from 22% back in 2020. AU was at the top. NZ had dropped off a little bit for some reason. French Polynesia and PNG were the up-and-comers. The rest of the region at that point in time was a 2% combined if I added everything up. If I look now, yes, we've bumped up a bit. The map's a slightly different colour. So green is good, red is bad. So if you look at the global map that Jeff publishes, it's varying phases of colour. But once you zoom into the sub-regions, it's relative to that region. So Australia being bright green on that map does not mean that we're 100%, we're just better than everybody else. So we've faded off a bit. And the top 4 are Niue, Tuvalu, Kiribati and Nauru, all with stars next to them. Why the stars? Well, Starlink, of course. So when I look at these numbers, every bit of this V6 is Starlink. Niue, 1,500 population, and they're 80% IPv6 capable. But what's important is context. When we look at the data in a slightly different subset, we look at the number of samples we're taking off of these places. If you actually physically go and look at stats, IPv6 stats from APNIC right now, Niue is sitting at 0 because somebody turned their Starlink dish off, probably because they haven't got the diesel to run the generator this week. So it's not there today, but it was there last week. So there's not a lot of samples there. The way the weighted samples work is because Jeff throws a ton of ads out there on behalf of Google. We use I think it's the World Bank Internet User stats that are updated every year, and we work out a weighting. So if we're oversampling, like in Kiribati, at 25k samples for a 15,000 population, it's not quite right. So we're oversampling the population, so we cut that down by about a fifth to give us a weighted average on what the actual internet user numbers are. Have I got that right, Jeff? Yes. Thank you. Whew. So I thought, okay, I then sent Jeff an email and said, can we put in a no Elon button so I can filter out all this Starlink? And he said no. So I went, okay, let's take a normal number. Let's say if I look for weighted samples of anything over, say, 20,000, that should give me a decent number. So that's what I wound up with. So Australia, Fiji, New Zealand, and PNG. These are all pretty legit numbers. I manually checked it as well, just to make sure I was only sort of grabbing the Starlink out of those numbers, and I'm pretty sure I'm there. So what about New Zealand? So I'm going to take you on a little bit of a history run. Who was in the industry in 2009? Yeah, fair chunk of you. How many of you heard about the New Zealand IPv6 Task Force? I know you did, I've seen your names on it. Right. So, the IPv6 New Zealand Task Force started out as an IPv6 steering group. And its whole aim was to get adoption happening, do education, raise awareness. I found this site completely by accident. I didn't know it existed until a month ago. So I also found the minutes from the 2012 meeting, which is the only one that was published, and even then they were talking about the task force's future. Was it meeting its objectives? Do we need to shut this thing down, shut it down? So I thought, okay, who's on here that I can ping? Dean Pemberton. So I've sent Dean a message and said, hey, can we have a chat about this V6 task force thing? And so we had a Zoom call last week, or a Teams call last week, and I said, okay, what happened? So 2015, it all stopped. I said, the job wasn't done. He said, no. He said, we sort of hit a wall. He said, we worked out that people weren't as passionate about V6 as we were. There was some, what's the word? Operational realities that they hadn't thought of, business realities. But they said, basically, we've done what we said we were going to do. They were around for the World IPv6 launch day. They wrote multiple papers, but in the end, it was time to wind it up. So the website still exists. You can still go there today. So if we look at, this is a graph of that time. Now, we only have stats going back to 2013 because that's when we started recording it. Top orange line is the world, and the bottom line is New Zealand. So it was still, I mean, even the world back then was sub 10%. We weren't even double digits. Somebody did try something for about a month there and then turned it off again. Seems to be the case. Something goes wrong, turn V6 off. So some of the interesting finds, there were 41 task force members when it started. It was a mixture of vendors, government, ISP, telcos, enterprise. 25 New Zealand registered domain names. Thought, okay, let's see who's still kicking around. 2 are completely gone. They were consultancies, so not unusual. 5 still have A records. Domains are registered, but they don't go anywhere. There's no end host. Nathan Ward, Brain Trust. 8 have quad A records, which go to end sites, which is fantastic. Still exist. 1 has a quad A, but when you go to the redirect, there's only an A record in New Zealand. And the other 9 don't actually have any quad A at all. So even at a DNS layer and in Cloudflare and the Amazon portals they're using, they're not pressing the checkbox to just enable IPv6 on their front ends. At least do that, people. Come on. And the last post was from Lindsay Hill, now at Steam. He had actually put together a list or a Google Doc of all of the IPv6 enabled ISPs in New Zealand at that time, in January. That Google Doc is still there. So you can go and have a look at it and see what's changed. So let's jump up. So what happened after the task force? Well, New Zealand capable was sitting pretty good. If you have a look, it was actually tracking fairly well with what the rest of the world was doing. But then sometime around 2022, something happened. Everybody just stopped doing V6. Now, we can't blame COVID because we were out of COVID mostly by 2022. Go figure. New Zealand gained 2.9% in that time. The rest of the world stormed ahead at about another 14%. So New Zealand has now stopped tracking in line with global adoption. But this is not everything. So this is our view of capability from 2020. As I said, it's sort of stagnated. Back in 2020, it was 25%. We're sort of sitting just under 30, depending on what day of the week you look. But it's not just us seeing this. Now, our stats are all ad-driven. We send out Google ads. If you're filtering your Google ads, we don't get your data. So let's talk to the content providers. How much traffic are you pulling off them with V6? So Google say roughly 21%. Cisco are grabbing some stats from somewhere, but they're saying around 21%. Cams was up here yesterday. He's saying around the same. And Cloudflare are generous, and they're saying you're doing about 25. So our numbers are all pretty much in line, so it's not necessarily a sampling bias or anything like that. So that takes me into the 4 stages of IPv6 grief. The first is denial. We still have CGNAT, everything's fine. Second stage is anger. Why is this router doing this? Bargaining. Maybe 464XLAT will be our saviour. And then finally, the 4th stage of grief is acceptance. Fine, I'll configure DHCP v6, done. Many of you are up here. I still have CGNAT, or I still have Ample v4, I don't care. Some of you are like this. Does anybody remember this graph from 2023? It's still doing the same thing, and this is a CPE problem. Why is this router doing this? I think they've worked out now why they know why it's doing it. So, thank you, Netcom, the gift that keeps giving. So, where are we now? So back to this pretty graph. This is your capability. I go and overlay the preferred. Now, you'll notice a couple of little things here. This thing here is not your problem. This was a Jeff measurement problem in March 2025. Preferred numbers weren't working for some reason. He will know, I don't. From this point on, it's now your problem. Now, why am I saying this is your problem? Who hasn't heard of happy eyeballs? Few people? Okay. So I'll give you a little bit of a rundown on happy eyeballs. So happy eyeballs lives client-side. Your web browsers, your operating systems, your software stacks. It will basically try and use the best protocol if you have got a dual stack device. So there's two RFCs currently covering happy eyeballs, but this is pretty much how it works. You have your dual stack client, and with the older RFC of happy eyeballs back in 2012, it would give IPv6 a head start. It'd say, you start first, and you go and do your DNS queries. Then it would wait between 30 to 200-ish milliseconds and then start the V4. So it's giving V6 a sufficient head start to try and be the winning protocol. So once we're there, we're now racing in parallel. Then whoever wins gets the data. So if V4 gets there first, even with the head start, then V6 just gives up. So happy eyeballs will choose the fastest path, not the newest protocol. So between V1 and V2, a few things were changed. So with V1, DNS resolution happened first, IPv6 was given its head start, and then V4 would start. So if there was any latency in V6, it would disadvantage IPv6. Version 2, the DNS and the connections are combined, and the A and the quad A is actually run in parallel. So as soon as we get an address arrive, then we start doing the connections. So there's less of a bias if the quad A is slightly slower. V3 is currently in draft at IETF, so if you'd like to go and get some bedtime reading in, you can track those through. So I've said it's your problem. Because, happy eyeballs, it's a client-side thing. How's that my problem? Well, remember what I said before. DNS and connection times. They're your problem, not the client. So I've done some measurements. I'd like to thank everybody who is running a RIPE Atlas probe in New Zealand. It is dual stacked, all 50 of you, and there are exactly 50. I'd like some more. There are lots that have been still turned off, probably sitting in boxes in drawers. If you'd like to go and plug them in, please, Nathan, that'd be great, so I can get some more views. So I did a DNS query from my 50 dual stack probes in NZ. I picked a specific A record that I wanted to look at and a quad A, because I'm going to be using that for further measurements. And this was what things looked like. Now, the horizontal line of this scatter is the V4 response time. The vertical is the V6 response time. Anything running up that median line or close to the median line means that things should generally work. But the problem you're going to have, which is this one, once we start getting this major divergence here between our V4 and V6 times, is where we start breaking happy eyeballs. Not great. So pretty much anything above that line is in the happy eyeballs risk zone. V4 is going to complete first, which means V6 hasn't got a chance. So next step is obviously to look at some ping responses. So again, I use the exact same 50 probes, and I picked 2 sites in Singapore. Why Singapore? Because that's where our measurements come from. So let's look at where we're measuring from. So I picked a government site, and I picked a government site specifically because Singapore has data sovereignty laws, and because it's CDN, it has to still be in Singapore. It might just be different nodes within Singapore. And I took a direct host, which is one of my jump hosts sitting in Singapore. It doesn't go anywhere. It's got a single V4 and V6 static IP. So I ran these pings. Now again, anything up the center line or under is okay, and anything on or about this red line, not so good. If we can't get the initial connection done, then again, what chance has V6 got? And this was the measurement to my host, and as you can see, it's very, very concentrated. It's a static single host, so things generally should be about the same. So the next thing to have a look at was, okay, well, we definitely have some latency problems on some of these links. These guys here, they took a holiday. They took a very RFC 7511 compliant route of getting to Singapore. If you need to, just go and look up RFC 7511. So I thought, okay, well, let's look at the hops. Now, hops don't necessarily mean that I'm taking a different path. It just could mean that there's other things within my network that I'm traversing through. So pings are generally okay. But it can give you an indication of other things that are happening. So the scatter plot for this one's a little bit strange until you look at this. And these are the same ASN. Now, there's obviously some MPLS happening here. Some of their V6 traffic is being 6PE'd, but some of it isn't. Now, I can only assume, because I don't necessarily know the inner workings of everybody's networks, but it's probably through a acquisition and they haven't quite finished merging all parts of the network yet, or they just went, you know what, we're just not going to bother, things are working. It could be one of those two things. But the thing is, when I did it to my host, I saw similar things. So different subnets, different everything else. So happy eyeballs needs consistency. So my V4 and V6 paths and times should all be similar. I've got to give V6 the best possible chance. DNS response times need to be similar. I can't have something that's wildly different and expect V6 to keep working and doing its thing. So what's happened? Well, we can't always control DNS. End users are going to end user. They're going to go and put quad 1, quad 8, quad 9 in their DNS because they think it's better, rather than using their ISP's own DNS. Operators can control within reason the routing. And when I say within reason, you can use BGP communities to signal to your upstreams, to not announce to places, or even just the choice of operators. But you should have consistent routing advertisements. Your V4 and your V6 paths should look very much the same. Choice of upstreams. Now, I'd like to find out from people in the room at some other point, but based on what I can see, a lot of the traffic is either domestic or Australia. Not too much of it needs to travel around the world, but some operators have better paths than others. Some have better further connections than others. So what's changed? So if I have a look back in 2023, this was the top 10, but I've decided I'm going to do the difference between capable and preferred, because this is where things have gone wrong. 2 degrees have been fairly consistent at about 5% based on that. Anything within about 3 to 4% is generally okay for an operator that we see. But you'll notice the volley down the bottom, 0.63% difference between capable and preferred. Now remember that number, because we can't even break 5% anymore. The top 10, we've got a 55% difference on one. Then Sky, who are actually quite good, are now at around 30%. Something's changed. So, without naming names, I start looking back the other way. So let's check the return traffic. So for things generally from Singapore, you're sort of in that sort of 120 to 130 milliseconds for a reasonable ping. These V4 and V6 are not taking the same path. I managed to find one probe sitting behind someone who's via a well-connected AS in New Zealand, and I was able to talk to the V4 and the V6 directly on that probe, so I could bounce straight in. Again, the V6 path was going strange places. These guys here went Singapore, Japan, Palo Alto, Auckland. Not exactly the fastest path. The upstream choice for this particular one is why I looked at both sides of the fence. They're winding up on a peering link in Australia that is now bouncing them into what I would like to call an undesirable network who doesn't treat V6 well, and the traffic's not going the most direct route. So, how can I fix this? Things in your control. Start monitoring things. Go and set up a RIPE Atlas account or an NZNOG ring account. Go and put some anchors and probes in your own network so you can measure inside and out, earn some credits, run consistent tests, see if things change. Check your announcements. Are you doing things uniformly? Is your V4 and V6 being announced in the same way? You remember last time, for those that were here, I highlighted the USP case in Fiji where ARNet accidentally set the local preference for Hurricane higher than their own route. Oops. And traffic for V6 for USP went via the US before it went anywhere else. Be cautious with who you peer with. No export communities exist for a reason. And cheap transit is cheap for a reason. Recursive DNS servers. If you are doing them and you are doing V6, stick a V6 address on them, please. Just help speed things along. So, stop buying more V4. You're feeding the denial phase of IPv6 grief. Since 2020, and this is a rough estimate, New Zealand networks have spent about $3.8 million US from out-of-region transfers. Domestically, there's been about 500k IP addresses traded within NZ amongst yourselves. Stick this money into fixing other problems, whether it be staff training, whether it be enterprise education. Jen Linkova did a fantastic closing keynote at Apricot this year on IPv6 in the enterprise. I recommend you go and have a look at it. So, 545 entities that I see in NZ with resources, 200 still have not even asked APNIC for an IPv6 delegation. Mostly they're enterprises and government. Out of the remaining 240, you're less than 1% capable. So you've turned it on somewhere, but you're just not doing anything with it. I can't tell you what to do. I can just tell you what I see. So if I see it, the rest of the world is seeing it, and I'm only telling you what's public information. So help yourselves before a major content provider decides that they're done with IPv4 and you're left out in the cold. That's all I have for you. Any questions? John.
Dave, what was the period that you did these measurements over?
Which one's my ping and traces?
Yeah.
They were all done within a 2-week period in March.
In March, yeah. Okay. And was Indigo West fixed then or not?
Yes.
Oh, interesting.
And that's how I know it was working. Because I saw the hops.
Excellent. Thank you.
If you're entering Perth, you're generally coming in Indigo West. Warren.
This is more of a practical one. You said about going and creating a RIPE account.
Yep.
What happens if you've got no credits?
If you need credits, come and see me. I've got about 18 billion credits I can loan people. I think they give you 100,000 to start with anyway, so...
Yeah, that was the other thing, is if you do need credits, I can give you a voucher code that gives you 500,000 or something.
But yeah, if you don't have a RIPE account, come and see me. I can go and set one up and I'll give you a couple 100,000 credits. Like I said, I earn about 3 or 4 million a day, so... I can't spend them faster than I earn them.
I was just going to add, you need more probes in New Zealand? Because I'm one of those 50, and my house has been having fibre issues for the last 3 weeks, which will have impacted your results.
Come and talk to me. I want to get your probe ID.
And I've got 190 million credits if anyone needs some.
Yep. And that's the other benefit. You earn credits by letting people like me do measurements, and you can use them for your own use as well. So they're useful tools. Nathan.
So the happy eyeballs thing,
Yep.
you were talking about DNS servers with V4 and V6.
Yes.
That's where it's using, UDP or whatever TCP over V4 or V6 transport.
Yep.
But happy eyeballs is more interested in the
Time.
quad A records, right?
Happy Eyeballs is interested in A and Quad A.
Yeah.
It's more so that you've got the option if you are, look, the way I would put this is start thinking towards a V6 only world now before it's a problem.
For sure.
Yeah.
Yeah, but I think you use the V4 and V6 transport as part of your data when I don't think that was relevant.
I don't think I did.
Well, maybe we could have a look at it after.
I'll double check it, but I'm pretty sure I used V4 where it was possible, V6 where it was possible, then fall back to V4 if there was no V6.
Yeah. Okay. Well,
So,
let's
yeah.
have a look after. Yeah. Sweet.
Cool.
So, kind of convoluted question. I keep asking this every time I hear a DNS talk. What are we doing to deal with the increasing use of in-app DNS entries over not just DNS over HTTP, but just random? We're going to point the DNS to our internal servers on our cloud server somewhere over some sort of JSON API, so we will direct your traffic where we want because you've done it from an app. What are we doing with that? Do you have any solution?
Ask the guy behind you. Look, Jeff's been yelling about this for years. This is not new. This is not a new problem, and it's getting worse. As Jeff says, the app vendors are going to take you where the app vendors want to take you. You have no choice on that.
Thanks, Dave. Over here.
Oh, yep, Tim.
Great data, great talk. You mentioned the difference in latency response for V4 and V6. Did you notice if they were the same resolvers based on path or any other correlations? And if so, what might cause that difference? Because I doubt there are people running V4 resolvers and V6 resolvers to be the same box.
I didn't check the IDs to see if they were the same box. Very few actually did have a V6 resolver. The bulk of them were V4.
Yep.
But I mean, it only adds a teensy bit, but that teensy bit can make a difference when you're borderline.
And why would the quad records be taking longer to look up than the A records?
So some of those quad A records that took longer, the V4 it was using, say, they might have had, like a couple of them I did find had like their own recursive server at home.
Right.
So I could see it was in the same subnet. But then obviously the recursive resolver hasn't got a cache for it, or it's got to go further for the V6 record. It just seemed to be longer.
Right.
The host record I used was that Gov Singapore one because I was going to use that for further measurements anyway, and I wanted to try and at least get it cached to see what was going to happen after that.
Yeah, okay. Because I'd sort of expect consistent behaviour from quad 1s, quad 8, quad 9s, whatever. Yeah.
You'd think so.
I'd hope so.
That's it. Excellent.
Right, thanks, Dave.
Thanks, everyone.
Right, so that's the end of the session. We're now on tea break. So just a few announcements for this afternoon. Jets X 5 p.m. So there's a taxi that has been booked and will take you from the conference at 4:30. There's another taxi booked for those that are leaving for the 7 p.m. session. So that will leave here at 6:40. For those that are doing the tramway, you can walk to the junction and check in with the team there 15 minutes before your scheduled booking time. Other than that, so we have tea break and final session this afternoon. Thank you. 2/3. So 3.
Okay. Only the hardened few remain. One last push and we've done it. Okay, so the final session, we are starting with Pierre from DataGrid, and he's going to talk about things in the Deep South and what that means for the industry.
Good afternoon, everyone. Thank you very much for staying here. It has been 2 long days. So today I will talk about DataGrid, what we are doing, and I will try to explain what will be the implication for the networks in New Zealand, basically. So first of all, my name is Pierre Guaffon. I'm head of connectivity for DataGrid, and my role is to ensure that we provide the right level of connectivity into the data center we are building in Invercargill. So before we start, I would like to give you an overview of why Invercargill and explain what is the opportunity for the South Island of New Zealand to host large data centers. AI. What a surprise. We talk about AI. It's a revolution, really, in terms of how we use, we work on a day-to-day basis. And it drives more and more requirement for the data center, for the connectivity as well. It impacts not only the IT, but everyone working in enterprise start to use AI to work on contracts, to do pretty much everything. So the requirements are increasing, and the network and the data centers are evolving to be able to cope with the demand. What it means is data centers are changing. What used to be a traditional data center, when a hyperscaler decided to build a data center, they typically try to build a data center as close as possible from users. So if we look at New Zealand, Auckland has been an obvious place where all the hyperscalers have decided to install their capacity. You know, the market, you have Sydney, you have Melbourne. That's how the location of data center was driven by the population that was served by those data centers. Now, it worked pretty well when the size of those data centers were still reasonable. Bringing tens of megawatts into a city is quite easy. Now, with AI, the requirements are totally different. We are not talking about tens of megawatts, we're talking about hundreds of megawatts, gigawatts data center. That becomes a challenge. So there is a change in the way we select site for data centers, and we try now to get close from the power, because this is a bottleneck. Where can I get enough power? Where can I get a site with enough power to be able to host large data center? So that's a big shift, and that's an opportunity for the South Island of New Zealand, because they have there is lots of benefits that can be used for that kind of infrastructure, and I will explain. Southland, why it makes sense to have a large data center developed in Southland? Power, that's the first requirement. We have in the South Island of New Zealand a lot of power. Most of it is green. 90%, more than 90% is renewable, mainly from hydro. But there are also a lot of projects being developed at the moment for wind farms and solar as well. So there is an existing base that is already quite large, but also a huge potential for growth in the amount of power that we can generate out of the South Island. So that's the first point. The second point is the climate. The cool temperature of the South Island Invercargill, I put 9.8 degrees here, which is the average temperature that we have in Invercargill. It's perfect. It's perfect for a data center. It means we'll be able to leverage the outside air, the cool environment, to cool the servers, and that will bring efficiencies. To give you an idea, we target for our data center a PUE, power usage effectiveness of 1.1 or below that, which is very low. And to put things in perspective, a typical data center in more warmer climates, Auckland, Sydney, Melbourne, will be more around 1.3, 1.4. So that's 25-30% more efficient, and it means 25 to 30% less expensive to run the same IT capacity. Water availability, so that's interesting. There is obviously in South Island a lot of water, a lot of rain that we can leverage, that we can harvest and use for the data center. The reality is that's an advantage. We don't see that as critical because of the first point, the cool climate. The requirement, the need for mechanical cooling will be quite limited. So yes, water is an advantage. However, that will be an advantage only during a very limited period of time during the year, during those warmer periods during summer. And we anticipate less than 10% of the time we might use a little bit of water. The rest of the time will just be free cooling, indirect free cooling, so using the outside air to cool the data center. Then the two other points are also extremely important. If we try to attract international players into New Zealand, the geopolitical stability is extremely important, as well as the ethical transparency. So we want to make sure that potential customers want to make sure that we have an issue here. Oh, okay. The screen I have here is not correct. So, sorry about that. So yeah, having a stable country is important to attract the kind of the customers we are targeting. Finally, education system, we have obviously, it's a strength of New Zealand, and we have everything in place to make sure that we have the right workforce to work on the data center. So based on all this, this is what we are developing. You can see here the high-level design of the site that we are developing in Invercargill. In Makarewa exactly, so it's just a little bit north of Invercargill. So that would be a campus developed on 50 hectares of site. We have just, you probably heard that, received the resource consent a couple of weeks ago for that specific design. The campus will be made of 3 main components. The first one would be a substation. The site has been selected because it's ideally positioned between the biggest hydropower plant in New Zealand, Manapuri, and the largest electricity user, which is Tiwai Point Aluminium Smelter. And we are right in the middle. So we have 4 high voltage lines, 220 kV, owned by Transpower. And we will tap into those lines to create a substation and have access to the national grid. So of course we will have access to Manapuri, but we have access to the grid, so we will have access to any generation that is connected to the grid. So that's the first element. That substation will be able to provide around 300 megawatt power. On the top of the site, you will see the buildings. So we plan to develop the site in 6 modules of around 50 megawatts, designed for AI requirements, so very large rack densities will be supported with liquid cooling. And finally, the site would also include a cable landing station. So I will explain a little bit after that. Because we will have a submarine cable landing into the site. Now, let's talk about connectivity. What do we need? What do we need to provide to that data center? First of all, we need to ensure that we have access to international connectivity. We are targeting international players, so having access to international connectivity is a key requirement. privacy is a minimum. So we need to have multiple options in terms of connectivity to have access to that international connectivity. Finally, in terms of capacity, we're talking about large amount of capacity at the spectrum or fiber pair level. That's very large capacity requirement that we expect. Now, I will focus on the international connectivity and how we will address that requirement. So the requirement for us and for our customer is to have 3 diverse international routes at the spectrum or fiber pair level. Okay? This is what we have today. That's a representation of the connectivity that we have into New Zealand today. So we have basically 4 submarine cables connecting New Zealand. Some of them are a little bit older than others. And if I describe them from the older one, we have Southern Cross, obviously, which is the historic cable that has been connecting New Zealand from 2000. That's a 3 fiber pair system that is connecting on one side Sydney and on the other side the US. Okay. 2000 means that cable is more than 25 years old, and my understanding is it will probably retire in the next couple of years. Then you have TGA, which is a more recent cable, Trans-Tasman cable connecting Sydney and Raglan, yes. That's a 2 fiber pair cable, yeah, so that's 2 fiber pair cable. And then you have Hawaii. That cable has been in service since 2018 and provides connectivity between, on one side, Australia, Sydney, with 1 fiber pair, and on the other side, Hawaii and Oregon with 1 fiber pair as well. And finally, the last one is Southern Cross Next, deployed in 2022. Again, similar configuration, Australia to the US with a branch to New Zealand. And here we have 2 fiber pair on each side. So what we can see here is everything is connected to Auckland, and our requirement is in Invercargill. So we will have a gap to fill here. What we can say as well is all those cables, even if we have a little bit of diversity, they are all coming to Auckland, and we have cables that are relatively skinny. Couple of fiber pairs at the maximum. If you compare that with what is being deployed in the world today, it's a minimum of 12 to 24 fiber pairs. So those cables are quite small compared to international standards and compared to what is used by the hyperscalers in other markets. I have to mention as well that cable, which is not available today, but will be available by the end of the year, at least is my understanding. It's a Google cable, Honomoana, landing in Orewa. Similar configuration as Southern Cross Next and Hawaii. That's a trans-Pacific cable connecting Sydney and Melbourne on one side to French Polynesia and the US, with a branch to New Zealand. That branch technically is a 16 fiber pair cable. However, my understanding is the real amount of fiber pair that would be usable from New Zealand would be much less than that. So how do we address the gap, and how do we provide the right level of connectivity to the South Island? That is what we will build as part of the project. So the submarine cable is required for the submarine cable. Sorry, the submarine cable is required for the data center, and as part of the project, we will build the Tasmanian network that you see here. So that's a ring, effectively, and if we start from Invercargill, that will be a first route from Invercargill to Melbourne and Sydney. Melbourne is important for us because, and I will explain later a bit more, but it's a growing market for data center, and it's also a great gateway to the rest of the world in terms of connectivity. On the way, we have an opportunity to connect Tasmania, Hobart. Hobart has similar advantages as the South Island of New Zealand, with a lot of renewable energy, cool climate as well, and they have a similar challenge with the connectivity, so that's something that we can address with that branch to Hobart. Then from Sydney to Auckland, we have that direct route that we propose to build, and then we have a domestic connectivity from Auckland to New Plymouth and Greymouth. Now, if we come back to that map, this is what that will provide. So the first route in the south is extremely important for us because it provides that direct international connectivity into the site. It will have many advantages. The first one is to increase the resilience of international connectivity in New Zealand. Again, you see that a concentration of submarine cables in Auckland that will provide that diversity. To give you an example, in Australia, for example, if you look at 5-10 years ago, Sydney was the only place where submarine cables were landing on the east coast, and now it has evolved, diversified to multiple landing points: Brisbane, Melbourne, Adelaide. The same has happened in the UK, with historically Bude was the only interconnection place between the UK and the US. Now you have many different locations to land submarine cables. So I think the same needs to happen in New Zealand as well. We cannot rely only on one region to provide 100% of the connectivity to New Zealand. We will have an impact for the South Island in terms of latency, of course. Today, all the traffic from the South Island is going to Auckland before going anywhere else. So there will be a significant impact. Of course, the closer from Invercargill, the better. The average improvement that we'll see from Invercargill will be 50% reduction in latency, which is significant. And then with that landing site in Invercargill, we really create a platform to welcome future submarine cables as well. And Invercargill could become a hub that will welcome multiple submarine cables, diverse from Auckland. There have been talks about a cable connecting Invercargill to Antarctica. That's a project pushed by the National Science Foundation in the US. And they have identified Invercargill as the right location to land that cable. So we will see if that happens. There have been talks as well to build cables from Invercargill to South America, Chile. So that's also some possibilities. It's not part of the project, but I'm just saying that's an option. Then, so that's for the South Island. For the North Island, the requirement here is really to bring more capacity. More capacity directly into Australia. As I mentioned, the number of fiber pairs is quite limited, and considering the requirements, the growing requirements of AI, we need to bring a large amount of fiber pairs into the North Island, into Auckland, because that is still the main data center market in New Zealand. So here, the Tasman Ring network will provide connectivity to Sydney and Melbourne with at least 12 fiber pairs. I can mention as well that there is another project, Tasman Express, which share the same vision than us on that, because that's pretty much the same route from Auckland to Sydney as well. So there is a need for that cable, whether it's Tasman Ring or Southern Cross, but there is a requirement for that. Now, if we take a step back and look at the map of the world, this is what's happening. We have what we call the Great Southern Route. Historically, the US has been communicating with Asia and the rest of the world using that direct Trans-Pacific route to Japan and then the South China Sea, which is more and more challenging because it's more and more challenging to maintain cable going in that area. So more and more players, hyperscalers, are looking at safer routes, and one that is emerging is the route south of Australia. If you look at all the cables being built and announced by Google, you can see exactly the map that you're seeing here. they are executing on that vision of the Great Southern Route. So today, that's mainly to connect Australia. So you have cables connecting Australia to the US. You have cable south of Australia with a SMAP and the Google cable being built at the moment. And from Perth, you have access to multiple cables, or you will have access to multiple cables connecting Perth to India, Thailand, Middle East, and South Africa. So by creating that Tasman Ring network, we put New Zealand on the map, and we include New Zealand in that Great Southern Route. And we can benefit from the connectivity and from the access to all those cables. New Zealand and Australia used, if you look at like 5-10 years ago, New Zealand and Australia as well were pretty much the end of the world in terms of connectivity. Those cables were connecting Australia with the US were only to serve Australia and New Zealand a little bit. Now they are really part of a greater ecosystem that allows communication from the US up to Asia, Middle East, and Africa. Now, let's talk about the domestic connectivity. So what we have described here gives us a route from Invercargill to connect to Australia, but we will need domestic connectivity to connect to the cables in Auckland. The requirement here is quite simple. We need a domestic fiber network to support 3 to 4 diverse international routes at spectrum level. When I say 3 to 4, I include the submarine cable that we just discussed previously. So this is an overview of New Zealand today, very high level, just from a user perspective, that's pretty much what we can get out of Invercargill. So if we start from Invercargill, we have basically 2 terrestrial routes, 2.5. 2 routes out of Invercargill. Either you go east to Dunedin, Christchurch, or you go west to Queenstown. Queenstown, you have 2 options. Either you go to the west coast, or you stay pretty much in the middle of the South Island. And when you reach the top of the South Island, you have 3 crossings available. You have Aqualink, you have Transpower cable, and you have the Spark cable. So you have 3 different options to cross today. And then you go up in the South Island, you can pretty much get 3 routes, and you arrive to Auckland. Auckland is a challenge as well because of the geography, and today it's quite difficult to have more than 2 routes, totally diverse. So the good news is it kind of works. With that infrastructure that we have, we can provide 2 fully diverse routes at the fiber pair level from Invercargill to Auckland. Now, can we improve it? Probably yes. There are options to improve it. The options are this one. So that's part of the Tasman Ring network that we propose. That's connectivity from Auckland, Muriwai, to New Plymouth, Greymouth. And that cable provides 2 main benefits. The first one is it provides diversity for the crossing between the North Island and the South Island. That is really much required. We do have multiple cables, but at the end of the day, they are quite close from each other, and they are all very close from the Wellington Fault. That route here proposed is further away on the western side of New Zealand and away from that specific risk. What it helps addressing as well is the diversity into Auckland. As I mentioned, Auckland, the geography of Auckland is quite challenging to bring 3 diverse routes into Auckland from the south. Having a route that is coming to Muriwai definitely helps to have 3 fully diverse routes from the South Island to the North Island. Another way to improve is, I think there will be a need at some point to upgrade the existing cables. Of course, we do have fibers in the ground, but those fibers, we all know, have been deployed quite some time ago. Before AI was even a thing, to connect the population of the South Island, which is now, and the requirements are now a little bit different. So I think there is some room to improve and overlay some fiber builds here. And finally, we could create a third terrestrial route as well. That is, and that wouldn't be too difficult, I believe. That will require some fiber builds, but that's definitely an option that we should look at. Now, I will finish with that slide to put things in perspective and how I see the future of New Zealand connectivity between the South Island and North Island. So the first thing is the Tasman Ring network landing in Invercargill will unlock the potential of the South Island. If today we don't have any large data centers there, it's mainly because the connectivity is not ready for that. If we bring the submarine cable to Invercargill, we will unlock that potential, and other data centers will come. I'm convinced about that. It's a perfect location. If you fix the connectivity, more large data centers will come. So the requirement will come from us, obviously, but from others. Other data centers will be in the South Island. The other thing is the routes Invercargill, Melbourne, Sydney will become a must-have in any network. That's what I believe. If you have your customers wanting some diversity, they will want you to be on the cable in connecting the South Island in any way. Telcos will want to be there. Hyperscalers will want capacity on it as well for the exact same reason, even if they don't have any interest in the data center. So that's not linked with the data center. Just from a diversity standpoint, they will want to be on it. Banks will want that diversity as well. So what I believe is you will start to see large requirements coming from Invercargill, not only from our data center, not only from all the other data centers, but from telecommunication users that will use a submarine cable. If you think about a hyperscaler, they will not come with tens of gigabits, they will come with terabits in Invercargill, terabits in Invercargill, terabits in Sydney, and they will want to link the two to create that loop that they need. So what it means is the connectivity between the North Island and the South Island will become critical for New Zealand. And we all need to be ready for that. And that's it for now. Thank you.
Quick question. How likely do you think the Tasmanian link would be? Every submarine cable project that I've been tangentially related to, Tasmanian government has been either disinterested or almost hostile to having more cables land there. Is AI enough that they go, ooh, yes?
So what I can tell you is we are, that's a work we're doing with the government. So they realize that they have missed a couple of opportunities in the past, and they are keen not to miss that one.
No more questions? Okay. Thank you very much, Pierre.
Thank you. Cheers.
Right. Now we have Conrad from Arista. And Conrad's going to talk about OpenRack, and you're using it in New Zealand, I hope.
Absolutely. Hi, everyone. Yes, I'm going to talk about OpenRack, and in particular, the experience that Weta FX had with deploying OpenRack v3 with the liquid cooling in their data center. Right, so clicker. So OpenRack is part of the Open Compute project. And the Open Compute project was started many years ago, initially by Facebook, where they said, okay, how do we make our data centers the most efficient that we can? And so it was an initiative that a lot of other hyperscalers have jumped onto for open hardware, open networking, servers, etc. And part of that is the OpenRack format. And so, OpenRack, it's a little bit different to the 19-inch rack format that everyone knows. It's a little bit wider, gives a bit more space for your cabling and cooling and whatnot. And it does involve a new 1OU rather than a 1RU. And so OpenRack version 3, not sure why my clicker is not working. Oh, sorry, okay, I've come back a bit. There we go. Sorry, working now. Right, so OpenRack version 3 implies that there was an OpenRack version 1 and 2, and indeed there was. Really, it's only now with version 3 that it's become practical for an enterprise deployment. We can see here the first version, ORV1, had 3 12-volt DC bus bars on it, fixed power shelves, battery backups, etc. ORV2 came a little bit better, but we've still got, open conductors and clamps, for power delivery. But with OpenRack version 3, we've got some upgrades. It's now a 48-volt bus bar, so 48 volts of DC, and it is a blind mate power connector that's touch safe. So you can't stick your finger in there and give yourself 1200 amps or whatever it is. And so it's a very efficient system in that we've just got DC power delivered to the devices in the rack. We don't need to have loads and loads of power supplies doing all the conversion for our different devices. So the racks are available as a 44 OU and a 50 OU format. In practical terms, the 44 OU is the one that most people go for. It's equivalent to about a 48 RU regular rack, fits into the same kind of space. The 50 OU, I've been told, is a bit impractical because if you're getting kit delivered from your vendor fully built up, it's too high to fit into air freight or whatever. So unless you've got an NZNOG, it's a bit of a challenge. The other thing that ORV3 delivers is the option for liquid cooling, and we're going to go and have a look at that in a moment. So here's a few pictures to show what the bus bar looks like. If you can imagine, there's this big strip up the back that's got our 48 volts of DC, and you can see the connector from our equipment just plugs directly into it. Clicky click. And so with the ORV3 system, we have power shelves that are distributed amongst the rack, and they deliver our 48 volts of DC. So these are, again, completely standardized as part of the OpenRack standard. A 1OU shelf has got 6 power supplies in it, and if we're running N+1, we can deliver up to 27.5 kilowatts per power shelf. And then we can stack more of them into the rack depending on how much power we need in total. And we can see here there's a new power connector. It's effectively delivering 3 phases. We can see on the next slide, those 6 power supplies delivered 3 from each connector, so 3 phases, easy peasy. AC in, DC out. So I mentioned the liquid cooling. We have the option of putting the liquid cooling manifolds into the ORV3 racks. We can see here, these come in here. They have a return side and a supply side, and the equipment we'll see can have the blind mate connectors. Just again slide straight in, easy peasy to service. Server-wise, there's again a standardized server format that it's available from multiple vendors. I've included here a bunch I just did from a quick Google. And one of the other vendors is Dell. I included a few things from Dell. This one here shows the server with the liquid cooling connectors. So you can see how they just slide straight in. And yeah, I guess someone made a comment yesterday about plumbing, but it's all very easy. It's very clean. It just plugs in. No mess, no fuss. Here's another picture of some racks with in this case, the Dell servers deployed in here. So here we're seeing the back of the servers connecting into the liquid cooling manifolds. There's our DC bus bar. So very clean on the back side. On the front side, it's kind of like a regular rack. So great servers, awesome. What about network gear? Well, of course, you can just take adapters and put your 19-inch equipment into it. I can go out and get a shelf, get little ears, and there is effectively the standard DC connector that I can use to connect up my DC power supplies. We can do a little bit cleaner than that, though. We can look at, effectively, you can call them native ORv3 network equipment that come actually in an OU, the Open Rack form factor with the DC power supplies, connectors, and again, just slides straight in. We can actually see here in the rack. I also use this to point out the fact that there are still rails in the Open Rack format. They're just a standard form factor. Network equipment doesn't always come with them, but they sort of slot in here, and then there's a little latch on the front. We can also see here, how the network equipment is just connected into that bus bar. One of the things you don't think about too much, or you should think about, is serviceability. Fantastic, I've got my native Open Rack servers, I've got my native Open Rack networking switches now. If I actually want to test them, how do I do that on a bench? So there are little connectors, adapters available that you can put on a bench to test them out. You can also get little 12 OU versions of the racks with the liquid cooling available also. So now I'm going to talk a bit about deployment at Weta FX. Many of you will probably know Weta FX. They're known for their computer graphics effects and the movie industry, movie and TV industry. They have a lot of compute power. And they're up to about their 5th generation of their compute platforms. And they were in a situation where they needed a bit more capacity. There was a bit of activity last year that they needed to beef up capacity on. And the existing environment was reasonably limited in terms of physical space. The current, or the previous generation of servers, they had racks which were 31 kilowatts of power and air-cooled with in-rack cooling units. And effectively, the density of the servers was limited by the cooling, the air cooling. And so they investigated the Open Rack v3 solution, and what they've ended up with is environments where they've got 68 nodes per rack, each with 256 cores. Now, you can actually get bigger CPUs than that, but this was just the right sweet spot in terms of price performance. But that gives them 17,408 cores per rack. And effectively, with 2 racks of Open Rack v3, they could have the same compute power as 10 of their regular racks with the previous generation of platforms. From a networking perspective, it was reasonably straightforward. They've got 100 gig per second data to each node and an out-of-band connection to each node. So it's You can see the whole solution there in terms of the cabling. We'll look at it without the cabling in a moment. So from a power perspective, with that amount of compute in there, they're using 6 power shelves. Each power shelf is technically 33 kilowatts, but with N+1, it's 27.5 kilowatts per shelf. And they've also gone N+1 shelves, which still gives them 137.5 kilowatts available per rack. Current processing, they're topping out at about 108 kilowatts per rack, so there's still plenty of capacity. The power is interesting. That is 108 kilowatts of power over a 48-volt bus bar. Touch safe, all very well, but I still want to be careful. So technically that's 2,100 amps of current over that bus bar, but what they do is they distribute the power shelves. In fact, I think I've got a picture here that shows, you can see the power shelves that are distributed amongst the rack, so that there's no more than 800 amps at any one point on the bus bar. In fact, if I go back, we can just see here, that's the back of the power shelves. So there's a controller in the power shelves also that's actually PoE powered, so that they can manage them even when they're off. Right, so it is, this is a picture of their environment. The 2 ORV3 racks there on the closest to the camera. It's direct liquid cooling. So the direct liquid cooling is the CPUs are cooled. So the servers still have fans, they still have memory and other components that are air cooled. But they've just gone with the, you can get ones that are liquid cooled memory, but they've gone for the direct liquid cooled CPUs. Because they now no longer need the in-rack chillers, there's actually less space taken as well. The open rack racks, the retail racks, the 750 mil wide, they actually take the same footprint as the 19-inch racks, and there's a slight difference in height, but the 44 OU is equivalent to about 48 RU, as I mentioned. They effectively built a new room to support the open rack deployment. They've got space for 12 racks, so they do have room to grow as required. One of the challenges they ran into was they're looking at multiple server vendors. But when you start to involve liquid cooling, the server vendors start saying, hey, actually, we don't want to share our equipment on the same cooling loop as other equipment, because they're concerned about interactions of different materials and whatnot. The solution for that for Weta was to say, okay, they've put smaller heat exchangers per row, so that they're not necessarily committed to a single server vendor. And you can't really see it, but there's a little picture of that in-row exchanger there. Now, from a real-world perspective, the results they've achieved. The previous G4 servers, the CPUs would run at about 85 degrees centigrade. And that meant that they were hitting thermal throttling. They were only able to run about 10% of the time with turbo speeds on those CPUs. And as it turned out, about 20% of the power those servers were using was just to run the fans for the cooling. Now the CPUs are running at a much better 65 degrees centigrade. They can run in turbo mode about 30% of the time. And of course, they've got much higher density. So 5 times the density in terms of that compute. What they're looking at doing next is expansion of CPU capacity. Obviously, it depends on how things are going with the business in terms of the production schedule. But they're also looking at GPU capacity. They currently have a different solution for GPU, but with ORV3 and liquid cooling, we can again get much higher density for GPUs. the nodes they've been considering, they can get 8 to 10 nodes in a rack rather than 3 to 4 in a 19-inch air-cooled rack. And they actually won an award for it. So there was this Oceania Cloud and Data Center Awards last year, and they won the Energy and Resource Efficiency of the Year award. So yeah, it's had recognition for what they're doing. Now I'd like to talk a little bit about what's happening with OpenRack. There's a few variants out there and a few interesting things happening in terms of really densifying things even more. ORv3, even within the hyperscalers, there's a little bit of variance between what some of the hyperscalers do. So ORv3N is a networking specific version of ORv3. The reason they've developed this was that they found that having that bus bar right in the middle of the back of the unit kind of annoying. So the ORv3N is a variant where the bus bar steps off to the side to open up the back of the rack. And Google and Meta use that. Oracle have a variant where they actually still have 19-inch rack mount within the OU form factor. Also on the networking side of things, the WetaFX deployment is just air-cooled network switches. And really at this stage, there's no, for many use cases, particularly in the enterprise, 800 gig and 1600 gig switches don't really require liquid cooling for the density of the current deployments. But as you start to get bigger and bigger AI clusters, more and more bandwidth requirement, we are seeing demand for liquid-cooled networking equipment. So there's an example here of a switch, which is a 2OU switch, which is 64 1.6 terabit interfaces, liquid cooling. But these are still using OSFPs, but they're the OSFP with a riding heatsink. So they're slightly thinner. They plug into the switch, and there's a liquid cooling loop in the switch that's effectively applying across all those OSFPs. So that's something that's in use for AI at the moment. But then looking forward, there's been a couple of mentions already this week about the new XPO optical form factor that was launched at the OFC conference a couple of weeks ago. So this is an open MSA. It's kind of the next thing after an OSFP or QSFP. And it's a form factor which is 12.8 terabits, 64 channels, so the equivalent of 8 1.6T OSFPs, but it has an integrated cool plate. So it plugs in, we can see here, actually plugs in to your liquid cooling loop and comes through the XPO. So the interesting thing about that is that if I take that form factor, I can fit 16 of those into a single OU, which now means I can do 200 terabits per second in one OU, which if you put it in an OpenRack rack, I can now do 6.4 petabits per second in a rack. Now it sounds obscene and it's crazy, but it really is about these AI scale data centers. In fact, if you look at some of the maths, if you have a 1,000 rack AI data center with 128 accelerators per rack, the current generation of networking, you need to support those 1,000 racks, 1,400 racks of network gear. But by going to this sort of density, you can effectively take it down to 25% of that. So 350 racks, still a lot, but it brings it down from being 60% of my real estate to 25% of my real estate. All right. Looking even further ahead, there are a few variants out there. There's Mount Diablo, which is another open rack format. Initially Microsoft, but now part of OCP. This is based on 400 volts DC and separate power and compute racks. And there's another one that's had a bit of attention recently, Open Rack Wide. And this is, if you think about the scale-up challenge of your AI accelerators in a rack, you can fit maybe 72 or 128, which is a scale-up problem. If I want to get bigger clusters, let's make the racks wider. So the Open Rack Wide form factor is 1.2 meters wide by 2.4 meters high. And so they can effectively double the number of accelerators they can fit in there. And so AMD have launched the Helios with this, and the Meta big effing rack, the BFR project from Meta. I'm kind of curious, it's all open source or open hardware specifications. Meta have even said, well, now that these racks are so big and so heavy, we actually need special tugs to be able to move them around our data center. And they're going to publish the specification for the tugs into the Open Compute project. Because these things now weigh like 4 to 5 tons when fully populated. Right, so that's it for me really on the Open Rack version 3. I've got a few references here to the Open Compute project, specifications, and also that XPO MSA for those interested in the optics. And I just wanted to call out Thomas Keir at WetFX to acknowledge his support and permission from WetFX to talk about the project. That's it, I finished a bit early. Any questions?
So I was in the US when the OCP original spec was published, and one of the big problems, and you kind of touched on it, was that scale down is just impossible. So especially even when we're talking about some of the larger network operators in the US like AT&T and Cox, when they started to get into compute for NFV, for all those type of, now kind of bread and butter, they couldn't get OCP compute because the scales that they needed were too low. And so just trying to order off HPE a white box kind of rack of OCP was impossible because Meta and Microsoft had the scale, but the telco segment just, they're not in the compute industry, right? So they're not after 4 racks of stuff. They want a rack of stuff to run their NFV workloads, and that's it. And so it was impossible to order it. Has that been solved, or is that still an issue?
I would say it has. Look, I know WetFX is a big customer for the local, well, for the compute providers locally in terms of local specifications. But there were, I probably can't talk about the vendors, but there were 2 vendors that were absolutely keen to and able to provide an open rack solution here. It ended up being, it started off, was going to be 3 or 4 racks. It's only 2 so far, but there was no issue with providing that level of scale. I think it's only really very recently that has become more practical. And the same thing even with looking at the ORV3 format networking gear, that has always been very focused on the hyperscalers. It's only really leaking into the enterprise space now. But I suppose my message is, it is possible and potentially very practical. Here we go.
It interested me that there was only one DC bus bar at the back of the rack. Is there any, have they got fusing or anything in it? I mean, in the rest of the world, servers, telco, anything, there's typically always 2 supplies and something shorts out and it takes out your A feed, you've still got your B feed. Is that a problem that a short on that bus bar could take out the whole rack, or have they got something built into it to sectionalise it or anything like that?
To be honest, I don't know about what's inside the bus bar. As far as I'm aware, it's massive chunks of metal. And the diversity comes from the fact I've got 6 different power shelves, each with 6 different power supplies. I don't know, I suppose if I went over my 2,000 amps or whatever, it might melt somewhere. But sorry, Yeah. Oh, yeah. Sorry. There's two separate. There's like a supply and a return, if you like. And there's kind of a insulator in the middle. So that's how those connectors work. But I take your point, right? If I'm a hyperscaler and I lose a rack, I probably don't care quite so much. But you know. Yeah.
Okay. No more questions. Right. Excellent. Thank you very much, Conrad.
Cheers. Thank you.
Right, so now we're up to the final sort of half hour, which is our lightning talks. So if everybody who's got a lightning talk can be somewhere close to the stage, we've got a few people to get through. Just before we start that, if you're a sponsor, your banner has now been packed up and it's ready for collection, I believe. Okay, so first lightning talk, we have Cams to talk about Peering Asia.
So, hello, I'm not representing Akamai this time. I'm representing the Peering Asia Steering Committee, because I'm part of it. So I just want to let you guys aware that we'll have the Peering Asia event 8.0, our 8th edition, in coming November. So all the information is here. So it's going to be on from 3rd to 5th of November in Osaka. So if you are into peering interconnection, no matter you are an ISP, content, hosting, internet exchanges, I mean, as long as you have an AS, you do peering, so feel free to join. I think the registration will open in due course, maybe in 2 months' time. But if you're also interested to sponsor, stay tuned. We'll have the sponsorship package also available very soon. So hope to see you guys in Osaka. Thank you.
Right. Okay. Next up, we have Josh from .NZ talking about some community feedback.
Right, kia ora everyone. For those who don't know, I'm Josh from Internet NZ. We do authoritative DNS for .NZ and CCTLD for New Zealand. Just a few little things I thought I'd get up here. We're still working on a lot of internal projects and we don't have a lot to talk about since there was no technical talk we did this year, but we're still progressing our DNSSEC work and hopefully we'll have some more information for you guys later in the year about how we'll transition and cut over to the new system we've been working on. And we've been slowly moving stuff out of some older data centers. So we moved one of our NTP servers. You may have noticed the IP address change, and we'll be doing another one later this year as well. But the main reason I wanted to jump up here is we're currently working through our next 5-year strategy for infrastructure, how we do and deliver .NZ to all you guys, and fun times, how we deliver .NZ. We've also, as part of that, we'll be doing some planning for how we deliver the registry for .NZ, and because that's coming up in 2028 for its next hardware refresh and any considerations there. So we've also got a small little bit on the side, the public good infrastructure that we do. So that's our 4 NTP servers distributed throughout the country, which are publicly available to use, and currently as well, the PGP service that we run. So I'm just really sort of calling out if anyone has any feedback or information that want to speak to us about how we can better provide those services to you. There's locations or places we should be better connected or anything like that. Just reach out to us is the main call out that I wanted to do. And just email us at registry.internetnz or scan the QR code to open up an email box. And yeah, look forward to hearing from you if there's anything. That's it.
Okay, thanks Josh. Next we have Steve, whose talk was previewed during the middle of Josh's talk, but anyway, Steve's talking about out-of-band access.
Thank you to the NZNOG team. What an awesome event, so really pleased to be up here. I wanted to talk about something that I've been working on. A bit of a challenge, found a solution, just wanted to share it. So here we go. So out-of-band access simplified. So I work a lot with customers on designs and data centers, WANs and so on. I kept hitting a problem. I couldn't find out-of-band serial solutions that scaled down. I wanted access to console ports. A lot of the equipment had single power supply, maybe a little wall wart that would like to fall out on the rack, awkward rack mount solutions, limited network interface types, often quite clunky to set up and use. So I went looking to see if there was a solution that was better. There was a whole lot of SFP holes sitting in the out-of-band switches that weren't being used. Those switches, some of them had dual power, they had really good networking and didn't need any more space in the rack. I wonder if we could use those. I found an SFP, with some help from somebody else, that had a serial port on it. And I was like, yes, this is great. But it didn't play nice with the vendors. A lot of them just wouldn't bring the port up, didn't like it as an SFP. Didn't have DHCP, didn't have SSH. So you couldn't manage the thing easily without a lot of work. And then non-standard pin out. You couldn't use a standard patch cable to connect it to your console port on your Cisco, your Juniper, whatever. And it was still clunky to use. So I decided to make my own. What a challenge. But I wanted an SFP that just looked like a regular SFP to all the networking equipment. I wanted it to use DHCP, but fall back on a known IP address if it couldn't get an address. I wanted it to run Telnet, SSH with a CLI that made sense. But I also wanted to go straight to the serial port to manage the thing. And it had to be a standard port, right? So you could just use a cable, plug it into your Cisco, not a rollover cable, no special pinouts, off you go. Now, being a network geek, there were some niceties I really wanted. I wanted LLDP. So you can actually find this thing. You know, what's its IP address? Where's it hiding? Has it worked? So I added that. Now, lots of the switch vendors do Ethernet auto-negotiation differently. So I wanted a box that goes, so you want to do negotiation that way? I'll do it for you and come up and not be arguing with the switch. I wanted a known MAC address range, so I had the fun of figuring out how to buy MAC addresses, so I bought a block. So that when you're looking for it in your DHCP server, you can find it. And I wanted a simple CLI. But I had to enlist the help of a friend. We did the circuit design, we used KiCad, we made a PCB, and we got it made and assembled in China. Turned out to be quite an interesting process. We sourced SFP cases through Alibaba, and we did the final build, testing, and loading the software in NZ. So this is what the PCB looks like when they come. So you get these massive sheets of PCBs, and then we have to have all the fun of snapping them off, and we get that little module there at the bottom that you pop into the case. Along the way, we had to learn a lot about how SFPs work and behave, so we ended up making a lot of our own tools as well. So the top's a little dummy board, so you can bring all the SFP pins out of your device, and the one in the middle is like an extender, so we can snoop on regular SFPs and see what they're saying to the switch, monitor power, and all that kind of stuff. And then the final thing with what we're actually working with is that SFP shell, and it's got the board inside it. And I thought, what's better than one port? 2 ports. So you can have one regular port with hardware flow control, or with a breakout, you can have 2 standard RS-232 ports with no flow control. Turns out most network devices on their console port don't use hardware flow control anyway. And I thought, ooh, that leaves a spare pin. So I added some power. So through software, we can turn power on and off on a pin. So in the future, we can drop out some power to a micro. You can have some sort of active device there, speaking RS-232, getting some power, I don't know, a little display in the rack or something. So here's one in action in a little EX2300. Looks like a standard SFP. That cable's going off to another Juniper switch and connecting at 9600, so none of these 400 gig, 800 gig stories. This is as slow as we can go. But hey, it's working, and really neat to see it in action. The other issue I had was, I've built some of these. The remote access was always clunky. So vendors had something that was complex to set up, needed IPsec, OpenVPN, or some magic reverse SSH tunneling to get things going, which you can do, but it's a pain. The GUIs are always not that nice to use. So, help of a friend, we thought, right, what would a real portal look like? So, it could be used in the cloud or hosted on-prem, using the latest sort of web tools to make it easy. and get rid of all those weird things. The SFP, you just tell it to connect home, just does TLS, punches out through firewalls, just looks like HTTPS. But the local CLI, SSH Direct, they play nicely with the web terminal. So you can be debugging through the web interface and have somebody on the SSH connection at the same time. So here's a little dashboard. You'll see all your SFPs once they're registered. Connect in, you click on it. Here we're changing the settings on the port so we can change the baud rate. You can do some other detect stuff. And then click on the terminal button and hey presto, you're straight in. So really nice little JavaScript-based terminal. I've logged into my EX in the lab, I'm running commands. And I've been torture testing it, taking entire MX configs, dumping them on an MX and watching and learning what's wrong. So that's where I got to. Yeah, and I've given them away to lots of people to test, getting some feedback. And if you're interested, would love to get your feedback. Started a little thing called Wetatronics, but reach out to Searchlight. We're the ones that keep seeing the problems and would love to help. Thanks.
Right, thanks, Steve. We've got a couple of updates to finish with. Next one is Dave again, and he's representing APNIC.
All right, other hat on. So this is just a bit of a general update. I'm going to talk about Dash, a little bit of a policy update because the Kiwis have been active, or at least one anyway, and upcoming conferences. So for those that don't log into my APNIC every day, we have a thing called Dash. It's a network health dashboard. We can spit out things like routing status, suspicious activity, potential security vulnerabilities, and any bogons that are transiting or originating from your network. This is available for all APNIC members, so just log into your My APNIC account or log into dash.apnic.net with your credentials. If you have multiple ASNs or multiple sub-accounts sitting there, you can just hit the drop down and go into the correct one. So routing status Dash sort of looks like this. We're just checking for rower mismatches, all that sort of stuff. So this is my training account, not many resources in there, it's pretty quiet. But the other nice thing from this is you can also create alerts. So if somebody starts originating your prefix, you'll get an alert. If you have a mismatch on rowers that you've created, so you're announcing something in BGP, but your rowers don't match, we'll create an alert. And you can get that alert through multiple different channels, email, SMS, webhooks, Slack, etc. Suspicious traffic. So this relies heavily on one of our projects called HoneyNet. So we're looking for traffic coming from your networks that are doing all the typical bad things, so password sprays, port scanning, that sort of stuff. This is off a carrier in Indonesia, so at least they've had a decrease. They're down to 77% of prefixes doing stuff. But this is the summary screen. We can see your prefixes compared to the rest of your country again, so Indonesia, not looking great. And you can get actually a report of anything that is coming from, or what IP, what subnet, what IP addresses, what protocols, what did it try doing. You can download all this data as a CSV, so you can see even more detail. So you can see the password attempts it tried to do, that sort of stuff. So pretty neat. Next one is new. This is a potential security vulnerabilities dashboard. We've partnered with Shodan to basically leverage their API. We check your resources, or we check Shodan for your resources. We've set up a few specific ones that we consider high-value targets. So things that provide very large DDoS and reflection and amplification sources, as well as things like, I don't know, unauthenticated SMB v1, v2 file servers that just give you data for nothing. Anonymous FTP, while sometimes it's intended, a lot of the times it's not. So this particular dashboard we don't have alerts on yet, coming soon. Again, it gives you a nice little list. So if you click into the vulnerabilities, it gives you the IP, the host names, and the problems that were found. And last but not least is the bogons. So are you propagating or transiting bogons? So this is for a carrier in Australia, and they're passing on 205 bogons. For people who don't know what bogons are, you should by now, but it's addresses that shouldn't really be on the internet. So things are unassigned, reserved, or RFC space that they're pushing through. Policy. Everyone loves policy. It's so exciting. So a couple of proposals got through in the conference in Vietnam. This one is about who is privacy. This was proposed by your very own Jonathan Brewer. It reached consensus at APNIC 60 in Vietnam. Basically, we've started redacting private info out of bulk whois, with the exception of IRT. So we started doing this on the 9th of March. It's been active since. Just a little bit of a background. We contacted every bulk whois user for feedback before we did anything. 4 people responded, 2 of them were John. So he has 2 bulk whois feeds. And within about 3 weeks of us implementing it, we started getting why is this data missing? So if this data is missing for you, it's not our fault. We told you. We told you it was going to happen. So regular whois searches aren't affected. So if you're just doing a whois query from command line, you'll still get that info. So a lot of this data is allegedly being used for, what's the word? Sales calls. So we'll try and clean that up for you a bit. The other big one, but it doesn't really affect us too much in this part of the world, was revocation of non-functional RPKI certification authorities. So what this basically means is if you're running a self-hosted RPKI repository and it goes offline for 60 days, we're going to cancel your certificate. There's only about 30 within the whole of APAC that are privately run, so it doesn't affect that many. We only had, I think, 2 that were at risk when we implemented the policy. And the last one is version 2 of Prop 167, which was publishing statistics on directory services usage. You can guess as to who proposed this one as well. So very soon, before the end of Q2, we will start publishing stats that we have listed here. So number of queries received over whois, top 1,000 ASNs that are pinging us, the types of queries, is it coming in over whois, or are they using RDAP, etc. So this, I think, is going to shape the next ton of John's proposals that I'll have to read. with love. So why should you participate in policy? So everything that is done in terms of number of resources is decided by you. If you propose stuff, it gets discussed within the community decides whether or not it's worthwhile, and then we have to implement it. These changes, as I sort of highlighted with the bulk whois, can affect things that are happening. So you need to know what's happening, and if it's going to adversely affect you, maybe you should have a say about it. Like I said, we contacted 420 users and got 4 responses. So people are not listening. So you've got to make sure that whatever your organisation wants to do, your needs are represented. So make these policies work for you, not against you. A couple of links for the current proposals archive. If you're not part of the Policy SIG mailing list, just send an email to sig-policy-join at list.apnic.net and you'll be staying up to date. And the last thing is upcoming conferences. So next one will be APNIC 62 in Mumbai. From the 3rd to the 10th of September, we'll be running 3-day workshop program plus usual conference stuff. Then Apricot alongside of APNIC, APNIC alongside of Apricot in Hong Kong next year, 28th of Feb to the 4th of March. Same deal, there'll be training as well as the workshop. And get the AI working to get your business case to the next one in Mongolia, from the 3rd to the 10th of September. I've been to Mongolia 3 times in the last couple of years. It's definitely a must-go-to destination, especially if you like vodka and meat. And that's it from the APNIC side.
Great, thanks. And lucky last, we have Morgan from Megaport.
Thanks for the opportunity, NZNOG. Just provide some update from MegaX. It won't be a technical session or a sales pitch, just a quick update, a couple minutes, just exactly the time you need to get a Megaport service up and running. Yeah, this is a picture I actually presented last year in NZNOG Napier with all the locations we actually up and running with our gears and the connectivities. And based on that, provide some update to the NZNOG. This is a current location we are running our services. All the amber ones are actually we adding more data centers in the region. All the red ones are brand new locations we are operating now. And you notice that we are entered the new, like largest population in the world, new country, India now. So we can have all your connections. I'm not sure if that's a legit requirement to peer from Auckland all the way to India. That's actually now possible. Talking about South Island, last year we committed we come to South Island, and we actually made that happen. The first data center near the airport ready for service last October. And thanks for all the community members come to our launch event last year. And we are going to have a second one ready for service very quickly June this year. So if you have any other data center you want to see available on the Megaport portal, please reach out. We'll try to make that happen. So this is a general location, and more specific about the Mega-IX. This is again the Mega-IX map I showed in last NZNOG. We had 3 new locations last year, and this is the current situation. All the red ones, I guess roughly 15 of them, are new IX we have enabled during the past year. In the APAC region specifically, we have enabled Adelaide, and again, the India market, we have 7 locations now available, actually 7 cities, over 40 data centers. That's actually through a acquisition Megaport made last year called Extreme IX, a local IX operator in India. So we can now provide you peering opportunity in the India market if that's of your interest. Yeah, welcome to have a look of our looking glass as well as Extreme IX looking glass, and let us know if there's any interest to grow the community or grow the roadmap map. Talking about Auckland Mega-IX specifically, in the last year we saw roughly 4% of growth in the IPv4 prefix and over 10% growth on the IPv6 prefix. Actually, thank you so much for the community. New Zealand being really, I guess, good community in terms of participate Mega-IX responsibly. Please keep doing that, and please build your service with redundancy as recommended by Megaport. Last but not least, one more thing. I know Christchurch is not yet available for Mega-IX for now. So I have 2 paths available now. If you want to peer from Christchurch to Auckland Mega-IX, we can provide more affordable long-haul connectivity for you to get here from here to there. The other thing is I want to try that. I'm not sure if Gav here. If any of you want to see a Mega-IX Christchurch version, please let us know. We're gathering all the requirements, and we'll see if that's something we can do to help the community. I know we are probably number 2 largest IX provider in New Zealand. Joe is there, maybe number 2 or number 3, I'm not sure. Yeah, so let us know if you need use that as an alternative or backup, or just in case. We're happy to support the community. I think you probably all know Gav, somewhere in the room maybe. Gav is our interconnection senior director, and KB based in Wellington, happy to travel to any city in New Zealand to gather any requirement or feedback. Myself based in Melbourne, but I'm happy to fly down to New Zealand monthly or quarterly if it's required. Yeah, reach out to us. Which data center do you want to peer from? Which city do you want to peer? And which other entities or companies you want to peer with? We'll try to make that happen. Thank you so much.
Right, congratulations everybody. You have not only survived the largest NZNOG, so well done everybody, but we're finished. So see you next year in, I can't tell you yet. We're negotiating, we will be in the North Island, probably the upper North Island, but we haven't quite got contracts sorted, so I can't say. But yeah, looking forward to seeing you next year anyway. I hope you will have good activities tonight if that's what you're doing, and safe travels home. So thank you very much. See you again.